Hello YouTube. Here you can see the grass ball that we're going to do. We're gonna do 13 until like where are we? Like 20 or something. We've done symmetric matrices, right? I think we
Uh,
have. This shows how prepared I am. On
Wait,
the right side we have my
I
favorite
think you
tool
guys
for.
are.
Hmm?
I think actually you are at. Let me just check, because I joined y'all and I finished. The last one I did was 11.
Yeah, no, no. I actually I know I did 12 because I did it afterwards. Like I did 1 to 11 on one day and then 12 on another day.
Yeah, okay,
Because,
so you're at 12 to 20.
yeah, but
Basically.
like I think we still have lecture 21 to do tomorrow. But I'm not sure if that's 21 or 20. But either way, we'll do this one, see how far we get. Whatever.
Yeah.
Did you make a separate Graspo account for this?
No.
No,
This
he
is this
just
is.
hasn't done anything like a chat.
Oh,
Wait, you can't, right?
Hmm?
You
I'm
can't.
not sure if you
Can
can.
you make a separate?
No, no, no. It's bound
Oh.
to your university account. And
Oh,
here
is
we
it?
have a spreadsheet or a list with all the theorems, which is also the reason why this isn't going on public YouTube. You can find this PDF on in my Juris General chalkboard. It's one of the messages there. Just it's called LA lectures underscore LA.pdf. Just download it, open it. You'll see everything in there. All right. We are going to. What do you guys think? Should we do the pre-lecture exercises? We're not going to do the additional practice material because fuck that. But we can do like the update your knowledge and the second thing. So
I'm a bit. I think eventually you also just went to post lecture only. Oh, really not?
Mm,
no, I think it is all the
I mean,
pre-lecture.
we
I think
can
post lecture is just
we can
enough.
do pre-lecture and
Oh yeah,
post-lecture.
live split.
Should be fine.
Important.
Yeah, this is a speedrun after all, right? We're doing knowledge percent, by the way. So the moment we understand it, it's good. So we're not going 100%. There are some motherfuckers out here who are doing green percent. How?
I did
No.
3% for calculus.
You did green percent for calculus?
Yeah,
I
Dude,
feel
respect.
wordless.
No. That's
I passed
actually
calculus
pretty
after
good.
that though. So you know.
Knowing calculus well will help you in many other subjects,
Yeah. Fun fact.
like BTS. Next,
Fun fact. If you fail calculus, there's like I think 75% chance you'll also fail like the uni from statistics of last year. I thought I saw somewhere. My dad sent it to me a while ago, but yeah. Okay, let's get started because we are already like 22 minutes in and we haven't done a single exercise. So let's go. Bum. I didn't make any self splits because I don't really care. If you want to do that, you can do it yourself. So we are starting out. By the way, every time I'm going to also look at the lectures real quick, and then I also have this one, but this one is just the theorems.
Oh my god.
Oh no, my username. No, leaking it.
No.
No. My full name, which is Googleable. No. Where were we at? Complex eigenvalues. Lecture slides. It's just so funny to see this shit when you don't expect it. Let's see. Real part of an imaginary number, imaginary part of an imaginary number, the conjugate, we know all this stuff. If you have a real, if you have a matrix with real entries and a number is an eigenvalue, then the inverse of the conjugate of that number is also an eigenvalue, and the conjugate of the vector is also an eigenvector. Taking the conjugate of a vector is the same as taking the conjugate of all of its parts. And this is just, this makes sense. This is an eigenvalue, another eigenvalue is conjugate, so change the plus into a minus, or other way around. You get this.
Hello, person.
Hello. I see a lot less people are doing ADS than I thought. That's good.
well, ADS is terrible, so
Hmm?
ADS is not kind of not so good. So why would you do ADS?
Fair. 2v2 matrix with the complex number. Then there exists an invertible matrix such that this is a thing, and then P can be constructed as the real part of V times the or the matrix consisting of the real part of V and the imaginary part of V, where V is the associated eigenvalue with A minus BI. I see, interesting. Cool.
Interesting percent.
Interesting percent. Okay. Determine the eigenvalues by answering the following sub-questions. Compute a characteristic equation. Well, we start out with the matrix 2, 2, -10, 6. We want the null space of this minus lambda I. So then we. By the way, for the people new here, I do minus L for lambda because I can't write a lambda sign, and even if I could, that would be a lot of copy pasting that I can't be asked with. So this will become our matrix, and then we want the characteristic equation. So we want the determinant of this is equal to 0. Well, the determinant of this is 2 minus L, 6 minus L, minus 2 times -10 is equal to 0. Working this out gives, this becomes 12 minus 2L minus 6L plus L squared minus, and this becomes a plus, and this is just 20.
You can just write it as is on Graspo. You don't have to.
Oh yeah, I don't have to simplify. That's true. I do like simplifying, so I'm gonna do it. But for the next one, I probably won't. You're right. So
Yeah, it's generally not a good idea to simplify if you don't have to. That's just
true.
another way that you can make a mistake, and obviously you don't get any partial points here.
Yeah, that's true. Fuck this testing thing because you don't get partial points. So we have lambda squared minus 8 lambda plus 32. And because it's an equation, we have to equate it. So the polynomial would just be this part, and the equation is this part, right? There we go. Find the eigenvalues. Well, I mean, since we're going to have to find eigenvalues, I had to do this anyways. I'm guessing this is going to be complex, so I'm going to use the ABC formula. So we have 8 plus or minus the square root of 64 minus 4 times 32. 4 times 32 is 128. This becomes -64. And we divide this all by, I'm just going to say divided by 2. The square root of -64 is 8i. You divide both sides by 2. So then the two answers to this is 4 plus 4i and 4 minus 4i. Repeat eigenvalues according to their algebraic multiplicity. Separate your answer by commas. So 4 plus 4i, 4 minus 4i. Does it matter which order I do them? Does it have to be like from small to big or something?
That would be very stupid, but
Yeah, we can know Grapple, right? So
It doesn't matter. It calculates it themselves, I think.
there we go. Oh yeah, well this is just flexing.
what?
They split off the squares.
I entered it, but
Hmm?
oh yeah, no.
Yeah, can you stop sharing your screen?
Oh, I am epic.
Epic, Uber Gaming. You computed the eigenvalues, blah blah blah. Now work towards computing the basis for the eigenspace in C2. You need to solve a homogeneous system. Give the augmented matrix. Oh wait, okay. So we have the augmented matrix. Oh, that's the wrong one. That's this one. So it's a 2x2 thing that we want to solve for 0, 0 because we want the null space of it. And that is just the original matrix. So what we're solving realistically is like just the null space of A minus lambda I. However, our lambda is, in this case, 4 plus 4i times the identity matrix. So that means we have an augmented matrix which consists of, as first part this, and the second part 0, or the 0 vector really. So I'd underline this. So let's see, we start out by 2, and then we do minus 4 plus 4i. Here we have 6 minus 4 plus 4i. And then the rest is just 2 minus 10. I think this is correct. Dude, I'm good. Okay, and they just simplified it, but I didn't want to. Find an echelon form. Fun. Okay, we're working on echelon forms with complex numbers. There's no way this can go wrong. So I have the thing -2 minus 4i, 2, 0, 0, -10, 2 minus 4i. Oh, okay. Find an echelon form. So I want to have a multiple of this that fits into this. Um, Now I need to really think back about like how I would do this in a normal way and not intuitively, but actually mathematically. So to get rid of this, I would first of all I'm gonna multiply both of these things by -1 because that makes it easier on my brain. I also instead of just doing this, I should also flip these signs because I'm a dumbass. Okay, so what do I have to subtract from the bottom to get to the top? What I have to subtract for that is 10 divided by 2 plus 4i. So I subtract this times the first row from the second row. Yeah, and then this will go away. But that means I subtract. So then let me see. Let me first focus on this. Let me focus on this cell here. So I get
Won't it be easier to first calculate the conjugate of the first row?
Hmm?
To multiply the first row with its conjugate. Wouldn't that be easier?
with its conjugate. Why that?
To get rid of
Oh
the
wait.
imaginary part, basically.
Okay, let me see if what that does, because that's actually an interesting point. So then I multiply this
Yeah, basically, yeah.
by the conjugate of this number, which is -2 plus 4i. My matrix is not big enough for this. -2 plus 4i. So then we get, let me see if I can expand my matrix a little bit. -2 times -2 becomes 4. Then we get -2 plus 4i is minus 8i. Then we get -2 minus 4i is plus 8i. And then we get minus 4i plus 4i, which becomes plus 16. These parts cancel. This becomes... Oh. Is that correct? Yeah. And this becomes 20. A very good point, because 20 and 10 is a lot more fun to work with. And then this
Noise.
becomes...
Noise.
Yes. And this becomes this, which also makes a lot more sense to work with. Wow. Okay, this is why I'm doing it with you guys and not alone, because I would spend like 10 minutes on that. So what I do now is I divide this thing by 2, this row. And then I add this row to this row. So this becomes 0, and this becomes 0 as well. Huh. Then I divide both things on the top by 10. Okay. And then I have equals to, and then this goes away, so we have x1 is equal to 2 minus 4i divided by 10 x2. Well, I mean, at this point we only need the echelon form, so let me get that first. I was first thinking like why is this a thing? But of course it has like for something to be a basis of a echelon or a basis of an eigenvalue, it has to have at least one free variable, right? So yeah, of course these are like multiples of each other, the bottom row and the top row. Okay, so then this becomes, let me revert this, change back here real quick. Oh, so this is 1, this is minus 2 minus 4i divided by 10, and it becomes 0. Wow! Okay, cool. To find a basis for the eigenspace. So because it's a basis, it's a set. And the set contains a single, a single 1 by 2 vector. Namely, and then we only look at this one. So x1 is 1x1 and 2 minus 4i divided by 10. If this is correct, I'm literally going to yell. Okay, not literally, but it would surprise me. Oh, what? Okay.
You gotta switch x1 and x2 around.
I gotta switch, huh?
Yeah, so x1
Oh,
is
because x2 is the free variable.
Yeah.
Okay, yeah, that makes a lot more sense, yeah. So just switching it around would work. I fully put my trust in you. There we go. Yeah, that makes sense. And x2 is 2 is equal to x2. Yeah, okay. Cool. Compute the basis for mine. Ugh. Wait, actually. So I'm thinking, right? Since this is the complement of this eigenvalue, does that mean the basis is also a basis consisting of the complements of the base of the other one? Or is it just for the...
Try it.
Yep. Good point. Can't argue with that. So then this becomes 1, and this becomes 2 plus 4i divided by 10. Haha, nice!
Bro.
Bro, we have like 5 brain cells together. Holy shit, nice. Wait, that was
But it
the pre?
more- Yeah, that was just the pre.
Wow, that
That
was
was
like
the easy
relatively
stuff.
quick. Oh, we go green! Woo! We go green on the pre-lecture. Ooh. Oh. Okay, guys, this is gonna be some real big brain energy.
Wow.
Whoa.
Man, I don't know
Why?
how to
Why?
do
That's
that.
very difficult.
Like,
Certainly.
dude.
1 out of 3.
Please make that the question about complex eigenvalues on the actual exam. Thank
Yeah,
you.
I will take that W. This one as well, though. So this will be... Yeah, this is the same thing. It's just a complement. And this is just learning of the theory, because as you can see here, if we look at the thing about lecture 13... Yeah, here. So for a 2x2 matrix, with eigenvalues a plus or minus bi, where b is not equal to 0 and a and b are real, then there exists an invertible matrix P such that this can be invertible, and P can be constructed as the real value, the real part of V and the imaginary part of V, where V is an eigenvector associated with the eigenvalue A minus BI. That's like literally what it says here. I sure hope I don't have to actually do that myself, because it sounds like a lot of work. complex numbers recap. Now that is something I don't mind. Woohoo! Did I wish? Now that's the good question. It's -5 or -5i.
Without the I.
I see. What's the argument of the complex number of this thing? Give an angle. Okay, so then we take the inverse tangent. Wait, not inverse tangent. That's the arctan. Of was it -b/a? Oh, so -2 becomes 2 over -2 square root of 3. Oh wait, that's the okay, the argument. Oh, so it's not negative. That's what I did. So it's the arctan of b/a.
Probably not between 0 and 2 pi or something.
Okay, what's the arctan of 1 over square root of 3?
Fuck. Wait.
There's probably someone here who knows that.
Pi over 6.
Pi over 6?
I believe so.
Oh, that should be in range then.
Oh, let's see.
I really trust this man.
I trust this man with 100. Oh, because it can be plus pi. And
Hey, okay, listen. I told you the good number, alright?
no, you were correct. I was wrong. Yeah, no, this makes total sense because if we bust out the paint,
Oh, yeah.
yeah, this makes total sense. This is a good,
This makes a lot of sense.
yeah, good exercise. Bad me. So this thing is located at what's the complex number again?
Negative,
-2.
negative.
So it's over here. We calculated this thing, but it should be plus pi to get over here.
Yeah. Yeah.
Yeah,
A
that's
good
something
exercise in properly looking at your complex numbers.
yeah. I was thinking about that just now. I was like, yeah, I might have to do that because I remember doing that. And I was like, nah. Okay. What's the modulus of this thing? Well, the modulus of in complex value is the distance from the origin. So that should just be -2 square root of 3 squared. So it's the square root of...
Crespo really has to do that.
Squared plus the let's see, so this is -2 squared.
Also known as 4.
Shut up.
Oh wait, it was actually the final answer. Oh, that was
Yeah.
fun.
Wait, I was at the
Wasn't
final answer.
expecting.
Oh yeah, so this is equal to 4 times 3. This is 12. This is 4. 12 plus 4 is 16. Square root of 16 is 4. So that makes sense.
I totally knew that.
Yeah. No, Colin has like 400 IQ. Oh, use the arctan function. Pog. Okay, so we have the yeah. So this first thing is the modulo, so the range from the origin, distance from the origin actually, and that is the square root of 2 squared plus 1 squared. Square root of 5, that's what I said. And then we have the arctan of 2 over 1. No, is that correct? No, it's the arctan of 1 over 2. Because again, the tangent of a complex function is b over a. Okay, so here we do it again. So we have the square root of -1 squared plus 4 squared.
I think you have to put the 1 in brackets. -1.
Oh yeah, fuck. Fucking hell. Graspel, man. That totally was my mistake, by the way, not Graspel, but Graspel, man. And then this becomes the arc tangent of, and they say,
Come on, Graspel should just know this stuff.
yeah.
If you type
Well, I mean,
one thing, you mean the other thing. Graspel should just figure
exactly,
that out.
exactly. So it's the arctan of 4 divided by -1. However, if we draw it in paint, so this number is -1 plus 4, so this number over here. And the range of an arctan is over here, so we have to add pi. Because the arctan of like -1 over, or -4 will probably be somewhere around here, and then we have to add pi to get over there. Woo! How many do we? 4? I guess they want us to actually know the material, huh?
That would be terrible.
Yeah, dude, I would cry. So this is negative negative, so this comes here, so you have to add pi, so that becomes the arctan of or just 1 over 3, because, you know, negative cancel out, plus pi. That went too smooth, yeah. I agree, Graspel. Wait, why is that wrong, though? It's like b over... Is it not plus pi? This number lies in -3, so the number lies over here. Arctan only gives something in this range, so you'd have to add pi. Yeah, I'm sure this is the answer. Why? Without this? Minus pi?
Yeah, they want it within a range of -pi to pi.
Wait, didn't I say between? Oh, I thought they said between pi and 2 pi. Okay. Yeah, no, okay, that makes a lot more sense.
Gotta read the small letters.
Yeah,
You gotta
motherfucker.
read the small letters.
I really hope they don't do shit like that on the actual exam.
They
They will
probably.
definitely
No.
do shit like that on the exam.
Yeah, like I'm gonna spend every extra minute I have rereading every question to make sure, like, you know.
For sure.
Oh,
I've got
that's
like
tough.
3 mistakes for myself in the calculus exam. Okay, and 4, this is like -2, 2, so this will be over here. I said the range of the arctan function is...
Ah, yes, plus 685 over 4. Thank you for these nice numbers, Graspel.
Yep.
Yes.
So this is the arctan of 1. Let's see. So the arctan of 1, where would it land us? So this is the arctan function at 1, that would be like positive something. But we have to...
Are you sure it's the arctangent of 1?
Yeah, because
So
it's...
just artist.
Fuck
Sorry.
you. It's -1. And then I add pi. Damn it! I'm just guessing. Oh, what?
You don't need to add pi.
Whoa.
Okay. Oh yeah. Again. Okay. The number blah 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 can be written as blah blah blah. Well, this makes this is pretty easy because we will actually get r
Let's just skip
times.
this. We don't need this for linear algebra at all.
I mean, you kind of do, but also not. E.
I mean,
Oh.
you only need to work with simple complex numbers, and
Well,
not-
no, not
you
really.
don't
In
need
the
to
exam,
convert.
I fully expect them to give us like the most annoying, hard, complex numbers in the exam possible. Like,
That would
expect
be
them to fuck you
horrible.
over. They probably will, and if they don't, then you're prepared at least.
Yeah, fair point.
So this is the so this is how they want us to, or this is how they project it. This is equal to r times cosine of theta plus I sine theta. Fun fact, 0 is actually mathematically equal to theta. What can I use as a number that like? Oh, I should probably do this then. Big O is equal to theta in this case because I don't have a theta key on my keyboard.
Could you just use T? That would be easier.
Yeah, okay, theta,
Or like a uppercase T. It doesn't really matter which one.
whatever,
it
it's good. Now it says right. Okay, so we have R is 1, so this just becomes cosine of t plus I sine of t. I love how it just makes my I uppercase, and that just doesn't work like that in maths. And we have the cosine of negative pi over 6 plus I times sine negative pi over 6. Therefore, the real part is the cosine of minus pi over 6. And the imaginary part is sine of minus pi over 6. Back to lessons. Thank you, Graphball. That was a really interesting refresher on complex numbers. Where do we actually get anything about the actual use of complex eigenvalues and stuff, or is this it? No, this is it. Okay.
Juist.
I mean, I guess I don't mind, but
There are still exercises in Grassbook for post-lecture exercises. There's no extra.
oh wait, so this is where usually the yeah, okay. So we should also do the post lecture of this one. Okay, yeah, that makes a lot more sense. I was like, what? Okay, compute. Oh, another one of these.
Juist.
Used. So let me make some space. Then we get 2 minus lambda, 1 minus 4, 2 minus lambda. Then we have 2 minus. Can I just say lambda Pog squared minus or plus 4 is equal to 0. Find the eigenvalues. Well, then we have to actually calculate it. Damn it. Okay, so not exactly what I wanted, but thank you very much. 2 minus L squared.
I think that is the first time I've ever seen Graspop copy out LaTeX properly.
Yeah, well that's because it's a LaTeX in their in my answer, not their question. Then we
Yeah,
have
fair
2
enough.
minus L is equal to the square root of minus 4, which is equal to 2i. Actually, this is plus or minus 2i. And also this should be a square root. So then we have, I add L on both sides, and I subtract 2i on, subtract 2i on both sides. Then we get 2 plus or minus 2i is equal to L. Rearrange that, gives me L is equal to. So then we have 2 plus 2i, 2 minus 2i. Man, I'm good. I love how they just did this, but I already had the answer in the form I wanted for that. Okay, to compute the bases, you need to solve a homogeneous system, give the augmented matrix. Well, this isn't too hard. So then we have, what was the original one? Yeah, so 2 minus, and this is 2 plus 2i, so this becomes minus 2i, because 2 minus 2 minus 2i. Then we get 1, then we get 0, then we have minus 4, then we have minus 2i, and then we have 0. Check my answer. There we go. And then I have to find a echelon form. Minus 2, minus 2i, 1, 0. Minus 4, minus 2i, 0. Imagine if there was an operation to swap these two rows around. Would be pretty cool. I'm going to multiply everything by plus plus 2i. So then this times 2i. Well, this just becomes the negative stripes away with the i's. This becomes 4, and this becomes 2i. Add the top one to the bottom one. What a surprise! They are multiple of each other. It's almost as that's a requirement for a basis. Divide by 4. This becomes 1. This becomes I over 2. This becomes is equal to. This becomes negative sign. And then we have x1 is equal to minus I over 2 x2, and x2 is equal to x2. So then we have the, oh, I already did a step ahead, but that's alright. So then we have 1 I over 2. Every time I say I over 2, my brain goes, oh, you mean pi over 2? No. Then we also get the bases. Bases should be this. And then within that, a vector. So this is minus I over 2, and this is 1. Did I fuck up my minus signs? Oh, I
You forgot the
did.
second vector, I think.
Hmm?
Oh no, never mind.
Yeah, because we are taking x2 as a free variable.
Yeah,
But let's see, what was my... Did I fuck up my minus sign? What? Why is this? Huh.
you have to enter the second vector as well.
But the basis only contains one vector, right? Because there's only one free variable. Find a basis for the eigenspace. Okay, let me try that again. So we have the basis, the set containing the vector, x2 is equal to x2, and this becomes negative I over 2. What? What? Negative I over 2, 1. What do you mean? This is...
Bruh.
Didn't you write that?
That's literally what I wrote.
Yeah.
Robbed.
I think I had the
You got
same
robbed.
problem actually. I think I had the
What I had
exact
was-
same.
Yeah, I feel like
yeah.
Graspel got pissed at you for not including +0.
No. It could be, but what I did to fix this is you multiply both of them by I, so you get 1/2 over I, or 1/2 I, and it will accept that. So yes, it's trial and error, but if your first answer doesn't work, just multiply both top and bottom by I, and it'll work.
You see, if they fuck me with this on the exam, I will literally like just file a complaint. Compute the basis for the eigenspace. Ooh, so guys, now we're leaping into dangerous territory. It is namely the exact same thing, but then the
By the way, it's way
conjugate.
easier to just enter those curly braces.
Yeah, okay, that's true probably. This is incorrect. Okay, and now if I multiply everything by I times I becomes -1. This becomes -1/2, and this becomes I. What do you fucking mean?
What?
Call that.
Yeah,
That's fucking bullshit.
what is the corresponding eigenvalue? So what this really means? We have ax of a times x is equal to lambda times x. We know a, we know x, so we can just fill this in and have a look at what at like how many times you have to multiply this to get a result. So let's see. First thing goes here, so this becomes 2 minus 4, 1, 2. Second thing goes here, 2i, so this becomes -4i plus 4. This becomes 2i plus 2. Okay, and then we divide this by the top thing. So basically what I'm thinking is -2i plus 2. And what happens if you do -2i plus, or actually it's, is that correct what I just wrote? 2i plus 2 negative 4i plus 4. Yeah, but if you multiply the bottom this thing by I, you will get. Oh yeah. Okay. So this will become negative 2i or 2i plus 2i, which will become 2i minus 2.
Why do you always put your eyes first instead of last? I hate this.
Valid. So this is negative 2i plus 2. Let me see if that's still correct. Yeah.
But I've got a beautiful, like, later on in this one, they ask to calculate the scaling factor and the angle of rotation of a vector, or of a special form matrix, and I've got a very nice way of doing that. So
All right. This is Yella telling us stuff we don't need to know yet. Take off on your bingo cards, guys.
hell yeah!
Oh yeah.
I'm just saying that once you reach that, can I say how I do it? Because maybe it will help people.
You can try. Sure.
Cool.
The eigenvalue to this matrix. I mean, this is just quite easy. Just like 1.5 minus L, 1.5 minus L. Actually, so they use this theory. This one over here. And P here is just the identity matrix. So the eigenvalue is A minus BI, and also A plus BI. Where's A? Yeah, A is on the top. So it is this and this. That works too. Alright, interesting. Oh yeah, okay, well this is easy. Matrix M of complex eigenvalues. Those two. This vector is an eigenvector corresponding to the eigenvalue of thing 1. I was thinking this could be like the complement, and then we just swap them around, but none of the answers make sense that way.
Yeah, this is always a shitty question.
Yeah.
How would you even go about solving this?
It is so because the eigenvalue lambda 2 is the fucking complex complement. You just take the complement of this matrix or this vector. So put all the i's, turn them negative, and after that, you know that the value will be a multiple, complex or not, of the previous one. So if you take the conjugate of this vector, the correct vector will be a multiple, complex or not, of the previous of this vector.
I see. Again, it makes sense.
Yeah, it sucks to calculate though. Good
Yeah,
luck.
it really does. Then we have 11.0 20i, or well, this is really, these are just numbers, not 20i, and then this becomes 14.5 minus 3.5i. I'm going to assume the multiple consists out of at least like 2, because all the numbers are even, so I'm going to scale everything up by 2. 22, this becomes 40, this becomes this becomes 7, this becomes 29, Um, God, how the fuck do they calculate this?
Can you just divide to the possible answers?
Yeah, that's true.
Yeah, see if you get a decent number.
Yeah. So I'm gonna start with the top one. That becomes 11 plus 20i divided by. Let's see, which one will we take? I'm gonna take this one because wait. Yeah, I'm gonna take this one and see because this one gets used twice, and if this makes sense, then we'll see. Negative 9 plus 31i. What we can do here, we can multiply top and bottom by the complex conjugate of the bottom. Which becomes negative 9. I'm gonna get this out of this fucking cell, man. A little bit of a divisor line going on there, guys. No worries, no worries. So let's see, we've got 9 minus 31i. And we multiply this thing as well by minus 9 minus 31i. This just becomes, because we have something of the form a squared plus, or a plus b, a minus b, this becomes a squared minus b squared. So this becomes 81 minus 31 I squared. I squared becomes, it turns this into a plus. So this becomes, actually, it's 31i squared. So that means it's actually 31 squared. Wow, okay. And do we get a calculator? Yeah, right?
Yep.
Okay, so this is like
Wait, we do?
30 plus, or like 900 plus 60 plus 1. So this is 961 plus 81. Are any of these going to be proper answers to this? I probably made a mistake somewhere. So this is all scarcely divided by 1042. Is that right? Yeah. A 1042? You know what? So we're multiplying by. Then what's going to come out of this is a complex number. There we go. Easy, guys.
Hmm?
I guess.
Chad.
Chad. How is this equal to that? How is the scaling factor? Okay. So it should be a multiple of this thing, which makes sense. And then I guess you just divide all of them indeed by divide this thing by all of them and see like if top divided by top is the same as bottom divided by bottom,
Yep.
then you've got the answer. However, somewhere in my calculations I went wrong because my answer was divided by 1042. I have thorough belief that when you divide by 1042, I don't think you can get something good up here again. So yeah, that was just my bad. What are the eigenvalues of this matrix? It's A minus B. So it's, and of course the complex conjugate. So it is this one. Matrix special form, the associated matrix transformation, x becomes ax, the composition of a rotation and scaling. Let's see. So let me actually grab the slides here. Oh, well, actually, this I think this makes sense. So what this does is when you have the complex number belonging to a minus bi, so that is negative 2 square root of 2. It's minus b. This becomes plus 2 square root of 2. Let me grab that out of here. So this is equal to a complex number.
No. It's equal to 0.
No.
Oh wait.
Yes. Nice.
Yes. Well, I mean, 0 is also a complex number. It's just that the real and the imaginary part are both 0. You fool! Okay. So this is actually equal to this thing times -1 plus I. Well, actually, there's probably a better way to do this. So we want this in the form r times cosine of theta plus I sine theta.
I'm gonna be fairly honest with you, Chief. It's square root of a squared plus b squared.
Yeah,
I'm
yeah,
gonna
I
be
know.
fairly honest with you,
And
Chief.
we can also calculate the so we have a number now. We want to get back to this form. So then we have some formulas which we can use for this, right? So we know the r is equal to the square root of a squared plus b squared, which is equal to the square root of 2 square root of 2 squared, which becomes 4 times 2 is 8. And then the same for the other one, plus 8, which is equal to 4. So then we have 4 times cosine of theta plus I sine of theta. Funnily enough, we also have theta being the so if theta is the arctan of b over a, which is right hand divided by left hand, which is -1. So then we have the 4 times the cosine of, well, actually first let me enter 4 here because that's a scaling factor. The cosine of the arctangent of -1 plus I sine the arctangent of -1. And the angle of rotation is what's in here, so that's the arc. However, we do have to be careful that we get the argument right.
Yeah, and for this I have a trick.
Fuck it, we're less than an hour in. I can do with some tricks.
Sure. So if you want to know that, like, if you have two values and you want to know which one is the right one, because arctangent of x equals -1, I believe gives two values. That will be minus a half pi and positive a half pi, or positive 3/4 pi. Because you want your angle of rotation between pi and or minus pi and pi. I know actual arctangents only give one, but the actual angle can be one of those two.
Yeah, because you like add or subtract pi.
Yeah. So if you want to know where it goes, so what's the matrix again?
-2 square root of 2, -2 square root of 2, 2 square root of 2,
Okay,
-2 square root of 2.
So it's this and then something something as the matrix.
Yeah.
So you take because this is a rotation and a scalar.
Yeah.
You take the the matrix this, which when drawn on a plane is just straight up. I think it doesn't matter, but I think I'll just take this, like, so.
Yeah.
This thing is a vector going straight right.
Yeah.
If I put that in, I get -2 square root of 2, 2 square root of 2, which will turn to minus square root of 2 and then up.
Yeah.
So this turns the vector going straight right to top left. And we knew that the answer would either be 3/4 pi or minus a half pi. So the answer will here
Or
be
you mean minus a 4th pi, right?
minus a fourth. Yes, sorry, you're right.
Yeah.
So
Okay.
the answer will be 3/4 pi because this thing gets translated here and not down here.
Yeah. That makes sense. We also, however, know that the matrix transformation that we have to work with is equal to -2 something plus 2 something I. So we know that would be up here as well.
Yeah.
So there are two different ways. However, for like this matrix is in the neat little special form. If we get one that isn't in the neat little special form, your thing will work better.
Well, no, because if it isn't in a neat little special form, it won't be a rotation transformation matrix. It will be a skew matrix.
Oh, okay. Cool.
So like then it isn't a rotation or a transformation at all,
Yeah.
if I recall correctly.
Let me see. Okay, so the range of the arctangent of x is equal to this part. Namely, let me see. According to this Google thing, it's negative pi over 2 to pi over 2. So to get from something in this to over here, we can add pi. Yes. Okay, so that means I can go in Graphql and I can say arctan of -1 plus pi. Okay, what are the eigenvalues of this matrix? So we know it is this thing plus this thing and this thing minus this thing, doesn't matter in which order. So it is 3 squared of t to this one. Give the scaling factor. Well, the scaling factor we know that is the square root of, let me actually get rid of this. We know the scaling factor is equal to the square root of a squared plus b squared. So that means the square root of 3 squared of 3 over 2 squared, which becomes 9 times 3 is 27 divided by 4, plus, and this becomes,
9/4.
yep, 9 over 4, which will add up together to be, let's see, what's this, 36? Or, yeah, 36 over 4. Yeah, which is equal to 6 over 2. So that is equal to 3. I love how you have like such a big well, not complicated, but like, you know, thing with fractions and stuff, and it just simplified, and you answer the number 3. Okay. So again, our complex number is poles minus the thing in the top right, so that's also poles, which is just the output of the arctangent. So we can say the arctan of minus b, so that is 3 over 2, divided by 3 square root of 3 over 2. There's no way in hell Graphql will do that right on your first time. So be really careful with what you enter here and where the biggest stripe is. For me, the biggest stripe is in the middle, so it's the top fraction over the bottom fraction, but if you mess that up, it can get a different thing. That's what I said, pi over 6. Okay, find an invertible matrix P and the matrix C of the form blah blah blah, such that the matrix has the form blah blah blah, give the matrix as P and C or in that order. Okay. The matrix P can be constructed as... Okay, that makes sense. So what I'm going to do first is I'm going to calculate the eigenvalues of this thing. So we're going to have -1, 15, -3, 7, or -7, and it's going to become -L for minus lambda. This will be -1 minus L times -7 minus L. And this is going to be plus 45 is equal to 0. Then we get 7 plus 8L plus L squared plus 45 is equal to 0. L squared plus 8L plus 45 plus 7, that's like 52 is equal to 0. What are factors of 52 again? It's like 26 times 2, which is 13 times 2 times 2. Is there a neat way to go about this? Obviously there isn't. We're working with complex fucking values. Why would there be a neat way? -8 plus or minus the square root of 64 minus 4 times 52 all over 2a. So I'm going to factor a 2 from here, 4, and I'm going to factor a 2 from here, which is going to become a 4 in the square root. So this is going to become, it's going to go away, this is going to become 16. This minus 16, that's equal to 30 32 or negative 30. Oh no, actually negative 36.
No, 36.
Yeah.
Yep.
So negative 36. This becomes plus or minus 6i. So the eigenvalues are minus 4 plus 6i and minus 4 minus 6i. Now that we have the eigenvalues, we can calculate the eigenvectors. Or actually, I think we only need one eigenvector. What's the case with that? Yeah, okay, so we just need the eigenvalue a minus by bi. So we're going to take this one with a equals -4 and b equals to 6. So the matrix C is going to be -4, -6, 6, -4. And the matrix P, for that we first have to calculate the eigenvectors, or an eigenvector of this matrix. So then we have -1 minus -4 minus 6i. This will become plus. This will become plus. This will become 3 plus 6i. This will become just 15. This will become -3, and it's going to become -7 minus -6 -4 minus 6i. Sorry. So then this is gonna become -3. Okay. I will now proceed to take the complex conjugate of this thing. -3 or 3 minus 6i. And also do the same on the top here. This becomes 9 minus or plus 36. That's gonna become 54 or 45. Sorry, I keep mispronouncing these numbers. Divide this whole row by 15. It's going to become 3. And it's going to become this. Add top row to the bottom row. This is going to fade away. It's going to fade away. So then I can say, I'm going to get rid of this stuff. So we have x1 is equal, or actually I'm going to divide this thing by 3 as well. So we have x1 is equal to -1 minus 2i, x2, and x2 is equal to x2. So now we can take a vector that satisfies this, which is going to be the vector let's see, it's going to be the vector, yeah, so it's -1 plus 2i over 1. Yeah, this makes sense. So then the left part is the real part of this vector, which will become -1, 1. And the right part is the imaginary part of this vector, which is 2, 0. Let's go! Oh, that feels good. Wow, okay, nice. That's a bunch of computations, now it's right. Okay. Finally, let us look at the interpretation. So, the matrix P corresponds to a change of a variable from x to u. Matrix C corresponds to the linear transformation in this u plane. However, the particular structure of C allows us to interpret it as a rotation combined with a scaling. So now try to write C is equal to SR, in which S is a scaling matrix and R is a rotation matrix. Okay, this is also interesting. So we still have this thing. So this is what we're actually applying to it, right? Therefore, let's see. I'm first going to write this in the form r times cosine of theta plus I sine of theta. I know that r is equal to the square root of 4 squared plus 6 squared is equal to square root of 16 plus 36 is equal to square root of 52, which is equal to, can I get anything out of that? 2 times the square root of 13. Is that correct? Yeah, that's correct. And then we have the tangent of, or the angle t is equal to the arctangent of minus, well, it's actually b over a, so that's going to be 6 divided by minus 4. Okay. So this is gonna, this minus gonna carry away. This is gonna become 3 over 2. Yeah, so it's the arctan of minus 3 over 2. Okay. So I know how to do a rotation matrix, but I don't know how to do a scaling matrix. So I'm first gonna do the rotation matrix. I'm gonna say this is sine of arctan of minus 3 over 2. This is the minus cosine of the arctan of 3 over 2, or minus 3 over 2. This is the cosine of the arctan of minus 3 over 2. And this is again the sine of the arctan of minus 3 over 2. I think this part is correct. Did I get the rotation matrix right? Like sine minus
I think
cosine.
you
Cosine?
gotta switch sine and cosines around.
That could very well be. Let me Google real quick. Rotation matrix. Two-dimensional. Oh, it's cosine minus sine, sine, cosine. Yep, you're right.
Yep.
So it's cosine. I was close though. Minus sine, sine, cosine. Okay, how do we do a scaling matrix again? If I want to scale by a factor of 2. I know it's probably something along the lines of, so we have 2 square root of 13, so it's probably something along the lines of 2 square root of 13, 0, 0, 2 square root, square root of 13. I'm not sure if my value that I entered is correct though. As in like, is the factor that we scale with the thing we enter there?
I think so.
Then this should be correct, I think. I do want to check real quick if this arctangent is correct. So, we have negative 4 minus 6i. So that is negative negative over here. We start here. So I might as well add pi just for good measure. Because we want to get to there. Also, I think I might have fucked up. So, why do I say b is 6 here? Is that for a reason, or did I just make a mistake and should that be minus 6? I think that should be minus 6 then. Alright, let's redo some of the calculations, but not all of them. So because we square the number here, it doesn't matter here. And all it does here is it means the arctangent becomes positive. Which actually does have an effect because arctangent is repeating, is a, what's the name again? It's not,
Symmetric.
it's an odd function, so the minus sign carries out. Yeah, that's the word we're looking for. So, and then I
You want to keep the minus sign before the sign is, so.
Oh, yeah, fuck, I deleted one sign too many. And then I also add pi to all of them. This is a piece of art, this matrix. Oh, where's the closing bracket? Oh. Why? Oh, yeah, because it's a minus sign. Okay. Let's see if it works. Suspense is killing me. Oh, yeah! Let's go, boys!
Nice.
Wow, okay. We're almost halfway through the first one. Only 10 to go, guys. We're only an hour in. Right, this is like the exact same thing. We just did this, didn't we?
Yes.
Skip all.
Speedrun, let's go.
It's called symmetric if it satisfies that the A transposes itself, which makes sense. We will prove a real symmetric matrix A only has real eigenvalues. Didn't we only do symmetric things like way later? Okay, cool. Start a proof. Woo! We may use the fact that there exists a non-zero vector. Well, it's a fact that there exists a non-zero vector. But this one isn't true either. I know eigenvalues cannot be equal to 0 so we can use that. Okay, then it's the top one.
Eigenvalues can be equal to 0, can't they?
Can eigenvalue be equal to 0?
Eigenvectors and eigenspaces can't be.
Oh, that makes sense, yeah, because then it would be the trivial solution, right?
Yes.
But the eigenvalue itself can. Okay, my bad, that was dumb.
And if I recall correctly, if an eigenvalue can be equal to 0, the matrix is non-invertible.
Yeah, correct.
Yeah. Because there's no pivot in every row.
Yeah. Because the determinant is equal to, at least in a square matrix, the determinant is equal to the product of all the eigenvalues, and if one of them is 0, then the determinant is 0, and therefore it's non-invertible. Okay. Matrix A equals matrix, blah blah blah. We assume A is a real symmetric MBA matrix, and an eigenvalue of A, or a lambda is an eigenvalue of A. I just call it lambda n. Let x be an eigenvector corresponding to lambda. We do not know whether x is a real eigenvector, but conveniently, the expression of the inverse of x transpose times x will definitely be real. In fact, this expression is equal to. Okay, so imagine we have the vector. Okay, what does this do? We have the vector a, b. What this does, or let's say a minus bi, or a plus bi and c plus di. So if we take the transpose of this and then the inverse of that, that means we get a minus bi, c minus di, multiplied by the vector of x, that is just a plus bi, c plus di. So then this becomes wait, does this product multiplying a vector by a vector, what does that give? Just a number, right? Or just a vector, right? Oh, actually, you should look at this like matrix multiplication. So this is a. Oh yeah, okay. So this is c minus di times c plus di plus a minus bi times a plus bi. So this is just a singular number. And what stands here is equal to this, which is equal to c squared plus d squared plus a squared plus b squared. So that is So because the absolute value of this, or the absolute value of x, would be equal to the square root of this thing, that means this thing is equal to this the absolute value of x squared. There we go. All right. Whew, brain's working hard today. Jesus. Symmetric, blah blah blah. Find more about our eigenvalue lambda. We study the expression. Okay. X of t times a times x. This expression is equal to. So what do we know about this matrix, right? So we know that a times x is equal to lambda times x. Let's say Lx. Therefore, this is equal to x, like underlined, and to the power of t times lambda x. Is that one of the answers? And see, since this is just matrix multiplication, we can swap this around. And since we've already calculated that this is equal to the absolute value of x squared, that means we get absolute value of x squared times lambda. This is a really interesting exercise, actually. I like these exercises. To prove that lambda must be real, we must first show that the expression xta x, the complement of x transpose times the matrix A times x is real. We do this by computing its complex conjugate. Well, we know the conjugate of one thing, or of one like big composite thing, is equal to the conjugate of the insides. Well, the conjugate of the conjugate becomes this thing itself. I don't understand this step. Why can't they just remove the conjugate from A?
Because A is symmetric. Oh no, is A real?
Yeah.
A is a real matrix.
Oh
so
yeah. Okay. So the conjugate is
real.
itself.
Yeah.
Then, they take the transpose. Oh well. Why is this equal to its transpose?
I think, and I could very well be wrong here. So if you transpose, and I'm just spouting out of my ass, so I'm definitely wrong here. But I would say if you transpose, you turn around the order of the things in there, so you get.
Oh wait, that's
X
true. Yeah.
transpose,
So ABC transpose is equal to A transposed, or C transposed, B transposed.
I'm not sure if this is the case,
A
but this would make sense if it.
Yeah. Yes, exactly. This is it.
Yeah. Okay. Well,
cool.
then that makes sense because then this
I
thing.
completely didn't know that.
Yeah, me too. Then this thing transposed will get at the start. This thing transposed will get to the end, and A transposed. Well, it's a symmetric matrix.
And I think the same happens when you invert something. It also changes the order of things.
Yeah, that's true. I know that much, but I didn't know about transpose.
Didn't know that either. I'm fucking behind.
And we know A transpose here as well is the this thing. Oh, Pog. So give the arguments for the first equal signs. For the first equality sign. So this is just because we're talking about like vector matrix vector. Then this is true. Yep. Second equality sign. So that's this one. Well, we know that the double transpose is equal to itself, right? So yep. I love how we already did this, but we just didn't know it was a question. We were just trying to get through this theory. Prove that it must be real. Yep. Third equality sign. So 1, 2, 3. That's this one. Well, that's just A is symmetric, so actually, A is real. Yep. Then we can take the argument of the fourth sign, that's this one. That is...
The fact that's they have the wrong answer for this.
Hmm?
They have the wrong answer for this. The answer. What do you think the answer is?
Wait, actually, this is just a number, right? Because it's lambda that we're trying to prove. So the transposition of a 1-by-1 matrix does not change the matrix.
Okay.
Like, we know that this is equal to lambda, a number.
Yeah, because the size, it's lambda times the size of x, and the size of x is also.
No, like we literally like, if we go up here.
Yeah, but x transposed a. Yeah, that's lambda times the size of x.
Yeah, but the size of x is also a number, right?
Yeah, that's what I said. Yeah.
So this is just a number, and the transpose of a number is a number.
Yeah.
Okay, 50 quality sign. Well, that's what we were discussing. So this, and then the last one. Oh, and the final equal signs. Well, that's because it's a symmetric matrix. What conclusion can we draw about the expression using the identity we just proved? Well, if its complex conjugate is equal to itself, then it is a real number. Now to wrap up the proof. Yep, that makes sense. Because the only vector with length 0 is the 0 vector. It was a really good exercise. I like this exercise. Every real 5x5 matrix has at least one real eigenvalue. Every real 5x5 matrix.
Remember, they come in pairs.
Oh yeah, that's true. Well, yeah, okay, yeah, that makes sense. That's true because there's 5 eigenvalues. They have like, even if there could be complex eigenvalues, that would be like one real, one imaginary, one real, one imaginary, and one real. Because if you had another imaginary one, then it would also have a real pair, which doesn't work.
Exactly.
Yeah, and because it is I think the better thing they say is more explanatory. A degree 5 polynomial always have at least 1 0.
Yeah, makes sense. Following statement.
Or 1 real 0 at least.
Yeah. Because it will always be something in like this, right? And it will either be like or whatever, but it will go infinitely to the top and infinitely to the bottom. So it will cross 0 somewhere. The eigenvalue vector of a real matrix A corresponding to a complex eigenvalue can have all real entries. The eigenvalue of a real matrix A corresponding to a complex eigenvalue can have all real entries. Huh. I mean, I don't see why not. So if we have a real...
No, I just did this one and I got it wrong. But it makes sense. Yeah, you got it wrong as well. Because the entire matrix is real. And the eigenvalue is complex. So like...
we will eventually get something in the form... like a number, A plus bi.
But like, think of the shape ax equals lambda x, yes?
Yeah.
So a is real.
Yeah.
And you say that if so x is a vector, yes. So you say a is real and x is real, and I or lambda is complex. So then you get real equals complex, and that can't be possible.
That's true. Yep, makes sense. Back to lessons. Okay, we're 1.5 hours in. And we have done a single lecture. Bolg.
I
So we need...
recommend not doing pre-lecture.
No. Well, I mean... I don't know. We could. How many things are there actually? Because there are less now, because we only have to do like... Do
There's
we have to
20
do
in total.
14, 15, 16, 17, 18, 19, 20.
That's
So we have
6.
7 to go.
Oh, 7, shit. Yeah, my math is wrong, yeah, 7.
CSE level can't do a simple aftreksom.
And also we can probably skip 17 because 17 just reasoning.
Yeah, true.
Well, reasoning is important.
Yeah, okay, but we skipped 7 as well, which is also reasoning.
Okay, sure.
Yeah, we made a mistake before, so we're gonna do it again.
So what do you call, what do you call it again? The
Scuffed?
fucking... No. The fucking... Sunk cost fallacy.
Yep, exactly. Oh wait, did this motherfucker get an SSG duo DNT thing? Cool.
Yep.
Okay, practice. Let's look up the slides real quick before we start. Oh, I was like, where's the slides? But it's the wrong thing. I wonder what we're gonna discuss tomorrow. Like, if there's gonna be a new topic or not.
No, it's just...
No, it's just gonna be a review. Mark
Yeah,
should
not
lost
for
time or
LA.
something.
Wait, it is? Bog! Then after this we will be done with LA after the test? Or, well, we always will be done, but like...
Well,
Hopefully.
some of us will be.
Yeah, okay, that's true.
The other 50% of us will be doing the resets.
I love how you say some of us instead of most of us.
Well, I mean, the percentage is decreasing for last year. Like you have the most for calculus, then you have less for LA, then you have the least for like proper stats.
I think I actually
think.
posted the stats in my channel once. So let me have
Yeah,
a
a
look.
while ago.
So for LA, 71% passed. For IDM and OOPP, it was like 95 or more. Or actually, it's 94.5 for or 94.4 for IDM and 98.7 for OOPP.
It's. I mean, to be honest, you need to take some effort to fail OOPP like.
Yeah, just you need to actually go out of your way to not show up twice. About that.
And then like doesn't do any work at all.
Yeah, true. Let's see. So we have discrete dynamical systems. I watched a video about this a while ago. Yeah, okay, so we have like, let me get rid of all of this. If we have like, VK is equal to A times VK minus 1, that is?
Script.
Yeah, okay. Alright, yeah, actually let's do it the proper way, so we have this. Yeah. In that case, we would have Vk plus 2 is equal to A times Vk plus 1, which is equal to A times Vk. Therefore, it's A to the power of K times V0. Does that make sense? Well, I mean, I probably should have proven it for the base case as well, because you can't just do inductive shit like that, but... Yeah, this makes sense for me in my head. So, this is the correct answer. A discrete dynamical system. Yeah, for all real values k. Real positive values k. State vectors. Then we have the initial state vector, okay. This does not look like fun.
We all agree.
Hmm?
We all agree.
Yeah. Okay, so we have this thing, which is like the kth vector is equal to a constant times the eigenvalue 1 to the power k times the eigenvector belonging to that eigenvalue for all eigenvectors. Or actually, not for all eigenvalues, because that will be like infinitely to the power of 6 many, or to the power of however dimension your thing is, but for all eigenvalues. Okay. Oh god, this shit again. Ugh.
The only trajectory here is towards dying.
I love how negative everybody is. Well, everybody, mostly this one guy. But yeah.
Just me, you know me.
Yep. Okay, so this is about the eigenvalues and which yeah, so this is about the eigenvalues, and if they are all less than 1, then they will all go towards 0. If they're all less bigger than 1, then they will all blow away exponentially. And if one of them is bigger than 0, one of them less than 0, then it will saddle point. Yeah, that makes sense. And it also makes sense if you look at like this thing, because it will be like x of k is equal to a constant times a number bigger than 1 times another constant, or like in this case a constant vector.
Can you scroll up a bit to the previous slide?
And since n is bigger than 1, it's just gonna get bigger and bigger as you raise this thing to the power k. Okay. Everybody just thinks they've had enough. Here you can see, because yeah, that makes sense. So we have a saddle point. This one is bigger than 1 and this one is smaller than 1. And we don't care about the C1 and C2 for now. Unfortunately, we will have to care about it later. Which general solution is sketched here. So it repels in both directions, so that means both of them are positive. So this one is not, or both of them are like bigger than 0. So this one's not true, this one's not true. And then we can look at which one is the biggest like repeller. And that should be, let's see, so we have, this one is 1, 1, and this one is 2, minus 1.
And once you put down a point, it really starts moving into the direction of 1, 1 before it starts moving into the direction of 2, negative 1.
Mm-hmm.
Like, you can see that things really want to go in the direction of 1, 1 and less so in the direction of 2, negative 1.
Yeah. For example, if we look at this trajectory, it will go way more this way and way less this way. So
Yeah,
you can see that this one has the highest attraction, therefore it is the one with the biggest coefficient. In another case, these are both repellers, or yeah, both repellers. Or actually, no, never mind. My bad. This is a saddle point. Yeah. So they all just go like whoop, whoop, or whoop, whoop. So let me see. The first point, again, they're using the same value. So this one is the 1, 1, and this one is the 2, negative 1. And we can see it's trying to get away from that 2, negative 1 and closer towards 0. But then the closer towards 0 it gets, the more it like gets repelled by the by this point, by like this one. So you can see it kind of like this is a repeller or an attractor which gets it to 0, 0, and this one is a repeller which gets it to like this line. So you can see it's going like whoop. I really hope you guys can see my mouse, because otherwise it doesn't make any sense.
We can.
Oh, good. Okay. And again, this is just all starting to bounce in towards 0, 0. So this is a thing where we have 2 attractors. And then you can see one of them is a bigger attractor, which is this one. And you can see it's just going way harder towards this thing than towards this thing, or this direction. Yeah. So this one has like a bigger, what's it called? Yeah, a bigger attraction, let's just say it like that. Let's see, what else do we have? Behavior, okay, so this is a rotation of... Yeah, this makes sense, because if you apply rotation of k or of theta degrees twice, you get 2 theta. And if you apply it k times, you get it k theta. I think they forgot a k here, but whatever. This makes sense as well, because you, if you take this whole thing to the power k, you do this thing to the power k, which we just discussed would become this, and a scalar to the power k is just scalar to the power k. So I think no surprises so far. Scale rotation, well, we know the scale would be this thing, and yeah, just raising a matrix like this to the power k. We already had raising diagonal matrices to the power k when we had diagonalization, so we knew this as well. And if not, it is trivial to prove. This proof is less than an exercise to the reader. Yes. Okay, I guess this makes sense because this is like already in form A minus BB. So this is just literally only rotation. And this is still multiplied by some other thing, which is also a like a skewing. Okay, cool. Yeah, and if we have an diagonal no, not diagonalizable, like let's say a matrix in the form of this with 2 by 2. Oh yeah, we talked about this earlier. Then this will go towards yeah, this will go towards either towards or away from the origin. Yeah. Yeah, and that depends on the how do you say that? That depends on the length of a plus bi. So the r here in the a plus bi is r cosine theta plus or minus I sine theta thing. Yeah, and this is what we said just now as well. If it is less than 1, then it spirals towards 0. If it's 1, then it's the other round. If it's bigger than 1, it spirals away from 0. Okay. We studied the population dynamics of a group of mice by counting them once every year. YK is the number of young mice. AK is the number of adult mice. 45% of them live to adulthood, while the others die. While the others will die. Young mice are too young to reproduce, but not all of them. The number of offspring per young mouse per year is 0.15. Okay, yeah. So what this thing is doing is it's asking us to express yk plus 1 as a linear combination of yk. So this is the number of young mice. How do I do that without providing 2 different formulas? Whatever. while the others will die. Okay, so this number is irrelevant because this is only about the number of ones to make it to adulthood. So this is, yeah. So the young mouse reproduce at a rate of 0.15, so that's 0.15 YK. And the adult mouse reproduce by 2 of their own things, so 2AK. Yeah, okay, that makes sense. So, what a lesson. Holy shit, guys, I have to calm down from that one. In half an hour, by the way, we will have a break for an hour. Maybe a little less, well, maybe not less, but maybe a little more. Depends if my group actually takes longer than that. But yeah, it's just for OOPP. Okay, so now we can update your knowledge. CSE. The knowledge of the eigenvalues of a discrete dynamical system is sufficient to judge whether the origin is an attractor, or a repeller, or a saddle point, or none of these three. True. Because you need the eigenvalues. If they're both smaller than 1, we have an attractor. If they're both bigger than 1, we have a repeller, and otherwise we have a saddle point. Oh, and then if they're all exactly 1, then they're just rotation. Eigenvalues negative 1 over negative 0.3 and and positive 0.9. That's the eigenvalues. So then the nature of the origin when we consider the discrete dynamical system is, let's see.
Oh, vandaag
They're
gesproken
both.
dus man. Very klaar.
All right. They're both smaller than. They're both smaller than 1, which means it is an. It's an attractor. There we go. Is it possible that a point different from the origin is an attractor? Nope. Because the reason it's an attractor is because when you do a fraction less than 1 to the power of infinity, it will tend to 0. There's no number, so that if you take it to the power of infinity, it will tend toward a number. Yeah, no, okay, that's true. And in this case, you can see that the nature of the origin is a saddle point, because here it is bigger than 1, and here it's smaller than 1. Ooh. I can see that everybody is getting their like rejected, accepted, and stuff, because we're like dropping like flies. I guess they'll be back soon though.
Yeah.
So we have V1 and V2. Huh. I understand that we have 7 over 18 is equal to 10 times V1, which is 10, 10, minus V2, so that has become negative 3 and plus 8. I don't understand how this helps us. Or actually we do have this, that's good. Yeah, I see. So what we have to do now is use this thing. Oh yeah, okay. Now I understand why this helps us as well. So we have x0 is equal to c1 v1. I have my caps on. X0 is equal to c1 v1 plus c2 v2. C1 is equal to 1, C2 is equal to 10, C2 is equal to negative 1. Therefore, we know that x of k is equal to 10 times lambda 1 times 1, comma 1, the vector, plus, or minus in this case, 1 times lambda 2 times the vector 3, comma negative 8.
Lambda to the power of k.
Thank you. It looks a lot worse when you're looking at non-latex, when you're used to looking at latex. Let me get rid of this. So then we have lambda 1 is equal to 1.4, lambda 2 is equal to 0.3. In this case, we are looking for... Oh. In this case, we're looking for x8, which is equal to this to the power 8, equal to this to the power 8. Because they say we don't have to calculate explicitly, that's good. Then we can say 10 times 1.4 to the power 8 times the vector. I'm not sure if we can use the dot product like this, or the time signs like this. We probably can actually, now that I think about it.
Yeah.
Minus just 0.3 times, or to the power 8 times the vector 3, comma negative 8. Let's go. We are so good, guys. Oh fuck.
That was pretty k.
The entries of the solution for x8 are greater than 100 and keep getting further away from 0 when k increases even further. Can you give a non-zero vector x0 for which this is not the case? Give the vector explicitly. Hear me out, guys. Fuck, it says non-zero. Okay, I thought I could get away easily.
Like, how the fuck are we supposed to calculate the eigenvalues and eigenvectors of these small ass matrices?
I mean, that's not that hard, right? Especially for 2x2.
Try and solve me the equation 2.72, or no?
Oh, small s is in fractional.
Yes.
I mean, you can still use the quadratic formula. It's just going to be less pretty.
Yeah, I guess the quadratic formula is the only way. But then, oh yikes.
Mm-hmm.
Then, like, one of my fucking matrices is like 1.82.
Oh, fun.
3.3.
But you're allowed to have a calculator, so it's fine.
Are you?
Yeah, no, like a basic 4 function calculator.
Oh wow, that's news to me. That's actually pretty cool. Then I guess you can just fill it in your calculator and calculate it that way.
Yep, correct.
Okay, that makes it a lot less gruesome.
Yeah. You're allowed to use your winner calculator even.
Yeah.
Wait, really?
Yeah.
Yeah, that's what I did for the midterm.
Yeah,
Pretty sure even in scientific mode.
Alright, let's continue real quick. So, entries are greater than 100 and keep getting further away from 0 when k increases even further. Can you give a non-zero vector for which this is not the case? Yes. Oh, wrong one. So what we have to do then is make sure that both of these coefficients are negative. Because then it will be smaller than 0 and getting further away from 0. So then I would have to make a vector that is composed out of negative this thing and negative that thing. So that would be negative 4 and negative 1 plus 8 is 7. Negative 4, 7. I see, motherfucker. So basically what they're saying is we only want to care about this part. So we can just take something linear to this vector, linearly dependent on this vector, a multiple of this vector, whatever. And then the x0 will be 0 times v1 plus whatever times v2. And since this is less than 0, that means that as the power goes on, it will go further and further towards 0. Hell, I can use 1, and then this will become xk is equal to 0.3 to the power of k times 3 comma negative 8, which will just get smaller towards, get close towards 0 as we go. All right. Now the question: can we speedrun the next thing in 19 minutes? Probably not, but I'm not going to waste that much time, so I'm going to do it. Suppose the eigenvalue matrix are 3, blah 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 blah. Find the solution of the difference equation for specified x0. Explicit eigenvectors and eigenvalues. Ugh. So we have x0 is this thing plus c3v3, which means that x0 is equal to c times, or actually it's the matrix v1, v2, v3 times c, where c is just the matrix c1, c2, c3. We can probably use linear algebra to solve this, so I'm gonna try that. Yeah, so if I just make a matrix out of this stuff, 2, 1, -5, and -3, -3, 7, and make this an augmented matrix to this thing, then reducing this to echelon form should give me on the right side the values for C with the Okay, let's try this. So first of all, I'm going to add 3 times top 1 to the bottom one. This will become 0. This will become 1. This will become -2, and this will become -3. Then I'm going to subtract this one from this one. When you subtract -3, you add 3, so this becomes 1. When you subtract -5, you add 5, this becomes 2. Well, here we have the answer for this one. I'm going to add 3 times this one to this one. This will become 1. I'm going to add 3 times this one to the top one. This will become 0. This will become 4. I'm going to subtract 2 times this one from this one. This will become 2. So the answer is, that was really quick, really easy. 2, 1, 2. Okay. So then I can say x0 is equal to, or xk is equal to, then we have the c1 times the eigenvalue that belongs to it to the power k times the eigenvector that belongs to it, which is 1, 0, -3, plus 1 times 4/5 to the power of k times the vector 2, 1, -5 plus 2 times the vector, or 2 times 3/5 to the power of k times the vector -3, -3, 7. This should be correct. And this also means that the only thing that v0 or x0 changes are these coefficients. Motherfucker takes half an hour to answer. That means that when x of k goes to infinity, that means that... Can I still copy this and paste it over there? Probably. Probably, he says, like a fool. Probably. X of k. First of all, let me type it here. Actually here. So let me see. We have 2 times 3 to the power k times this thing. So 1, 0, 3. But as you see in this thing here, as k grows to infinity, this thing will fall away and this thing will fall away. What did they want me to do? Do they want me to just say to the power infinity? Or do you want me to say to the power k? I think this is what they want. Yeah, I know. Okay, maybe they want like this. Oh. What do you want? Okay.
Yeah, you wrote xk is before it, but it already was above.
Oh. Fuck off. Anyways. Classify the origin as an attractor, repeller, or saddle point for this system with A is equal to blah blah blah. In that case, that just means that we have to calculate the eigenvalues for the system. Fun stuff. So then we have 0.2 minus L minus 0.5 minus 0.6, 0.1 minus L. So then we have 0.2 minus L times 0.1 minus L minus 0.3 is equal to 0. So when we do this away, we get 0. Actually, let me get rid of this stuff. This becomes 0.02 minus 0.3 L plus L squared. And this is gonna, let's see, so we have minus 0.3 plus this stuff, so that's minus 0.28. So this becomes L squared minus this plus this. I think the only way for this to happen is if both of them are smaller than 0. So this is a attractor. All eigenvalues are less than 1 in magnitude. Quod erat demonstrans. Find the direction of greatest direction is given by line through 0, 0, whose direction is defined by a vector AB. That's fun. So I can say 0.3 plus or minus the square root of 0.09 minus 4 times 0.28 divided by 2. And this thing also divided by 2, so this is going to be 0.15. Then I can take this, plop that straight into Google. Wait, no way, that's correct. minus 4 AC, so this should be plus. That makes it a lot more logical already. Because I was getting some imaginary value. I was like, no way. But this is just equal to 1.1. And I should still divide by 2. So this is equal to 0.65. So therefore, the numbers are 0.8 or minus 0.5. Yeah, that seems correct. So the point of greatest attraction is the fraction that's closest to 0, and therefore that's this one. So what I'm going to do is I'm going to enter this eigenvalue, which will turn this into a plus, and this into a plus as well. It's going to 1, 5, and it's going to become 2, 5. Then I can set this to 0 and 0 because we want the 0 space of this. Okay. So what I can do then is I can multiply everything by 100 because fucking hell. Okay, wait. First I'm gonna multiply this by a minus sign. Then I'm gonna multiply everything by 100. So this is gonna become 60. This is gonna become 25. This is gonna become minus 50, and this is gonna become minus 15. Then I can divide everything by 5. So this is gonna become 12. This is gonna become 5. This is gonna become 10. This is gonna become 3. I'm going to multiply this value by 12. This becomes 60. This becomes 120. I'm going to multiply this value by 5. It's going to become 60. Minus 15. I'm going to subtract the top value from the bottom value. It's going to become 0. And this is going to become... So minus 120 is plus 120, which will turn this into 105. 1. This is going to become 1 minus 2. I think I fucked up. Because what we wanted to solve was AX is equal to VX. Or AX equals to LX. I see. So what I'm going to try to do is just take an eigenvector that corresponds to this value. So we have, and it has to be non-zero. Yeah. So if x1 is equal to 2x2, x2 is equal to x2. So it is x2 times the vector 2, 1. Therefore, the vector 2, 1 is a good answer. Smallest eigenvalue and magnitude is minus 2 over 5. What did I solve then? Huh. Where did I go wrong? This was minus 55 because it's 1.1 divided by 2. Fuck! Okay, so this becomes 0.4 and this becomes 0.7. So I should do all of that again, but then instead of for 0.5, I should do 0.4. My answer is fuck you. Hey, that's what I said, right? So what's gonna happen now is, where's my... Okay. Pause this page up, cool. So I'm gonna pause this timer. Can I unpause it with the same key? Yep. So, I'm gonna have lunch. I suggest you guys do the same. And we are going to have a break until an hour past now. So, 2:30, that is. Yeah, okay. My English is not too bad. So break until 2:30. Alright, see you guys then.
Enjoy lunch. Bye bye.
Bye bye.
See you.
Ik ben zelf nog even bezig met die... Nee, ik zit nu met de post-lecture exercises van de volgende. Van de Graham-Schmidt en zo. En het is allemaal heel simpel. Compute distance between x en y.
Alright. Okay, so video's back on.
Epic.
Welcome back, everybody. On the Discord, it's a little lonely so far, but I assume people will join back eventually.
We go chilling.
Yeah, and yeah, we'll see how far we get.
Yeah.
Okay, let A be blah 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 blah. Let the vector. Oh, actually, we're busy. The vector is an eigenvector of A and two eigenvalues.
Can you share your
I'm
screen?
sharing your screen. Yeah, no, I was about to say I'm not sharing my screen. This might be useful. Okay, the vector is an eigenvector of A and two eigenvalues are blah and blah. Construct the solution of the dynamical system that satisfies this. Let's see, do we have any easy collapse? Nope, there's no like.
What you really gotta do is put in the eigenvalues and get the eigenvectors from there.
Yeah,
Fun,
that
fun,
that
fun,
too,
fun,
but
fun.
you see, are these the three of them?
Those two and the vector there.
Ah, okay, so that's good at least.
Yeah.
So then I can say 0.4 minus 0.5, that becomes negative 0.1, 0, 0.2, 0, 0.3, now minus 0.5 becomes 0.3, 0.3, 0, and 0.3, 0.2, 0.5, 0. I'm going to divide this row by 3, so this is going to come 0.1, 0.1, 0.1, 0. I'm going to add this row to this row, this is going to become 0, this is going to become 0.3. I'm going to add 3 times this row to this row, this is going to become 0, and this is going to become 1.1. And I'm going to add, subtract 2 times this row from this row, this is going to become 0, and this is going to become 0.5. What does this become? 1.
Moving some things above it become 0.
Yep.
Which means that it's 1, 1, 1. Used. Then why is this an eigenvalue? Because this doesn't seem like an eigenvalue to me. Or I guess... No.
No, wait, did I take the null space? Should I have done that?
I mean, to create the eigenvalue, yeah, you calculate how this is 0, and this is only 0 if, you know, you've got the null, or if you input the 0 vector. So somewhere
I think I fucked up.
Well. Yeah.
Oh yeah, I just fucked up. No, it's very not.
Very not levensmooi. Fucked up.
Yeah, so this is, and then I subtract 0.5 from here. I forgot to subtract 0.5. That makes it a lot more logical.
Not a lot cleaner, but a lot more logical.
Yeah, you wanna make it cleaner? I'll multiply everything by 10.
Yeah, that's probably gonna make it a lot cleaner.
There we go. Adding. I can't make it pretty without fucking it up. I'm gonna add 3 times this row to this row. This becomes 0, and this becomes 6. And these two are multiple of each other. So this becomes 0 and 0. This one I'm gonna multiply minus 1. And here I'm gonna say is equal to, and this is gonna come negative. This is not gonna become negative. So then we have x1 is equal to x2 x3. x2 is equal to minus 3x3, and x3 is equal to x3. So we have the vector 2 minus 3 1. So that's the eigenvalue for the eigenvector for eigenvalue 0.5. Let's see what else we have. So we have 0.2, so that's going to become 0.20, 0.20. Fun stuff. 0.3, 0.6, 0.30. Fun stuff. 0.3, 0.2, 0.30. I'm gonna subtract this one from that one. This will become 0. This is gonna become 1. And this is gonna become 0. And I'm gonna make this into 101. And I'm gonna, this is gonna become 0. And this is gonna become 0. And this is gonna become 0. Skipped a lot of steps, but you know,
That's fine.
it's where the fun stuff happens. So we have x1 is equal to negative x3, x2 doesn't, and x3 is equal to x3. So then we have for eigenvalue 0.2, we have minus 1, 0, 1.
Yeah. Yeah,
Okay,
one
construct
left.
the solution of the.
We still want the eigenvalue for the eigenvector 0.1, 0.6, 0.3.
Do
Technically, unless because you want to know what happens as xk approaches
Oh yeah, that's
infinity,
true. So then we need the eigenvalue.
Yeah. Welcome to this very small party, Ruben. We are
Ruben! Hey, Ruben. Okay, so
apparently the party of 10 turned into a party of less than 10.
So we have 0. So what we know is we have. Oh well, that's really easy actually. So we know that A times V1 is equal to L times V1, with L as being a real number. Hey, Kalle!
Hello.
Thank you for saving us from being lonely. As well with Ruben.
Well, I won't be here for too long, but
That's okay.
we're meeting with our LV project group.
Yeah,
Cool.
I just had our
Hello.
meeting.
Oh, nice.
It went really fucking well.
Nice. Did the TA like the video?
The TA didn't watch the video. He's gonna watch it when the like during the Q&A. We basically asked us some questions about the course, and we had a little emotional moment because he was such a fucking good TA and we had such an amazing group, and he was like, "Yeah, I don't see teamwork like your group and like many other groups at all."
We had one of the points of the agenda being, how is Ruben's day? Okay, so for the points of the day, we have asking Ruben how his day was, asking if there is a coverage requirement, and asking Ruben if we were a good group. So, point
By
one
the
of the
way,
agenda.
it's a coverage requirement.
I don't think so.
Okay, because RTA is a complete dick, and I hope this is being recorded.
Oh, it is.
Oh, okay,
Hey,
well,
Theo, if you hear this, Call of TA was a dick.
yeah, I guess
fire
it's
him.
on YouTube now. Thanks.
Fire him. Actually,
He's actually in this Discord, so please don't.
don't fire him.
Okay, then let's see. I mean,
No, but
realistically,
he's been very unclear about a lot of things. Let's
Okay.
put it like that.
fair.
Yeah,
Yella,
understand.
I have done this. Right?
Why is 0.4 times? Oh, wait, that's scuffed. Never mind. Continue. What do you want to ask?
And you see, because this is 0.1, and we know it's an eigenvalue. I know this exists for the eigenvalue 1.
Yes, it is. It is an eigenvalue 1. How did you know that?
Why do we have to deal with these matrices?
Yeah, it sucks. How do
Good
you know
question.
that? Because 0.4 plus 0.5 plus 0.8 is 1.7? Or
No,
is it
no, none of it. Like all of this 0.1. We know what we want to know. How many times this matrix is equal to this matrix?
Fair.
Or-
Another way you can do it is because you know the other two things, and you know that the trace is equal to, like, what wasn't it? How the fuck did that go again?
The trace
What
is
is it?
equal to the eigenvalues plus each other.
Yeah, that makes sense. So like, the trace is 1.7. You've got 0.7, so the last one is 1.
How the fuck do you know the trace is 1.7?
Because 0.4 plus 0.8 plus 0.5 is 1.7. It's not
Oh,
difficult.
the trace is the diagonal sum.
Yes.
Oh, I didn't know that. Cool.
I learned something new.
Well, I'm just gonna check because I just want to check I'm not being retarded.
Oh no, you probably aren't. I've just not been paying attention.
Me
No.
neither.
I don't think
Absolutely
they never mentioned this, but like Tim
Well, no,
said,
they did. Yeah, they did, but it was in the first 15 minutes of the thing when we were having breakfast.
oh yeah, we usually come in 15 minutes late, and when we're having breakfast.
I
Yes.
could come in 20 minutes late and I would still be more on time than our fucking lecture.
That is pretty funny.
Like, that guy decides to just... Yeah, I'm just gonna, like, recap the last lecture for the first 30 minutes and I run out of time for this one.
Wow, what a surprise.
Every time!
And want to know how you fucking
Well, this is easy.
deconstruct it into the
Yeah, well, that's fucking easy.
Yeah.
So we have this thing. We have this
Yeah,
thing.
I recommend scaling it up to let's see, what is it? I think 1/3. Fuck.
And
It
then
is-
this is 0, 0.3, and 0.7. And I'm gonna multiply everything by 10.
Yeah, that works as well. I would recommend scaling up the last row to 1/3 to 1, but this works as well.
No, this works.
Yeah, sure.
Okay.
Go ahead, Mr. Joster.
All right. Let's have a looky look. So I'm going to add this row to this row. 0, 30. This is going to become 4, and this is going to become 7 still. I'm going to add this row to this row. This is going to become 0. This is going to become 10. This is going to become 10. I can subtract this. I can subtract this. I'm going to subtract 1 times this row from the top row. I'm going to subtract 4 times this row from the bottom row. I'm going to divide.
Wait. Can you go back a bit? Because, yeah, it's fucking 7 minus 4 is not 4.
Thank you very much. Oh. And then this is going to become 1. This is going to become 10. I'm going to add, subtract 2 times this one from the top one. This is going to become 0. This is going to become minus 3. And this makes sense. I'm going to multiply this by a minus sign. I'm going to divide this by 10. So that's 0.1. I'm going to divide this by 10 as well. I'm going to swap these rows around. Well, and there we have our answer. So, therefore, this is equal to 0.3 times 0.2 to the power k times the eigenvector minus 1, 0, 1. Oh.
If you've got this correct, you can practically go to the next one. Honestly, this is 99% of the work.
0.1 times 0.5 to the power of k times the vector 2 minus 3, 1 plus 1, just literally plus the vector. Or actually, it is.
No, it's
1.
one.
So it's the eigenvalue 1, and it also has the coefficient
1.
1. So it's just literally plus the vector.
Which is going to be real interesting when it goes to infinity.
Check my answer. I'm a legend.
Yeah, so this is going to be real interesting.
So what happens when it goes to infinity? Well, it's for sure going to be, because this thing doesn't go away, and this thing goes away, and this thing goes away.
Check my answer.
God, we're good.
We're gaming.
We are most definitely gaming. Okay. So, the owl and the wood rat populations for time k is given by blah blah blah. Thousands rats, blah blah blah. They're described by these equations. P measures the rate, the deaths of rats due to predation by the owls. The predation parameter P is equal to 0.2, and you start with a positive number of owls and rats. Imagine starting with a negative number of owls. Will the owl population grow or decline in the long run? So the owl population is 0.5 times OK plus 0.4 times RK. And RK is equal to 0.2 times OK plus 1.1 times RK. I'm tempted to just say 1, 1, 1, 1. Then this thing will be 0.5 plus 0.4, so that's going to be 0.9. And this will be -2, so this is also going to be 0.9. Ooh. Yep. So the eigenvalues are 0.7 and 0.9. I didn't calculate that at all, I just made a wild guess. Cool. Classify the origin as an attractor, repeller, or saddle point for the dynamical system, blah blah blah. So how we're going to do that is we're going to make a what's it called? A characteristic equation, which is minus 11 divided by 10 is equal to 0. Well, I'm just going to put this down as 1.1, which because it's easier. And this is going to be 1.7 times 1.6 minus 3.3L plus L squared minus 1.1 is equal to 0. I don't know why I put that bracket there. Then I'm gonna grab my, wait, can I say, oh, no, fuck off Cortana. Go exa 1.7. Do I have to say comma? Fuckers. 2.72 minus 1.1, 1.62. So that's gonna be, therefore we have L squared minus 3.3L plus 1.62 is equal to 0. Surely there will be two values such that this is this just goes nicely, but I guess that means we have to do the thing. So this is going to be 1. Or actually it's negative b, so it's positive 1.65 plus or minus the square root of 3.3 squared. What is 3.3 squared? Instinctively you would say 9.9, but it's actually 10 plus 8, 10.81 or 0.89 minus 4 times whatever the fuck that is. So that is 4 times 1,62. So 6,48. So then we are left with 1.65. Oh, it's actually this thing should be divided by 2 as well. The square root of 4.41. That's probably some neat little number. Probably like 2.1 or something. Actually, that's the square root there. Hey! Not to say I'm a god, but I'm a god. But here we can easily tell that this is like both of them. Actually, no, it's a saddle point. So this is going to be 3.75 or what's it called? Honestly, I'm like too lazy for this. So we have 1.65 minus 2.1 and minus 0.45. So we have one that is bigger than 1 and one that is smaller than 1. Therefore, we have one. Therefore we have a saddle point, and these are like the eigenvalues.
Also, bigger than 1 or smaller than 1? Do you mean
in absolute value?
Yes.
So in magnitude.
Actually, in magnitude.
Find the direction of the attraction. This is given by line through 0, 0, whose direction is defined by a vector a, b. Well, we have to find then the direction of attraction. So we want to know what. So the thing that goes to 0. So that's that's this one. So we want to know the eigenvector of this one. So we get 1.7 minus. Actually, it's minus the eigenvalue, so it's plus this. 1.1, 0, 1, That's 2.05, 0. I'm gonna start off by multiplying or adding these two up first of all. So this is gonna become 2.15. So I'm just gonna multiply everything by like a fucking 100. Okay. Then I'm going to divide everything by 5. This is gonna be 22. This is gonna be 43. This is gonna be 20. This is gonna be wow, that took way too long. 21. I'm gonna subtract this one from the top one, so this is gonna become 1. And this is gonna become 23. I'm gonna multiply this by 21. 23 times 21, that's the same as 22 squared minus 1. Oh. I don't know what 22 squared is though, so my neat little trick unfortunately didn't help this time. 484. 483, I'm dumb. Then I'm gonna subtract the top one from the bottom one, so this is gonna become 0, and this is gonna become negative. It doesn't matter because I can subtract it. I can divide by the number itself, and it will become 0. Then I can get this back to 23, and this back to 1, and then I can get this back to 1, and it's gonna become 1 over 23. Wait, actually, what? But then I can subtract the bottom one from the top one. This is gonna become 0, and this is gonna become 1. But that's the 0 vector.
Mm-hmm.
So then I fucked something up.
Probably.
So this is 2.15. Is this the matrix we went to deal with? These are 0.1 apart, so that makes sense. Okay, and it was negative. Yeah, okay. So I did have to solve this one. I just fucked it up somewhere during the solving. Let's try that again. I'm going to subtract 2 times this one from the top one. That leaves me with -3. I'm going to divide everything by 3, multiply everything by 20. Subtract the top one from the bottom one. This is going to become what? Did I fuck something up over here? Actually, let's do that here. Oh, I fucked something up over there. Pog. Oh! Motherfucker, I forgot to divide by 2, so this is actually 1.05. So that means the answer is either 2.7 or 0.6. That is really funny because the answer for the first one is still correct. Either way, we want the one who's the direction of attraction, which is this one. So let's do that again, but this time with proper numbers. Sorry for wasting you guys' time. I just fuck up sometimes. 1.1, 1.1.
But it happens.
1, 1.0. Oh. I wonder if this is a multiple of itself. So this becomes 1, this becomes 1, this becomes 0, this becomes 0, this becomes -1. and then we end up with this is the vector 1 1, so I can say the vector 1 1. How the fuck that up? Oh wait. Okay, yeah. I already put down the equal sign, but I didn't do it there. So that it should actually be let's see, x2 is equal to x2, x1 is equal to negative 1 x2. There we go. Fuck me. Okay. And then we have the direction of repulsion, which is the same thing, but instead of that we take this. I love solving this stuff for 2x2 matrices because you know one of them is the multiple of the other. This is going to become -1, this is going to become 1.1, this is going to become 1, this is going to become
One is a multiple of the other.
-1.1. Since you are working with eigenvalues and eigenspaces are always, or no. Okay, to get the eigenvalue vector, one of these two has to be 0, right? Or one of these rows has to be 0, because otherwise you're going to end up with what I said.
Yeah, in that way, yeah.
Yeah, so I already know the top one is a multiple of the bottom one. I just have to figure out what.
Real quick, what are the eigenvalues for this matrix, or have we not found out yet?
Yeah, it is 0.6 and 2.7.
Yeah, okay, so here again you can see that 1.7 plus 1.6 equals the sum of the eigenvalues, so that trick always works.
Cool.
Poggers.
So then we have x. Okay, so then we have this equal to the vector of. I really need to get a new mouse. I was desperately trying to scroll down there. So 1 and 1.1. There we go. Classify the origin as blah 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 or blah. Uh, 0.1 minus. I love how like these two are probably hand chosen and these two are probably random generated. But it is a good. Okay, guys, I'm going to stop doing maths and I'm going to wait for one of you guys to answer this question for me.
Hmm?
And I don't want any of you to do maths either. I just want you to look at the questions.
I think it's a settle point.
Yeah, I think it's a settle point. Give the direction of greatest repulsion.
Yeah, I gotta love these questions, honestly.
Yeah, but it could have been a settle point. Settle points are great.
It could have theoretically been a settle point, yes.
No, because settle points have one direction of repulsion and one direction of attraction, so it would be redundant to say
there
greatest.
is still one direction of greatest repulsion.
Yeah, okay, that is true, but I trust Graspel to be
there is
dumb.
repulsion, which is slightly less.
If there's anything I've learned, it's that Graspel is dumb, but it's consistently dumb.
True.
Okay.
Honestly, wouldn't call it consistent. I would just call it most often.
It's consistently, yeah, consistently dumb.
Well, it's consistently a piece of shit, that's for sure.
What I want to say is consistently inconsistent.
How do you get a fucking square root in Word?
/sqrt and then just imagine there's a square root there.
I hate you.
Okay.
Square root by 13 is 1 divided. Okay.
Okay, I do have to calculate them anyways, unfortunately. Actually, I shouldn't even just write this stuff down. I can just do it by heart. So this is going to be 0.1 minus L, 0.2 minus L, minus 19 times 9 divided by 50 is equal to 0. At this point, I fully trust you guys to...
I wouldn't.
No, me neither. I fully trust you guys to do this calculation, even though I made a mistake in it just now, but I don't care. So it is minus 1. Huh? It is approximately minus 1.7.
Vind je goed?
Or 2. Well, I guess that is... Oh no, it's not. Why is it saying approximately? It's exactly.
Because there could be a 0.01 difference to calculation or something.
Yeah, but there's
It
not.
uses a theory that gives approximations also when the value is exact.
That's dumb. 2
Yeah.
or minus 1.7. So then we have a look here. The direction of greatest repulsion. So that's for 2. Then we have 0.1 minus 2 is minus 1.9. Then this is minus 0.45. 19 over 10 is 1.9. And boy, am I... Wait. Greatest repulsion, that's 2. But then this should be minus 1.8. Is 9 divided by 5? Oh, wait. Huh. Oh, it's... Yeah, okay, this is just 1.8. I thought it says 5 divided by 9 and not 9 divided by 5. Either way, woohoo. I can guess what this is, so I can say this is equal to... I don't even write down the zeros on the right anymore. So then the answer to this thing is x2 is 1 of x2 and 1 18 over 19 x1. The fact that they... Gee golly! I wonder which one it is! Realistically though, this is pretty interesting, so let's have a look. Let's get the eigenvalues real quick. Real quick, he says. 1.4 minus L. 0.6 minus L. Plus 0.2 is equal to 0. L squared minus 2L plus 1.4 times 0.6 plus 0.2 is equal to 0. Wow, this keyboard does not have a calculator key. I am so scared. Does your keyboard have a calculator key? Leave that reaction and many more below so I can gain content. 1.04. Okay, so then we have positive 2 divided by 2 plus or minus the square root of 4 minus 4 times 1.04 divided by 2. So this is 4 minus, so this is 0.16, which is actually equal to 0.4 I. Is that divided by 2 yet? No, so that's actually 0.2 I. Hey, I was correct. Wow, cool. I didn't even look at that. It's a repelling spiral point because the absolute value of this is greater than 1. In which figure are shown some orbits of the system.
Yo, can I ask you a question real quick?
Ask ahead, King.
The fuck is the like in general VC?
Yeah.
Okay, shit, this doesn't fucking show properly. But it's like, if you have a basis W, what the fuck is this? Where this thing is at the top? So, B loodrecht, I guess. Because I don't recall that notation being used, and that could be because I don't pay attention, but it could be because
I've seen it used.
Yeah, no, it's like the it's like the row space into the column space or something like that. Let me see if I can find. Yeah, no, let me see if I can find it real quick. Actually, it's probably in here somewhere. What lecture are you at?
Next one.
Yeah, here. The orthogonal complement is the set of all vectors that are orthogonal to all vectors in W.
Oh, screenshot.
Screenshot.
Sell water to a fish, sell the time to a clock. 7 press on the
Oh no, I'm gonna get copyright strike by PewDiePie. Okay, so the thing is, because this is a repeller, because both of the absolute values of this thing are bigger than 1, because it's 1 plus something, we know that it's gonna start out at 0 and then apart, drift away from that. So, let's see. This one could be it. I think it's a more uniform thing though. It's not this one, I know that much for sure. It could be that one. It is not this one because this one goes towards 0. And it could also be this one. Now the question is... Huh. I would say which one is the greatest... the greatest attraction, but they're like equal, right?
Just guess, Lemeo.
Ooh, solid, solid. It's this one. Fuck. Which one was it? Oh wait, we don't see that yet. What's the direction of rotation? How the fuck do we tell that? Oh wait, it's probably the direction of rotation can probably be found by taking the, I guess, the tangent of this thing. Or actually, you can. It's better than the tangent. Paint. So we have 1 minus 2. So it goes this way. Therefore, it's a rebuilding system working leftwards. So it's not this one. And it's this one, but didn't I click that? Wait, it's plus or minus, so it shouldn't matter. It's correct. Oh, no, I wanted to see it! Can I go back? No.
Dikke oef.
I have no clue why I chose that one. Okay, let's have another look. Then we have one. Let's actually do this one completely. So this is 1.5 minus 2.5 L. This becomes 1. This becomes plus L squared is equal to 0. And then we have L squared minus 2.5 L plus 1 is equal to 0. Then we have L minus 2, L minus 0.5 is equal to 0, so L is equal to 2, or L is equal to 0.5. Okay. Cool, cool. So now what we do is we fill it in the matrix. So we have 1, 0.5, 1, 1.5. Oh. We subtract 0.5. Then we get 1, 1. This one has eigenvector 1, minus 1, or minus 1, 1, doesn't matter. Then we have this minus 2, so this becomes minus 1, 0.5, 1, oh, 1, minus 0.5, well this thing falls away. I could theoretically just not write down the second line. However, it's good to have a check if your values are correct. And then this becomes equal to. So then we have 0.51. So these are the two things. This one belonging to 0.5. This one belonging to the eigenvalue 0.5, and this one belonging to the eigenvalue 2. All right. So they should have equal impact, right? Because when you have a vector like 1, this will pull with equal force on it at this one. So let's see, we have this line, or 1 minus 1, so this line is for the 0.5, and let's see, 0.51. Wait, that should be... Hmm. 0.51. So that should be... Oh yeah, this could be it. So then it's either one of these two, and the question is which one? Well, we know that in this direction it actually goes towards 0 because the absolute value of 0.5 is less than 1. And in this direction it's actually bigger than 0, so it goes from here to there. And you can see here that this is x0 and this is x4, so it's going this way. Alright, back to practice. Okay, so we only need to do 15, 16, 18, 19, 20. So 5 to go. Yeah, okay, cool. Makes sense. Pre-lecture exercises. Let's see, what thing are we doing? Imagine doing the midterm. So we have the inner product and orthogonality. What is the length of this vector? Well, that's just the vector times itself, square root of that. Right, so it would be the 1 plus 4 plus 4, 9 plus 16, that's 25, square root of that's 5, yep. Distance between two vectors? Well, that's just one minus the other, and then the square of that constantly, right? Let me check that. So that's going to be... I'm going to do left minus right, so that's going to be minus 1 squared. Left minus right, it's going to be minus 5 squared. Left minus right, that's going to be minus 5 squared. Left minus right is going to be minus 7 squared. Equals to 100, square root of that is 10. Yes?
Hello,
Hey, Berend! Gezellig.
I'm back.
Welcome back. The unit for the vector, the unit vector is in the same direction as v given by... Well, this is just this thing divided by the distance. We already calculated the distance here being 5, so we divide everything by 5. Orthogonality. A vector is orthogonal to a subspace of W if x is orthogonal to W for every W in V. In W and W. Notation, x is orthogonal to W. If vector P is orthogonal to W, if and only if each of the spanning vectors... only the spanning vectors. Cool. And we have the orthogonal complement. The set of all vectors that are orthogonal to all the vectors in W. Yep. Okay. The orthogonal... okay, so this is a little bit of a fucky one. The orthogonal complement of the column space of A is equal to the null space of A transpose. And the orthogonal complement of the column space of A transpose is equal to the null space. The dimension of W and the dimension of the orthogonal complement of W is equal to n, which makes sense because if you look here, this is 3-dimensional, then this thing is 2-dimension, this thing is 1-dimension.
Can you scroll up a bit to where the yes? So yeah, because because I know that the column space is basically like the output space, so the inverse or the orthogonal fucking basis of the output space is the transpose of the null space, which kind of makes sense. It doesn't make sense that you transpose it, but I guess that's the same way to get them in the same dimension.
Yeah. Fair.
Yeah.
I don't have an intuition for this, but I can learn the formulas.
Yeah, fair. Practically, the column space is the output space, like it's the space of all the values that the output can take.
Yeah.
And you kind of want the inverse of that, because you take the orthogonal thing, orthogonal basis. However, that's got to be in the same like dimension as the column space. So, and the null space is not in the same dimension, but the null transposed is in the same dimension. No, because with a 4x3 vector, the null space
4x3 vector.
like
matrix, yeah.
Yeah. With a 4x3 matrix, the null space will have will be like 1x4 or something, and if you transpose it, it has the same dimension as the fucking what do you call it? As the columns. I'm probably rambling, but it makes sense in my head.
Yeah, that's good. It gets that it makes sense. Well, application. Oh wait, we're talking about Hamming codes. Those are cool.
Oh yeah.
Orthogonal sets and orthonormal sets. So orthogonal sets means that everything with a dot product with each other is equal to 0, and an orthonormal set is so that everything with each other is 0 and it's also normalized. So the distance of everything with itself is equal to 1, or the magnitude. Basically, the magnitude of each vector is 1. Yeah. Okay. U1, U2 is an orthogonal set. Not true, because when you take these two, you get 0 plus 1 plus 0, which is not 0. Let W is equal to span U1, U2, then Z is equal to the complement of, or the orthogonal complement of W. Well, we can check that, because if we do this thing times that thing, we will get 3 minus 3 0. If you do this thing times that thing, we get 3 negative 3 or 3 minus 3 0. So this is true because because both of them are equal to, or both of them with the dot product with both of them and Z is equal to 0, and therefore if, let me scroll up a bit for that. A vector X is orthogonal to W if it is orthogonal to all the spanning vectors, which we just discussed. Cool. Is the following set orthonormal? If you multiply this one by itself, you will get 0. Or 1/4 plus 1/4. Or orthonormal. Let's see. Let's do that one first. My bad. This one multiplied by that one gives 0. Okay. So it is orthonormal or orthogonal of orthonormality. That means that is the magnitude of these vectors should be 1. Sorry that I'm taking a little while. I'm getting confused by things. Orthonormal and orthogonal, blah blah blah. So this thing squared is 1/4 plus this thing squared is 1/4. That's not 1. I think if you had like 1 over the square root of 2, then it would be correct, but it's 1 over 2, so it's not correct. Is the tableau an orthonormal basis for r squared? Well, there are two linearly independent vectors, and also they have if you multiply them with each other, you get 0, because this is like 1/10, this is negative 1/10, and if you multiply them with themselves, you get 0 and 0, or 1 and 1, yeah. The vectors, yeah, this is not true. Okay. Is this the Gram-Schmidt thing?
Yes.
Okay.
If you want to construct an orthonormal basis to a original basis, then you use Gram-Schmidt.
Oh wait, no, Gram-Schmidt is like next lecture, I think. Yeah. So this is the projection of all the orthonormal bases or orthogonal bases of anything onto a. It's the projection of the point onto a basis, but that basically means by taking these values for the coefficients of this basis, then you will get y. Which makes sense because this is like y projected onto this plane, y projected onto this or line, y projected onto this line, and then you will eventually get the output. Okay. And this thing makes sense as well because if you have v1 times v1 is 1, then this will just be divided by 1. And we also have orthonormal columns. That means if u transpose is equal to u inverse is equal to I, which makes sense. Ux times uy is equal to x times y. The absolute value of ux is equal to the absolute value of x. And ux is orthogonal to uy if and only if x is equal to if x is orthogonal to y. Okay, cool. Compute u dot v. 8 minus 14 plus 15. That's 9. Square root of that is 3. Oh, wait, shit. Yeah, I forgot. I accidentally took the square root. Shouldn't have done that. Computate the distance. Compute, not computate. Between x and y. So that's square root of 1. Plus. Let's see. So this minus that is 1. This minus that is minus 4. So that means 16. Square root of 17. Let's go. Find a unit vector in direction u. Well, then we take the square root of 4 plus 1 plus 1, square root of 6. So we take that vector and we multiply it by 1 over square root of 6. What is the length of the vector? Well, that's the square root of minus, or actually, I'll just say 5 squared plus 4 plus 4. Distance between these two vectors, that's the square root. That's like minus 10 minus minus 5 squared plus 8 minus 6 squared plus minus 5 minus 3 squared. Why is this wrong?
It should be -3.
Thank you.
No problem.
There we go. Find a unit vector in the direction of u. Well, that is. Oh, this can actually be done easier. So I can say square root of 25 plus 2 plus 4 plus 4 times the original vector. Minus 5, 2, minus 2. Do I have to explicitly add it in here? So let's see, we have 25 plus 4, that's 33. This would make sense. What the f- Okay. Cool. I filled something in and then I said, no, you're not allowed to do that. And then I changed to something else and then it was, yeah, right, your original thing is the answer. So now...
We gotta
Okay.
love Grapple.
For all vectors v and u and v and Rn, this is true. Yes. Product of numbers are commutative and addition of numbers is commutative as well. For all vectors in u and scalar c. Well, let's actually try that. So if we have a and a vector, let me scroll up a bit. If we have the vector a b and we multiply it by a scalar c, that will become ca cb. And we have square root of ca squared, or that because let's do it like this: c squared a squared. I can already tell it's true, by the way. B c squared b squared is equal to the square root of c squared times a squared plus b squared. Oh, yeah, is equal to square root of c squared times square root of a squared b squared, or plus b squared. My bad. Is equal to c times the absolute value of x, or in this case u, because they call it u. True. Motherfucker. It's the absolute value of u. Ah, oh, that's tilting. That makes sense, but it's tilting. So we have the vector 1, 2, and the number -1. Yeah, I forgot about that. That's kind of annoying, but makes sense. Okay, A and m by n column, the orthogonal complement of a column space is equal to... So we have the column space, the orthogonal complement is equal to the transpose of the null space. I remember this by very easily thinking that the what's it called? Transpose? The transpose? Okay, so the column space is equal to the null space, and there should be a transpose and a orthogonality sign in there somewhere.
Juist.
Yes. The inner product is a real number. Give a 1 by 1 matrix. Which formula can be used to compute the distance? Well, it's the square root of all the all the differences squared, which makes sense. In Rn, what is the things orthogonal to Rn? Well, there is no vector that is orthogonal to all n, or to everything, you know, so it's the empty set. Maybe the 0 vector is orthogonal to... Huh? This notation was the orthogonal... Huh. Being orthogonal to a vector mean... Oh! Yeah, being orthogonal to a vector means that... the vector times the other one is equal to 0, right? So 0 is orthogonal to every vector. Okay. Wait, by definition then 0 is included in every orthogonal complement. Well, okay, that makes sense.
Yeah, because the orthogonal complement is a span. Yeah.
If S is an orthogonal set of non-zero vectors, then S is linearly independent. If S is a linearly independent set of non-zero vectors, then S is orthogonal.
It has to be one because like not every set that is linearly independent is orthogonal, is it?
Yeah, exactly. It would be pretty funny if 2 is true though.
You guys still, bro.
We're like halfway through.
Yeah, last time it took it 8 hours.
Damn.
Yeah, man, on the grind.
Mad lad.
Thanks. Every diagonal matrix D is an orthogonal matrix. So for a matrix to be orthogonal, the columns have to be... And this is what confuses me. Where is it? Okay, so it's an orthogonal matrix has orthonormal columns. So this is false because you can have columns which are orthogonal but not orthonormal. Yeah, and you know that won't happen unless they are 1 and minus, or like they are not 1 and minus 1. Cool. Suppose U is a matrix with orthonormal columns. Which are possible sizes for U? Orthonormal columns. So, well, that's basically orthogonal because, you know, we can just divide them by the length. So I know for a fact that 2 by 3 can be done because that's like this. I don't think 3 by 2 can be done because this will not be linearly dependent.
Wait, hold on. What's the question?
Suppose U is a matrix with orthonormal columns. So basically orthogonal columns with length 1. Which are possible sizes for U? I know 2 by 3 can probably be done. And a 3 by 3 can probably be done. But 3 by 2 probably not.
So 3 wide and 2 high, you mean? That's
Yeah,
2 by 3.
like this is impossible.
Yes, correct.
Yeah, because we had this thing.
You only have 2 dimensions to spare.
Yeah, exactly. Where was it? The dimension of W.
Yeah,
This one.
Yeah.
And in this case, this would be like 3 plus a positive number, maybe 0, is equal to n, which is 2. So, you know, that won't happen. So only A and B. Only B and C.
Yeah.
I keep fucking up, man.
The first number is the height.
Yeah, I know, and I should know, but I don't. And ach.
Ach en wee.
Ach en wee. What a good.
Juist.
Juist.
Graspel's tired.
Yeah, but so are we. It's only 4 o'clock, 3:30 actually.
We're tired of fucking Grespel.
Graspel. Graspel.
Fuck Grespel. Al mijn homies heten Grespel.
Al mijn homies heten Graspel, hallo.
Het is toch zo?
Alright. Which of the following
Of niet
statements...
dan? Of niet dan?
Nee, precies. Is an orthogonal matrix with orthonormal columns. T is the linear transformation of the standard matrix U. 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 U.
Oh god.
Then T preserves length and orthogonality. True. The reason I know this is true is because over here at the bottom, you see that when you have an orthonormal column, it preserves length and orthogonality. Alright. Okay, so this is the last one for this one. Calculate U times U. Well, that's square root of 2.
That's a very difficult question.
This is pain.
Well, it's without a square root, since you're not calculating the length.
I don't know. Wait, so then it should be. Yeah. Okay.
Poor you.
Assembly God.
I'm not Tim, okay? Tim is the math god. I am the assembly god.
For real though, Tim Mad Lad.
Tim is mad lad. Calculate V times U divided by U times U. -2 plus 3/2.
Nou, veel succes nog. You.
You.
So this is -half times U. -1/2. I don't know why I keep putting down the square root. You only put down the square root in the case of length, right? Like when you're calculating dot products, you never fucking put down the square root. Why do I keep doing it?
Where's the square root in the dot product, Nave?
I don't know. Find the unit vector in the direction of 1 over square root of 16 plus 16 plus 25 times 4 minus 4, 5. Find the distance between, so that's the square root of 5 minus 2 squared plus 9 squared. Are the given two vectors orthogonal? 2 minus 6 plus 2 minus 15, or yeah, minus 15. So this is like minus like 17, so no. Are they orthogonal? Let's check. So if we have, so these two are orthogonal, the rightmost and the leftmost, or the rightmost in the middle. This is -5 plus 4 plus 1. These two are orthogonal, and this is also orthogonal. So yes. With every passing second, I want to do less and less of this. So we have -20, -4 is -24, plus 24, these two are. -12, -9, minus like a really big number, minus an even bigger number, what do you mean? There we go. This is how I do my mathematics, guys, minus a really big number. It is an orthogonal basis for R3. 6 minus 6, 2, 4, 0, 3, minus 3, yes. Oh, this is also a way to do it. Express as a linear combination, give the vector, blah blah blah. Oh, yeah. Okay, sayonara guy. Good luck on your quest. Do not fucking fuck this shit up. 5 minus 3, 1. I'm gonna add this one to the top one. Then the top one, or actually this one to the middle one. This is gonna come 0. This is gonna come 4. This is gonna come 2. This is gonna come 2. Divide this 1 by 2. This is gonna come 2. This is gonna come 1. This is gonna come 1. Subtract this one from that one. It's gonna come 1. It's gonna come 1. It's gonna or 0, 0, and 4. Then this is gonna become 1. This is gonna become 4 divided by 3. Then I'm going to add 2 times this one to the top one. This is going to come 0. This is going to come 9. This is going to become 3. This is going to come 1. This is going to become 3. Then I'm going to let's just do it like this. I'm going to subtract this by divide this by 3. I'm going to add it. I'm going to multiply this thing by -1, and I'm going to add 4 times this one to that one. This is going to become 0. This is going to become 1 over 3. I'm going to swap these columns around. That's actually really not that hard. So then we have our vector. He just got vectored. 4 over 3, 1 over 3, 1 over 3. Bam. To the above ref. Okay. Is the set orthonormal? Goeie vraag. This square becomes 1/4. This square becomes 1/4. So no. It's orthogonal, but this one is not. Yeah, that's what I said. Cool.
So Jure, is a set with one value orthogonal?
Yes, by so it says for all pairs, any set of one vector is per definition orthonormal by what's it called?
Epic.
What that one thing that Stefan always says. Stefan, dude, I miss him. Vacantly true.
Yeah.
There we go. If it's an orthogonal basis for W, then multiplying by a non-zero scalar C gives a new orthogonal basis. Yes. It's just intuition. Oh, I thought it said the whole set by C, but it was only V. Then it's a lot less intuitive. Okay, I imagine. Compute the dot product of these two. Well, it's minus 25, minus 5. Can we have exam questions like this? Square root of 9 plus 49. Distance is square root of...
Honestly, if it's the same as calculus, then LA's exam questions will be easier than Graspel.
Like 49. That was... I don't know. I didn't have a hard time with calculus. I got like a 6 point something, but it wasn't easy either. If you get what I mean.
It was easier than the fucking Graspel.
That's true, and I completed Graspel with the help of like everybody else, but.
One divided by.
1 divided by, yep. You see this orange? We don't talk about it. They need to be orthogonal, therefore the dot product of these two has to be 0. Therefore we have minus 9 minus 4h minus 8 is equal to 0. This becomes minus 17 minus 4h is equal to 0. 17 plus 4h is equal to 0. 4h is equal to negative 17. H is equal to minus 17 over 4. H is equal to minus 17 over 4. For 4 vectors of the same size, the equality of A times B times C times D, D times C times B times A. Well, I mean, since the dot product is what's it called, commutative, and these two numbers are just exactly that, numbers, then even if they weren't the same size, this would still hold. Okay, so we want the square root of minus 3. Actually, let me get rid of the square root. So it's minus 3 squared plus 2 squared plus h squared is equal to 64. This becomes 4. This becomes 9. This becomes 13. We do 64 minus 13. That's 51. And we say h is equal to plus or minus the square root of 51. Is that correct? So we do end up with h squared is equal to 51. Yeah, okay. Given non-zero vector u, there always exists a unique unit vector orthogonal to u. No. Oh fuck, non-zero. Fuck, I keep reading over that. Then yes. No, wait. So let me actually try this out. So for a given vector, let's say 1, 2, we will get there will be a vector AB, so that 1A plus 2B is equal to 0. But this is not a unique vector. This is a set of infinitely many vectors, because there's a free variable. Wait, I should have clicked fucking. I had the right idea, but I clicked the wrong button.
Imagine it's green.
Yeah, then I would cry. Not really, but it would be pretty funny. Oh god, another one of these. 18. Yeah, okay, this is correct. 12. Wait, 12 plus 6. Yeah, this is correct. 6 minus 18, 12. It is an orthogonal set. Create an orthogonal U. This is like the most trivial thing ever. Holy shit. Oh, it needs to be an orthogonal matrix by putting multiple of the given vectors on the columns. So to create an orthogonal matrix, we need to create an orthonormal column space. Me? Oh, this is so trivial. Also me. Wait, this is actually really interesting. So it's 3, negative 6, 2, 6, 2, 3, 2, 3, negative 6. So this is, let's see, all of these contains 6, 2, and 3. So I can say the square root of
The
9.
2 from the most left vector should also be minus 2.
Ah, yeah, my bad. 9 plus 36 plus 4. This is the square root of 49, which is 7. So that means I can say 3 divided by 7, negative 6 divided by 7, minus 2 divided by 7, 6 divided by 7, 2 divided by 7, 3 divided by 7. That's not a 7. And here I can go 2 divided by 7, 3 divided by 7, minus 6 divided by 7. Beautiful. Are the columns orthogonal? So columns are orthogonal. That does not mean the matrix is, but the columns are. Let's have a look. 4 minus 4, yes. 2 minus 2, yes. 2 minus 8, or 2 plus 8 minus 10, yes. Matrix U is orthogonal if and only if UTU is equal to I. Well, we can actually we know that in this case U transpose is actually equal to U inverse. Is that true though? Yeah, because I can multiply with U inverse, and then we get U transpose is U inverse. And we know that U inverse times U is equal to 1, or the identity matrix, and U times U inverse is also equal to the identity matrix, so yes. Are the columns orthogonal? No. Yeah, no, this just didn't, no. All the columns get multiplied by the same scalar vector. However, it's an orthogonal matrix, which means the columns are orthonormal. It would only work for CS1, but for the rest it wouldn't. Is the matrix orthogonal? No, it is not an orthogonal matrix. Because, yeah. Is the matrix orthogonal? The square root of square root of 2 squared plus square root of 2 squared? Yes, it is. Find the inverse matrix. Ooh, well, let's just, since it is U transpose, yeah, okay. U inverse is U transpose, so we can transpose this, and we will get the inverse. So I can say minus square root of 2, square root of 2. Is there really, holy shit. Minus square root of 2 over 2, minus square root of 2 over, minus square root of 2 over 2, square root 2 over 2, minus square root 2 over 2. There we go. For an m by m matrix, vectors of the null space of A are orthogonal to the vectors of the row space of A. The row space is equal to the transpose of the column space. So what this is saying is null A is equal to col A, or vectors in the null space are orthogonal to vectors in the row space. Transposed, that weird orthogonal sign, which is true. Ooh, find a basis for find a basis for W inverse, or the orthogonal complement of W. We know that is actually a span of only one vector. Yeah. So we need to have a vector such that
What happened to all the people?
I went to have lunch and then when I came back nobody was there.
Oof.
We're just vibing here.
Yeah, we're just vibing. We have like what, 7 people or something?
The Arctic Aaron.
8. Yeah, this is the Arctic Aaron.
We're the people that are gonna pass exclusively.
Okay, to be
Yeah,
fair,
we
people can very well be within their ADS project right now, but
it's a bit late for them. Isn't it?
we're only like 3.5 hours in though. That's like nothing.
Oof.
Find a basis for the Oh yeah, okay. So find a basis for the orthogonal complement of W, which means we need to find vectors that are orthogonal to all of to both of these. Both of these nuts. So we know that for our vector, let's call it x, y, z. We know that -3 times x plus 1y plus 12z is equal to 0. And we know that 6x plus 1y or 6x plus or minus 18z is equal to 0.
0y.
0y, yep. Okay, now how do we well, this
So
is just
you can one say like you can make this a matrix, but you can like see that x equals 3z, and from there you can work on out, but do it however you like.
yeah, true. That could also work. I'm gonna make it like this though, but it would work. I'm gonna multiply this whole thing by 2. It's gonna become 6 to 24. Add the top one to the bottom one. This is gonna become 0. This is gonna become something that I will turn into 1. I'm gonna turn this into 0, and I'm gonna say this is 3. This becomes 1. This becomes 0. This becomes minus. This becomes 1. This becomes minus 1 over 3. With the equal sign here, this becomes like this. So what I know is that x1 is equal to 1/3 x2. I know x2 is equal to x2, and I know x3 is equal to x3.
Right, it's equal to 0, don't you?
Hmm?
X3 is equal to 0.
Yeah, x3 is to equal to 0 because otherwise.
1x3 is equal to 0. It has to be.
Oh,
0.
yeah. Okay, yeah, my bad. I forgot about that. So that makes sense. So then the basis of this.
1/3 10.
Yeah, but it's a basis, so should it be the span then? Yeah, it should be.
The span of 1/3. Yeah, of 1/3 0.
1/3 1 0.
Yeah, 1/3.
Is it 1? Yeah, it's 1/3 1 0.
It's
the span.
It's 1/3 0, I think.
Is it? Can you make it the span of this all?
Yeah,
it's a
that,
basis.
it is.
Oh, yeah.
Huh.
Then we did a calculation wrong somewhere.
Well, I can also just calculate this the other way that I know. But that is not like the way that we haven't been taught, but a way that I know to for going through these.
Okay, let me first check. So we know that this is true.
We know that like divide the bottom row by 6. I think that's the easier way to start off.
Okay, so this will be 1 and this will be -3.
And then work
Add
from there.
3 times this one to that, so this becomes 0. This is gonna become
3.
3.
Oh yeah, okay.
Yeah, and then you have a difference. So it's 1/3 and minus 1/3 for the other ones. So it's
Yeah, so this is
it's minus 1/3. Minus 1/3 1/3 1 is the thing.
Yep. Wait, is it 1/3? Because these are the pivot, right? So it's just 3.
Well, you want to express everything in terms of the third one. So that's 3. Yeah. So what you can do is you can make the first one minus 1/3.
No. Okay, what I've
Or-
got now is. So if I put these things here,
Or actually, yeah, the first one will be minus 1/3.
so I know x2 is equal to -3 x3. I know x1 is equal to 3x3, and I know x3 is equal to x3. So therefore, I know that the thing will be 3,
Wait,
-3, 1.
wait. Yeah, I guess. Sure.
Okay, cool. So like they use the fact that the transposed column space is the null space of A transposed, or the
Yeah.
complement of the column space is equal to the null space of A transposed. We did that too, but then we just figured it out ourselves.
Yeah, but that was the obvious thing. It's the fact that, it's a single vector.
Yeah. Same thing here. It's also a single vector. Let's try to do it their way now. So we have this matrix of the column space. 6, -6, -12, -2, 0, 4, and 3, -3, -6. And they want us to take the complement of that, or the transpose of that. So let me see if I can zoom out a little bit.
Transpose was what you found, yeah. What you had.
Yeah, so this is going to be 3, -3, -6. It's going to be 6, -6, -12. It's going to be -2, 0, 4. And this is going to be 3, -3, -6. So this is the transpose of the matrix, right? So I can I can cut this, put it over this, calculate the null space of this, and then we should be in the home stretch. So I'm gonna add 2 times this one to the bottom one, and 1 times this one to the middle one. Start with that. This becomes -2, and this becomes 0. Well, that adds flair. Then I'm gonna add 2
Smooth.
times.
That's
Yeah. Feels good. Wait,
Yeah.
but that wouldn't make sense.
Those are just multiples of -2.
Hmm?
So your null space in this case contains 2 vectors.
Yeah, but it shouldn't, right?
Yes, it should. Because the span isn't linear, they're not linearly independent.
Oh, yeah, that makes sense because the first one and the third one are not are linearly dependent.
Correct.
So the dimension of this thing is only 2, and the dimension of my thing should be 2 as well.
Correct.
Fucking hell, that is cool. 1, 3, or 1, 2, 1. This becomes 1 is equal to. This becomes a minus sign. This becomes a minus sign. So then we know that x1 is equal to -2x2 minus 1x4. We know x2 is equal to x2. We know x4 is equal to x4, and we know x3
is equal to
0. So then I can create this set. I should really stop clicking in there. Of 2 vectors, namely, first one being the x2 vector, which is -2, 1, 0, 0, and the second one being the x4 vector, which is -1, 0, 0, 1.
Boom shakalaka.
Let's fucking go. That is fucking sick. Okay, cool.
We be out here with speed.
Hell yeah. This is just the square root of u1 squared plus u2. I love doing superscript and subscript. It just becomes so fucking messy.
Of course.
I keep putting the square root, man. Is there any vector for which u is negative? No.
No.
Because we're adding 3 squares, right? Is there any vector?
Just the fucking no. I don't want your number. No.
Yeah, this is like Okay, so let me just go over this real quick for the people who don't follow it. This is just, something you should know. Multiply dot product between this one and this one is just this plus this times that plus this times that plus this times that. It's just itself. Any case, any vector for which it is for which this is negative. No, because you're only adding 3 squares, and squares are always positive or 0. Is there any vector for which it is 0? Well, yeah, because the 0 vector squared is a 0 vector. And is there a non-zero vector? Well, no, because you're adding 3 non-zero, so therefore positive numbers, because they are squares.
Either or b square.
Yeah. Okay. If W is a subspace of if W is a subspace and X is a vector that is in W, in both W and W thing, then X is equal to 0. So there is no vector that is orthogonal to itself other than the 0 vector. And here you can see X is orthogonal to itself, therefore X times X is 0. This implies that the distance, or like the norm of 0, the norm of X is 0, so therefore X is equal to 0. Is the set an orthogonal basis? They're not linearly dependent. -9, +9, so yes. Honestly, I'm not even going to use anything for this. I'm just going to say 3/2 times and 3/2. Or this is 3/2 and minus 3/2. Because for the bottom ones, we know that the numbers should be -1 of each other. And for the top ones, if we have like 3 times this one plus 3. Let me just check it first. Okay, yeah. So
They really do be wanting us to do that.
oh yeah, no, I just figured it out.
Yeah, like that was pretty intuitive.
Yeah.
With those
sure.
fucking vectors.
For any other ones, this would have been a good example though. Oh god, this was so long ago that I did all of this. Ugh. All right. Fine. Set B is a basis of W and X is a vector. A vector in W. Compute the B coordinate vector of X. Let me get rid of this first. Alright. I love how we have one guy and he's just muted and deafened. Hello.
Yeah. Hey, Ron.
Yeah, so I just wanted to check up on you because I'm still way too behind to actually understand what's happening.
Fair.
But when are you gonna catch up?
Well, at the rhythm I'm going, I should. The thing is, there's a bunch of OPP stuff I need to do tomorrow morning.
You should be caught up about next month Wednesday.
So what?
You should be caught up about next month Wednesday.
No.
You have exactly 4 days.
Ron, get the fuck caught up, or I'm gonna go over to your house and gonna catch you up.
I mean, if you're gonna help me catch up, sure, do.
Honestly, I would.
You would.
I will catch you up with the Louisville Slugger.
Okay, listen, Ammon. Don't catch me up in linear algebra. I can do it. But please come on Tuesday and help me catch up the whole of IDM because I'm
Sure.
only 3.
Sure, will do.
Okay.
Yeah.
Send me your address at a time, and I'll be there.
You already know my address. What are you talking about?
I don't know your address.
Okay, sure. I'll do that.
Anyway, Yella.
American friend of mine said he would be streaming at 6 p.m. AST. That's midnight.
Sounds about right.
Okay. So we want to know a vector such that a multiple of this times a multiple of that is equal to this.
Yeah.
Anyway, I shall be caught up with linear algebra on Saturday evening. And
Good luck.
We might not have the session. I'm gonna be honest.
That's fine.
All right. Good luck, people.
Thank you. Bye bye.
Bye bye.
Well, first we have to check if it actually exists, right? Because this is an augmented matrix.
Well, it does say X is a vector in W.
Yeah, so it does exist.
It-
Whatever.
it does
I'm just gonna solve it, see what comes out of it. So I'm gonna add 2 times this one to this one. This is gonna become 0. This is gonna become 6, and this is gonna become -6. Therefore, we can conclude that this is equal to 1, -1. I can subtract this from that. This becomes 1. This becomes, well, subtract -1. That's adding 1. This becomes -4. This becomes 1. This becomes -2. And now the question is, does this become a 0 row? If that's the case, then we're good. So I subtract this from this. Then I subtract 2 times -2. That means I add 4. Is that correct? No, I subtract 1 times that. Okay, so I just subtract -2 from the bottom one. Yeah, I subtract -2, I add 2, so this becomes... I fucked up somewhere.
Yeah, I have no clue what you're doing.
Yeah, no, I can imagine. Okay, yank, 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 yank. Okay, again.
You can also just
add-
make this a set of linear equations.
Yeah, I could.
A matrix is a set of linear equations.
Yeah, that's what I'm saying. Just just do it the simple, or well, kind of do it a bit more of a simple way. Because right now, or
Nah.
no way, I'm lost. My brain is just
Okay,
not functioning. That's
we're
it.
gonna add this one to the top one. So therefore I can say this is 1, 1. I can subtract 2 times this one from this one. This becomes 6. I can subtract 2 times this one from this one. It's gonna become 3.
Yeah, now it's correct.
Now it's correct. Okay, so I can subtract -1/2 times this one. Flip the minus sign. Oh. Divide by 3. Or 2, my bad. So now we know x1 is equal to -3 and x2 is equal to...
Yep, -3, 1.
Yeah, how do I input a coordinate?
Same way, vector.
Okay. So this is...
Which I really
-3,
fucking
1.
hate. Fuck people.
Oh,
that,
they still want us to do this.
Yes, because it's a fucking projection. Trust me. At the start, I did it the way you did as well. But just the projection formula is so nice because you can just use it to always project onto it if you have a orthogonal basis. And
It's like a dad who really wants his kid to do football. You just gotta keep on projecting.
Like honestly, fucking, it's like the fucking ABC formula. You just keep using it; it keeps working. Like especially in the next one, you're not gonna use anything other than it.
Well, actually, we're starting with lecture 16, so we only have 16, 18, 19, 20.
Honestly, it was more fun. It was more fun when you had the fucking speedrun timer with the different splits.
Yeah, but I forgot to set it up, honestly.
Fair.
Nice. Time to get some snacks.
You.
Our opinions out here being split. Well, I should probably watch lecture 19, and then I should probably catch up to on IDM so that I can actually help them with IDM.
Well, you should also catch up on lecture 20 because it's already out.
Yeah, I know. I haven't watched lecture 19 yet.
Okay.
The thing to know about me is, people think I'm a good student, but I'm the worst student.
Do you have 6 out of 6?
Yes.
You're a good student. Folk champion.
Do you want to guess what my average is for those 6 out of 6?
5.7. It's worth.
8.25.
Okay. No need to flex. Actually, no. My average of the first fucking quarter was like a 9.2 or something. And
Yeah, I
the
saw
second
that.
Quarter was like
Fucking
a
nice.
7.
Yeah, same.
Like second quarter, so much more difficult than first quarter.
I'm looking forward to that half a point subtraction for OOP project though.
Oof, didn't show up.
Didn't show up.
What happened?
Overslept.
Oh yeah.
Fucking getting the morning group every time, boys.
Same. Fucking one of our group got kicked out on the last meeting with the TA.
Yeah, honestly, we have
He
one
overslept
person.
twice.
We have one person who hasn't written a single line of code, and I still don't know how he's not kicked out.
He's gonna get kicked out if you don't have an adequate part to the group. You're getting kicked. Like you're getting a 0.
Yeah, he's getting a 0 anyways.
Nah, you'll be fine.
But no, like, I wish there are two people I wish I had in my group. Yura for actually, being an organized coder who actually knows the shit.
Organize.
Well, as in, at least he's pretty.
He's good at coding. Let's keep it like that.
We all know he knows how to code.
Yeah.
And then Pigeon, because he could make a pretty good UI.
Our UI is fucking magic. Like, once the video has been submitted and everything, I'll post it in the.
I can tell you, our UI is the shittiest fucking UI.
I have seen one UI and it looked like a fucking goblin drew on a playground. Fucking.
Okay.
Hey, fuck you.
Okay, but guys.
It wasn't yours. It was like a fucking white background, red text, and everything.
Oh, you said I seen one UI and you've seen mine, so I didn't assume it was mine. Okay, cool.
Guys, but get blame. What percentage do you guys have?
Actually, not get blame. I've got the Git inspector.
Stats.sh. Total lines. Whatever. Either way.
Total lines for me. Let me just download the. Sorry, you're after this. I was
about to say, can we after this shut up and go back to the thing?
But this is our break. We're taking a break here.
You guys just had like an hour-long break.
Shut up. Don't be a party pooper.
I just want to know.
My percentage of the entire project is 36%, and of everything that's still a master.
39.
Everything that's still a master, it is 27. The fuck? Oh no, never mind. That's in comments. I've got on master also 36% or something like that.
Nice. Yeah.
With, 6,000 lines written, out of which 4,000 has been deleted.
Okay. What are the git blame commands?
Well, I'm just using stats.sh thing.
What do you say?
I'm using stats.sh, which is like a shell script I got from Kalle.
Okay. Yeah, I have like a git inspector report somewhere I can grab for you if you want. But like I wrote all of the backend, and then like that happened in the first 2 weeks, and after that I just couldn't do too much because I'm really good at backend, but not at front end.
Yeah, I'm very good at backend. I found out.
Yeah.
Backend is easy.
So
I'm
I actually only have 5%. Yeah, I'm the second lowest member, but
what did you do?
The backend, and then I was done, and then everybody put a lot of like time and effort into the front end, and I helped there as well. But I did like 3 major commits, and then we had to merge, but it didn't work well with Git, and we had Git mistakes, so I just sent my code to them. So I don't get a credit for everything I did.
I'm gonna guess you were a team leader type.
Yeah, definitely.
Yeah, that's what I would have liked to have on my team.
Oh yeah, without that it's like really hard. Like our communication and cooperation was so fucking sick. Holy hell. Let's continue. Okay.
Yeah.
Orthogonal projections. Okay, have a good one.
With the lecture. See ya.
Bye bye. Projections onto a line. What is projection of the vector y onto the line through vector u? I have no clue. Which of the following vectors is projecting the line through u equal to the vector 0? What the fuck?
What the fuck? What the it's probably gonna be like the fucking that one formula.
Yeah, the Gumstreet.
No, just the projection formula. If you're talking orthogonal, it's projection formula.
Yeah. Let W be a subspace, then for each Y in the subspace, it can be written uniquely in the form Y equals to I see, okay. So for every Y that exists in the entire thing, it can be written in a projection of Y into W and something in the orthogonality of in the orthogonal what's it called?
Complement.
Complement of W. Sorry, I've been busy with this for like 4 hours. It's getting hazy.
It's fine.
Exactly. So then we have the orthogonal projection. So if we have a basis, yeah, we already had this. And this makes sense of what I said, so. Yeah, okay, so this is the projection of this point onto this plane by having this thing and this thing. Yeah, okay. Application, please shut the fuck up. Orthogonal projection. If y and u are vectors and L is the span of u, then the projection of y until L is a scalar multiple of y. Doesn't have to be. Hell, the projection is the projection of y onto a line is like the projection of y. Y is equal to the projection of y onto a line plus the something within the orthogonal complement of L.
Because the orthogonal complement of the line is the plane around the line, and it's going to be somewhere, like, and that plane will be offset by the line itself, and in that way you can reach every point.
Yep. Okay. If W is a subspace and the projection of y is equal to y, then y is included in W. Well, yeah, that makes sense intuitively. Which is following statement true or false? For u is part of Rn, and the projection of u is equal to 0, then u is in the orthogonal complement of W. Well, yeah, that makes sense because that means if we have like a plane centered around, or yeah, that includes 0. If you project it onto the thing and it's 0, then that means it's within the exact. Yeah, it's hard to explain, but intuitively it makes sense. Subspace with an orthogonal basis, orthonormal basis, different thing. The orthonormal basis, then the projection of y into W is equal to u transposed y. Huh. How does that make sense? It's a standard matrix of the projection. But if it's an orthonormal basis, doesn't this mean that u times u transpose is equal to u times u inverse is equal to the identity matrix?
I think that's u transpose u.
Oh, you're not allowed to take that the other way around, or?
No.
Oh.
Because if you transpose the entire thing, you turn them around and transpose both of them, which turns into u transposed again. So then it's not the same.
I see. Okay. It's a standard matrix of the projection, and p squared is equal to p transposed. Flex. The best approximation is the line that is, or is like. Yeah, okay, so the distance between y and the best approximation is the smallest that exists. This from a vector y to a subspace is the distance to the nearest point in W, which makes sense. Which is also the distance to the projection. Because the projection is the nearest point. Okay. We've only have like...
Actually, you're
7 more pages of theorem.
just saying, you might want to do 17 like beginning. It's like literally a fucking list of questions. Like it's 25 questions, and they're quite nice.
Okay, for the test of your knowledge, I probably will.
Yeah.
Pre-lecture. Start. Calculate the orthogonal projection of W, orthogonal projection W prime, I'm going to call it. W hat, maybe. W hat of W onto the line spanned by X. So then we probably have to use the formula W times X divided by onto the line spanned by X. So it's X times, let me see if I can actually get the Yeah, times x. So to do that, we can say this is equal to. Actually, these should be the dot product, obviously. So let's see, we have the dot product of w and x, which is -12 plus 21 plus 5. We divide that by x squared, or just x squared. Oh wait, okay, I was thinking about the square root of the thing, but I don't have to take the square root because we're not talking about the distance itself. We're just talking about the thing with itself. Okay, so then that's 4 plus 9 plus 1 times the vector of x. And a good realization to have is that the w hat is a linear combination of all the vectors used to build it up. Compute the orthogonal projection w onto the line through x in the origin. Well, again, we can go. Let's see. So that is 15 plus 24 divided by 9 plus 4 times x. I'm getting a lot of messages. I don't know where. Oh, I haven't muted the server yet. Until I turn it back on. Thank you very much. Okay. I put in the wrong thing, didn't I? Yeah, I did. I pressed it, I was like, wait, that doesn't seem right. Oh! Dude, I am so good. Wait, was that the... Okay, no. I was looking at the wrong thing. I was like, wait, that's entirely post-lecture, but it's the pre-lecture. Okay. Update your knowledge. Hey, we're 4 hours in, boys! Woo! We've got a solid...
Yay.
Yeah. I know for a fact that was Berend.
Yep, that's true.
So we have a solid 4 people still listening. You're still here? Shout out to you, man. Alright.
Nice.
If
This is the only reason I'm gonna pass LA.
You are the only reason I'm gonna pass LA.
Fair.
If Z is orthogonal to both U1 and U2, and if W is the span of U1 and U2, then Z must be in the span of in the orthogonal complement of W. Well, yeah, that makes sense. For each Y and each subspace W, the vector Y minus the projection of Y is orthogonal to W. Well, yeah, that makes sense. So if you have a random vector and then we subtract that from the projection, you will get a... Yeah, okay, fuck. It's hard to explain, but I visually have it in my head and it makes sense. It's followed from the definition of the projection. Suppose L is the line spanned by the non-zero vector u in Rn, and y is a vector in Rn. Then the orthogonal projection of y onto L... Let's see... So L is a span of u, and y is a vector. Orthogonal projection of y into L is a vector orthogonal to u. How is that? Huh. Okay. I clicked it way too fast. I have no idea what it said. Following statement true or false? Let all of u be a subspace W of Rn, and let y be a vector in Rn. Then y is equal to y hat plus z, where y is in W and z is in W complement, or the orthogonal complement of. Yep, that's correct. And this thing holds as well. Yeah, this is just, the definition. The basis isn't set to be orthogonal.
true. Important.
Yeah, it is true and it is important, but it's also annoying. Whoa, this is the first time I've seen this one ever. Like, can enter it yourself like that. Holy shit. Let W be a subspace of Rn, let Y be a vector in Rn, then the orthogonal of Y hat onto Y, of projection Y hat of Y into W is the...
Closest.
Yeah, I'd say the best approximation, but that doesn't fit in the sentence, so it's closest.
Hey.
And the distance between these 2 points is given by this. The distance between the point and the... Yeah, it's like literally the definition of the distance between 2 vectors.
Just for a quick second, imagine they were like, we've got the orthonormal complement, and we need to give a name for the distance to the points closest on the line, and just the janitor walks in, Y hat. You're a genius.
It's he's wearing a hat. Isn't that funny?
Hat. No, it's a fucking whatever the fuck the symbol is called mathematically. Headkoper.
Oh.
Oh.
I can't wait to fail this exam. Okay, remember when we did the first part of the calculus marathon in 4 hours and 20 minutes? That's not gonna happen. Let y is equal to the... or let u is... Yeah, let y is equal to this vector, u are two other vectors, w is the span of the two vectors, let u is equal to a matrix consisting of the two vectors. We want to contribute to compute the orthogonal projection of y onto w. Well, you know, I really wish we had questions like this on the thing. So we have 2/3, 2/3, 1/3, 2/3, negative 2/3, 2/3, 1/3. Okay, and that's gonna go actually here. Oh, sometimes Word doesn't do what I want it to. So this goes here, and then we flip it. So then this becomes 2/3, negative 2/3, 1/3, 2/3, 2/3, 1/3. Okay. So then this becomes 4 plus 1 plus 4/9, which is 1. This becomes 2 plus 2 minus 4, which is 0/9. This becomes 2 plus 2 minus 4, which is 0. And this becomes 1 plus 4 plus 4, which is... Huh. Okay. Oh yeah, okay, this makes sense actually. And if they wouldn't be an orthonormal set, but an orthogonal set, would these just be non-zero, but still, like, different answers? So not one? Oh, fuck, we now have to do this, like, the other way around. So we have to take this one. I'm gonna put that up here for now. Whoops. Up here for now. Take this one, put it up down here. Take this one and put it up here. And now we get 8/9. This becomes negative 2/9. This becomes 2/9. This becomes negative 4 plus 2, so this is negative 2/9. This becomes negative 2 plus 4, that's 2/9. Is this a like, what are they called? Matrices with our symmetric matrix. Is this a symmetric matrix? Probably is. So this is 4, that's 5/9. This is 4 over 9, this is 4 over 9, and this is 5 over 9. Would I be able to say 1 over 9 times the matrix of? Yeah, right? 8 minus 2, 2, minus 2, 2, 5, 5, 4, 4. Let's go. The projection of y onto w. Alright. W consists out of u1 and u2, so then we have y times u1 over u1 times u1 times u1
Oh, dankjewel joh.
is equal to, plus, but so let's see, this is plus y times u2 divided by u2 times u2, or dot product u2 times u2, and yeah, that's about it. So let's see, if we have y times u1, that is, god, I forgot that there were so many divided by 3s. That is really annoying. Well, realistically, no, we couldn't. Okay. So this is 8 over 3 plus 8 over 3 plus 2 over 3. And this is 4 over 9 plus 1 over 9 plus 4 over 9, which is 1. This is orthonormal. Therefore, actually, we don't have to worry about the bottom. So this thing can go away entirely, and we can just say it's this thing times u1, and it's this thing times u2. So this is 8 plus 2, that's 18 divided by 3. 18 divided by 3 is 6. So it is 6 times u1. Here we have y times u2, which is negative 8 divided by 3 plus, then we have 16 divided by 3 plus 1 divided by 3. Well, this is 9 plus, that's 25. That's, no, actually, it's not true. It's 17 minus 8. That's 9. 9 over 3, that's 9 over 3, 3. That's 3 times u2. So it's 6 times u1 plus 3 times u2. 6 times u1, that is 4, 2, 4. 3 times u2, that's negative 2, 2, 1. We add those together, you get 2, 4, 5. So the projection of y onto w is equal to 2, 4, 5. I am a legend. And then UU transposed times y is equal to, since we know UU transposed is equal to the standard matrix for the projection, it's equal to the exact same thing. That's an important one to remember. So since UU transposed is equal to the projection of y onto onto the subspace spanned by the column vectors of w, then this is just equal to that. Good explanation, man. The orthogonal projection of y hat of y onto a subspace w can depend on the orthogonal basis w used to compute y hat. No. As long as w is the same, the projection will also be the same. If y is in a subspace, then the orthogonal projection of y, well, this makes sense. Because if you are part of a subspace and you want to get the closest point to yourself on that subspace, then it's just yourself. I love how I'm humanifying fucking points on a space. Ah, by God. I love how like IDM actually respects us and just, or IDM LA actually respects us and doesn't give us any new information on Friday, and then IDM just comes in with an extra lecture with more information. Okay. If the columns of an n-time P matrix U are orthonormal, then UUT Y is the... Oh, fuck! Oh, okay, that's
But
weird.
it's not like we start learning IDM before Monday. So
Yeah, okay, it's not like I started learning before Tuesday either.
yeah.
Okay, to be fair, actually, me and Jelle caught up a few days ago, or yesterday actually, and we actually did all the assignments as well. So we did catch up.
Was it
But
easy?
now we have...
Was it easy?
It's a lot of stuff to watch, and you have to understand a few processes.
Okay.
But we honestly don't know because we don't have the answers.
Yeah, fair.
Knowing IDM, they'll probably wait until like the exam is done before releasing the answer, though. Eggs. If the columns of an n times p matrix U are orthonormal, then UUT is the orthogonal projection of the vector y into the column space of U. This seems to make sense. It's a bunch of buzzwords. Wow, this is a lot of logic that I did not think of. Rive y is the sum of a vector y span in the span of U and a vector of y orthogonal to U. Okay, so let me first calculate y as in the y part that is in the span. So that is the orthogonal part. By the way, what they're saying here is we should calculate z is y hat minus y. Like we need to calculate both parts there. Or plus y, sorry. So I'm gonna use the formula to project u onto y. Sorry, y onto u, which is y times u over u times u times u.
Juist.
Sounds a lot more fucked when you say it that way, right? Minus 54 plus 20 divided by u squared, so that's 9 plus 25. 9 plus 25 is 34. This is negative 34. So this is just minus 1. So this is minus 1 times u. That's y span, so y span is equal to minus 1u. And we have y ort is equal to... Well, we know y is equal to... Oh, actually, let me write it in here first. Minus 3, 5. Oh, motherfucker forgets the minus sign. What a nerd. So we know y is equal to y span plus y ort. Therefore, y ort is equal to y minus y span. We know y, namely 18.4. And we subtract from that y span, which is minus 1u. So we add u onto this. So minus 3,5, which is equal to 15,9. Let's go. Okay. Consider the vectors y, u1, u2, and u3. Find the orthogonal projection of y onto the span. It's a lot of questions. Okay.
Most of them are like redundant once you've done the first part.
That's fair. Find the orthogonal projection. Okay, we're going to use the orthogonal projection formula thingy. So we are going to have y times u1, which is minus 22, plus 33, minus 6, minus 2. All that is equal to, that's minus 8. This is equal to 3.
times u1. Let's see, minus 33, minus 20, plus 3, minus 4. It's going to become minus 1. It's going to become 21. It's going to become 54. Minus 54 times u2. And u3 then. Okay, so that is minus 22 plus 10 plus 6 plus 6. So this is just literally equal to 0, right? Or, yeah. Yeah, this is equal to 0. Okay. Wait, I should still divide this by... Yeah, I should still divide this by u2 squared. Okay, that makes a lot more sense. So this should be divided by 18, which makes it minus 3. Okay, that makes a lot more sense. And y and u are actually orthonormal to each, or orthogonal to each other. So I don't have to worry about that. Therefore, the projection of y until span that thing is equal to 3 times u. So that is... Oh, fuck. Should have made a 4 by 1. So that is equal to, let's see, 3 times u1 equal to 6, negative 9, 6, 1, minus 3 times u2. This is going to become negative 3. This is going to become, let's see, minus 15. This is going to become, so minus 3 times minus 1 is plus 3, so that becomes 9. And minus 3 times 2 is minus 6, so this becomes minus 5. So the projection onto that will be minus 3, minus 15, 9, minus 5. Are these all orthogonal then? Well, yeah, because there's no option to say it doesn't exist, so they should be, but... So these two are orthogonal. 4, 3, minus 4, minus 3. These two are orthogonal. 6, negative 6. Yeah, these two are orthogonal as well. So, I think there's a problem then in my last calculation. So I'm going to multiply 3 by, or u3 by y again. See what happens. Then we get minus 22 plus 10 plus 6 plus 6. Is 0 divided by some non-negative number. That doesn't make any fucking sense, man. Okay, I'm gonna spam this until I actually get the right answer. What's wrong? They are orthogonal. Oh, wait. Okay, so the first one was actually 0 instead of 3, so I messed up there. Okay, but apart from that, I got it correct, so that's a W to me. Alright, we want to write y as the sum of the vector y in W and the vector z orthogonal to W. So that means it's just the vector that we just got, which is minus 9, minus 6, 3, minus 6. Oh, and the other vector, excuse me. So we know y is equal to y hat plus z. Therefore, z is equal to y minus y hat. Well, we know y, which is minus 11, minus 10, minus 3, minus 2. And we can subtract y hat from that, which is when we subtract negative 9, we add 9. Subtract negative 6, we add 6. We subtract 3. We subtract negative 6, we add 6.
-2, -4, -6, 4. There we go. Which point in W is closest to point Y? Well, obviously the projection, which is, because you know that's kind of the whole point of projections, which is -2, -4, oh, actually wrong one. So we want to have Y hat, which is -9, -6, or 3, -6. What is the distance from Y to W? Well, that's the difference of the. That's the magnitude of this thing. So actually, I still have it over here, so I can say square root of 4 plus 16 plus 36 plus 16. This becomes 20. This becomes 56, and this becomes 72, which is 6 square root 2. Find the best approximation to y by the vectors in the form blah blah blah. Use coefficients. Well, we already figured that out. That's 0 minus 3, 0. Which is what we get for the coefficients in this thing. Okay. Is all of this is going to be exactly
Yes.
this?
Yes.
Yes.
Honestly, just keep skipping until you reach one that isn't. If you've done one correct, you've done all of them correct.
Good point. Like, yeah, this is just exactly the same as the previous one. This one as well. Oh. Find the best approximation to y by the vectors of the form this thing. Well, that's not too hard. We can do that real quick. So
it is
we
not
have
exactly the same, so we'll do this one.
exactly that. So this is just y times v1 divided by v1 squared, or the distance of v1, the magnitude of v1, whatever. So we will have 17 plus 3 plus 10 plus 6 divided by 1 plus 9 plus 4 plus 4. Oh, we don't have to enter C1, V1, C2, V2 or something. We just have to enter the vector. Okay, cool. This times C1 or V1. This here becomes divided by 18. This here becomes 36. This is 2. Also, I made a typo. This should be V1. Okay. Again. Or positive 34 minus 2 minus 5 plus 9. This is equal to 36 divided by 4 plus 1 plus 9. What a coincidence. Is that exactly also 18? Is that still 2? So this is 2v2. 2v1 is equal to -2, 6, -4, 4. Then we add 2v2 on that. That becomes -6. This becomes 2. This becomes -2. This becomes 10. And then we throw that in here. -6, 2, -2, 10. I've got the hang of this, you could say. I can't wait for them to just give one of these to me with not, which is not orthogonal.
They won't. They'll only do that once you know Gram Schmidt.
Yeah, and then I have to make it orthogonal and then do the exact same fucking thing.
Yes.
If X is not in a subspace
And
W,
the best part is to create the orthogonal, you're doing the exact same thing as well.
yeah, it's practically the same, but then you're using different things.
Yeah. You're projecting onto you're removing projections until you get orthogonality for the basis, and once you have the basis, you're projecting onto that basis. It's
Exactly.
annoying.
Exactly.
Yeah.
Compute the distance from Y to the line through U and the origin. So that's just the distance between so we have the span of U, that becomes the line through U and the origin. And we want to project Y into the span and see what's the difference in that. Since these are only two vectors, I can do this one just to check if I've got it right. So let's see. We've got 4 minus 45. That becomes negative 41 divided by U squared, which is 25 plus 16, which is also 41. So the answer is negative 1 times U. So therefore, Y hat is equal to negative U, which is 4, 5, 4, 5. And then we calculate the Y. Let's see. So we have Y is equal to Y hat plus Z. Z is equal to Y minus Y hat. So we want negative 1, 9 minus 4, 5. So this becomes negative 5, 4. Fuck, that's the line, but we need to calculate the distance. So that is square root of 4 squared plus 5 squared. Ugh, so close, but yet so far. Calculate your orthogonal projection W onto the line, span by X. Okay. This is why we're doing knowledge percent and not green percent. Okay, now let's do that test your knowledge. This is actually interesting because this is like a recap of everything we've learned so far, at least that's what I think.
Mm-hmm.
So let's see if we can do this. Start test. So these are our eigenvectors of an n by n matrix corresponding to the distinct eigenvalues of these. Okay. The set does not contain a zero vector. It's not necessarily orthonormal or orthogonal, so I think it's linearly independent. Oh, it doesn't give you the fucking answer. A matrix A is called similar to B when there is an invertible matrix P such that this holds. Yeah, that's the definition. Suppose U is a matrix with orthonormal columns. Which are possible sizes for U? As we discussed before, 2 by 3 is not possible, 3 by 2 is possible, and 3 by 3 is possible. So only B and C. Yeah. Let A be a 2 by 2 matrix with complex eigenvalues. Then can we find a decomposition? Then we can find a decomposition, yes. Okay. How can we find a real invertible matrix? It's the real part, comma, the imaginary part of V, where V is an eigenvector of A corresponding to the eigenvalue A minus BI.
No, this set is linearly independent. Ignore this and start the Gram-Schmidt process anyways. Thank you, Graspel. But I've already done this one, but I'm not helping you because it's a test your knowledge.
Yeah, obviously. Consider an n by n matrix. Which statement is true? Let's see. I know the first one is false. It's either the second one or the third one, which follows from the first statement I did. I think the determinant of A transposed is a determinant of A, and the determinant of A inverse is 1 over the determinant of A. Let A be an M&M matrix, let lambda be an eigenvalue of A, which in the following statements about the eigenspace is true. It's equal to the null space of A minus lambda I. Easy. Consider a matrix A with a determinant of 5, and consider matrix B which is constructed by multiplying the second row of A by 2. What is the determinant of matrix B? 10. Because when you multiply a row by a scalar, you have to multiply the determinant by a scalar as well. Save answer. In Rn, what is the... These are just all like questions from their repository. I have done all of these before. What is the orthogonal space to Rn? Well, only the zero space. Which of the following statements is correct? Hello. Which of the following statements is correct? An n by n matrix with n distinct eigenvalues is diagonalizable, a diagonalizable n by n matrix and n by n eigenvalues, and both of them are or both of them are correct. I think they're both correct. Let A be an M matrix, V a vector in VR, and lambda a scalar. Then we have this is an eigenvector. Oh yeah. Vector V is an eigenvector of A, and lambda is an eigenvalue of A, unless V is equal to 0. Yeah, this is correct. So the eigenvector cannot be 0 because then this would hold for everything, because a 0 vector times A is always equal to a 0 vector times lambda. Okay, separate your eigenvalues by commas. We've seen before that this is that on a triangular or diagonal matrix, the eigenvalues are on the diagonal. So it's A, B, C. Is the following statement true or false? U is an orthogonal 3x3 matrix, which means it has an orthonormal column set. And T is the linear, well, yeah, we've had this before. But T is the linear transformation and with standard matrix U, then T preserves length and orthogonality. Yes, multiplying by the standard matrix of an orthogonal matrix, then that preserves length and orthogonality. Characteristic equation of matrix is given by the determinant of A minus lambda I is equal to 0. The eigenvalues of matrix A are equal to the entries on the main diagonal of A. Only if it is a triangular or diagonalized matrix. I wish the test would go this well. Let this be a basis for a subspace H if X is a vector in H with XB is equal to C1, C2, C3. What does this imply? The vector X can be computed by this thing. Yes, that is correct. What is the second eigenvalue in this matrix? Negative 6.5 minus 2.0 I. The O looks abnormally big there. Which of the following statements is correct? In S is a set of U, orthogonal set of non-zero vectors, then S is linearly independent. This is correct, but not every linearly independent set of non-zero vectors is always orthogonal. So only one. Let A be an n by n matrix. The orthogonal complement of the column space is equal to the transpose of the null space. Let A be a square matrix. By the way, if you at any point have any questions about anything I'm saying or like that I'm filling in, please ask. I am going really fast now, but that's because these are just test yourselves. Either that or just do the test yourself. Okay. Let A be a square matrix. Let lambda be an eigenvalue of A. Which of the following inequalities hold? The geometric multiplicity is less than or equal to the algebraic multiplicity. I think this one, but I'm not exactly sure. Does this include everything? No, it doesn't. I'm just gonna go with the top one. Similar matrices have the same eigenvalue and the same eigenvectors. I don't know, I still have to study the properties of similarity, but I guess it's true. Let lambda 1 be an eigenvalue of the square matrix. The geometric multiplicity is equal to the number of vectors lambda minus lambda 1 in the characteristic polynomial. I know for sure it's not the number of distinct eigenvectors of A corresponding to the eigenvalue lambda. I think it's the dimension of the eigenspace. What's the algebraic multiplicity? That's 2 because it gets it's squared, so it's in there twice. Which of the following statements is false? This is true. This is true. This is false, and this is true. So this becomes a to the power of n, or k to the power of n times the determinant of a, because you multiply every row by k. So then you multiply by k n times, that becomes k to the power n. Which of the following eigenvector corresponds to eigenvalue 2? Well, then you just swap the plus and minus signs around. So that is this one. An n by n matrix is diagonalizable if and only if it has an linearly independent set of n eigenvalues, a diagonal matrix, or n distinct eigenvalues. I think this one. The column space of A plus the null space of A is equal to... So let's see. M by N. I think it's M. Suppose L is a line spanned by the non-zero vector U, and Y is another vector in the same thing. Then the orthogonal projection of Y onto L is a vector. Well, yeah, because Y is equal to the span of, or Y is in the span of L, so it's parallel to U. Every diagonal matrix D is an orthogonal matrix. No, because this would mean that all the diagonals ever would only be 1 or minus 1, because an orthogonal matrix has orthonormal columns, and therefore the only values in there could be -1 or 1. So this is false. If Z is orthogonal to both U1 and U2, and if W is the span of U1 and U2, then Z must be in the orthogonal complement of W. Correct by a theorem that we saw before. Let A be an n by n matrix. Let lambda be the eigenvalue of A, which corresponds to eigenspace lambda E of lambda. Which of the following statements is true? Well, 0 is an element of every subspace. So the vector 0 is not an eigenvector of A. But it is an element of E. Of the eigenspace of that lambda. I want to submit my test. Oh!
Dang, boy!
Damn!
I got 25 out of 30. Impressive.
Sit, kid! Sit the fuck down!
CYS sign, son.
Taking a screenshot, posting it in Uriel's or in Yuri's general chalkboard.
Were the people happy after it?
Yeah, for the people who were like, ooh, they're actually doing some stuff in there. And this is where we spam the sunglasses emoji. Whew. Okay, I'm gonna take a quick sip because I'm talking so much. My throat is starting to hurt, and we're only 4.5 hours in. Only, he says. Take care of yourself, kids.
Important.
Important. Self-care is a human right.
What?
I don't know. See how you answered each question. 4 questions wrong. I posted my results somewhere, and I said I was doing an LA marathon, and he was like, Los Angeles?
Yes.
Guys, we're going to Los Angeles, holy shit. Okay.
I am going to America.
They end up in Holland instead, SMH. Okay, so this is one I wasn't certain about, so an n by n matrix with n distinct eigenvalues is diagonalizable, which makes sense if you have like a diagonal matrix which has like it's literally a diagonal matrix which is 5 times the number 3, then it doesn't have 5 distinct eigenvalues because they're all 3. Sayonara. Welcome back. Similar matrices. Oh, okay. This was because I didn't know yet what similar matrices do. And they do have the same eigenvalues, but not the same eigenvectors. Okay. It's diagonalizable if and only if they have a linearly independent set of n eigenvectors. Oh yeah, because if this isn't the case, you stop diagonalizing. Yeah, I remember, because then you can't construct P. And if they're not linearly independent, it's not invertible. Okay. And yeah, I just had this one wrong.
Epic.
Epic gamer. Whew. All right. And the rest we have been gaming.
Certainly.
Okay, Graspel.
No Grasplay.
Grasplay, you're right. 1, 2, 3. Oh, 3 to go. So now we have the Gram-Schmidt process, the least squares problem, and symmetric matrices. That's not that bad.
Nah.
Okay, cool. So let's try the Gram-Schmidt process.
Just the same fucking things a billion times.
Hell yeah. So Wow, I almost got a 9 on that thing. I expect the thing won't be the same, but it does feel good. Okay, cool. Lecture slide. The Gram-Schmidt process. To perform an orthogonal projection of a vector y onto the subspace W, you need an orthogonal basis of W. An orthogonal basis of Rn. Performing an orthogonal projection using non-orthogonal basis results in. Okay. So if you don't have an orthogonal projection and you try to do it anyways, you will get a y which is on W, which makes sense because y is a linear combination of the vectors of W, like the vectors of the basis of W, but just z won't be on the orthogonal complement of W. Dude, I'm spitting out fancy words like it's no tomorrow. Holy hell. Small me would have been so amazed by everything I'm saying. Okay. For two vectors. So you pick one, that's your B1. You pick the second one, that's like B2 minus the projection of B2 onto W. Wait, this is really fucking easy. And I do that a bunch.
Yep.
Wow, okay. Interesting. Is anything else discussed in this thing?
Nope.
Nope.
Yeah, least squares, but it's Gram-Schmidt, but then big brain.
It's at least square, but that's Gram-Schmidt, but then with a PP.
Sure.
Sure, I'll take it. Pre-lecture exercises. Oh, there's only two of them. Let U until UP be a basis for a subspace W of Rn, and let Y be a vector in Rn. Then Y equals Y hat plus Z, where Y is in W and Z is in W complement. No, because this is not an orthogonal basis. False. Nerd. Nerd. Fuck. I have to compute some shit. Ugh. Okay. God, I have to actually put in work. That's annoying. Let's see. Gib mir eine Sekunde. Mein Deutsch ist ganz sehr gut. Alright. Je suis ready to do not Gram-Schmidt, this is just production shit. So we have x1 times y1, which is 2, divided by x1 times x1, which is 6, which is 1 over 3, times x1. Then we have this, which is 1, divided by, then we have this, which is also 3, or actually, no, this is 1 over 6, x2. And then we have 1/3 times x1, which is 2 over 3, negative 1 over 3, negative 1 over 3. And then we have 1 over 6 times x2, which is 5/6, negative 1/6, and let's see. So I subtract a third, or I subtract negative. No, I add negative a third. So I subtract a third. So this becomes negative 2 over 3. Let's see, is that correct? Minus 2 times 1/6. Minus, yeah, okay, that makes sense. So projection is 5 over 6, minus 1 over 6, minus 2 over 3. Is the vector which we just computed an element of W? Oh, we have computed a vector y hat, or y tilde, which is probably not the orthogonal projection of y into W. Let us verify this. Is this an element of W? Well, I mean, it's a linear combination of this thing, so yes. compute the difference between y, or the y minus this thing. So we have the original y, which is 1, 0, 0. And from that we subtract this. This becomes 1/6. This becomes 1/6, and this becomes 2/3. Is the difference orthogonal to W? Fuck. Is this thing orthogonal to W? But we have an orthogonal basis, right? Is this not exactly what we were doing before? Oh! Non-orthogonal. No, it's not. Als niks helpt, lees dan de vraag. Back to lessons.
Okay, Jure, can you just like go to your word thing?
Hmm?
Can you just click on a cell in your word thing? And just imagine I was trying to type B0, you know, one of those things. But I kept my finger on the shift for long. Can you type B0 for me with your finger on the shift?
Oh, that's... Huh? What the fuck?
Huh?
Oh! I keep pressing control instead of shift. Run! I sincerely feel for anybody who has to deal with all the shit we do. Can I
don't.
undo
Fuck
all
'em.
of... Hmm?
I don't fuck them.
That's true. They're here by their choice.
Exactly.
And this is probably helping them or something.
Or something like that.
Shout out to my homies in the chat. We've still got 1, 2, 3, 4, 5. Actually, 2 guys muted them or deafened themselves. So we have 1, 2, 3, 4 people other than me and Yellow.
Nice.
Nice. Strijders. Fucking strijders. If everybody heard Dutch, can I then continue in Dutch? No, I'm not doing that.
We've got
Ja,
YouTube
maar
people.
wel.
No, I'm not continuing in Dutch. Het orthogonale complement. Dude, I would fucking cry.
Kaaskop dab erop.
Kaaskop dab erop. The Gram-Schmidt process produces... Imagine this is like the best your university has to offer. The Gram-Schmidt process produces from a linearly independent set an orthogonal set with the property that each k, the vectors, span the same subspace that is spanned by... No, that's not true. Oh, wait. No, that depends on your choice for like B1 and B2, right?
Orthogonal set. With the property each k, the vectors k spans the same subspace. That is correct, I think.
Yeah, but it depends which ones you pick.
No, it doesn't, because the Gram-Schmidt process takes them in, puts them down in the same order.
Yeah, okay, that's fair. Again.
Just do it again.
Okay, that is pretty funny. Yeah, just
do it again.
divided by the distance. That's like not hard. What is the formula needed to obtain V3? V3 is x3 minus I genuinely don't know. Where is... I forgot if it was minus or plus.
Minus.
Okay, yeah, so you have the number minus the projections.
Yeah, which makes sense if you think about it. I like to rationalize it for myself. So what you take is you have a number, you have like a number, and you want to remove all the other, like, you want to remove the projection onto the basis, on every basis you already have, so that all you're left with is something orthogonal to all of them. Because if you have a vector and remove the projection from that vector onto a new vector, the remaining vector is orthogonal to the vector you projected on.
Yes.
Okay, I'm gonna show it in fucking MS Paint, and then you're gonna see it, and then you're gonna be like, yes. So
I can't
you've got this, yes.
I feel very bad for the people who cannot watch this at home, but also completely not. Yes.
So you've got this one, and then the bitch should have been here. You got this vector,
Yep.
and say you've got this vector. You want to make from this one
Yep.
a something orthogonal to this one.
Yep.
Why shit? They're already orthogonal.
I was about to say that's like really easy.
So say we've got, I'm gonna be fucking basic. This one. So you want to know
Yep.
how this how this orthogonal is. So you do is you project it onto here. You know, I'm gonna just draw this one a bit longer so that it's actually visible.
Yep.
So what you do is you project this onto here.
Yep.
And remove that from this one. So this one minus.
Oh yeah, I see it.
Yeah, so it's this vector.
Does that mean that
minus this vector, and then you keep this vector, which is orthogonal.
But does that mean that when you project onto a vector that they're always when you project onto a one vector into another vector,
yeah,
is that always like an angle of 90 degrees?
But no, but like the thing is, you're practically removing everything that has to do with this vector from this vector. So when you're projecting, this is always 90 degrees. That's what a projection means. A projection is the shortest distance, and you know shortest distance.
Oh yeah, that's always 90 degrees.
Always 90 degrees. Yeah.
Okay.
So if you take this, then it's not 90 degrees. But if you take the shortest distance, then yes.
Okay, makes sense. Cool.
And so you did the same in. So if you have like a three-dimensional matrix, which would imagine this is somewhere up or something. Then first you remove everything to do with this one matrix, and then you remove everything to do with this one matrix, and then like the formula makes sense.
Yeah.
So you take the original matrix, then you remove the projection from the original matrix onto the first matrix, then you remove the projection from the original matrix on the second Gram-Schmidt matrix, etc.
All right. Use the Gram-Schmidt process to retain an orthogonal basis. Okay, that's like literally the thing we're doing. I am saying b1 is x1. Then I will use b2 equals x2 minus b1 x2 divided by b1 b1 times x. This should be x1 times x1. This doesn't seem very pretty, and I think it's wrong. It's b2. Yeah, okay. So I swapped around variables. That's my bad. So it's x2 minus Oh, I'm swapping around b1, b and v. So okay, v1 is equal to b1. V2 is equal to b2 minus b1 times v1 divided by v1 times v1 times v1.
I could show you the way I do it. I don't know if you're interested. I've done
Not
like
really,
7
but I
of them just
appreciate
now.
it. Not really, but I appreciate the effort.
Okay.
And then we have v. I'm actually gonna not put this in here. This is like a terrible place to put this. Then we have v3 is equal to b3 minus b2 times v2 divided by v2 times v2 times v2. I should stop using the same symbol for both of these things, but it's so easy, man. And then I do this minus b1 times v1 divided by v1 times v1 times v1. So v1 is v1. So I can say v1 is equal to x, or 4, 6, minus 6, 0. I can say v2 is equal to b2 minus, and I can say b2 times v1, or b1 times v1. That's not correct, is it? Yeah, is what I put down for this one correct?
Let me have a look.
It should be b2 times v1, right?
No, looks fine to me.
But if
Wait, this is b1 or what?
Hmm?
The fuck are you doing?
Yeah, this should be b2.
Uh,
This should be b3, and this should be b3.
Oh, yeah, okay. In my head, the B and the V were turned around. And I was like, eh?
Yeah, that's fair, but here it's asked for v1, v2, v3.
Oh, yeah, fine enough.
Okay, so we have b2 times v1. So because v1 is b1, I can just say these two. So we have, this is negative 8 plus 36 plus 60. So that means this is 96 minus 8 is equal to 88 divided by v1 squared. v1 squared is equal to b1 squared. By the way, the b's here actually are x's here, but I'm just using the formula in the way I remember it. So it's 88 minus, or divided by, it's 24 plus 36 plus 36. 36 plus 36 is equal to 72. 72 plus 24 is equal to 96. I kind of don't feel like this is correct. At the same time, it would be like, it wouldn't be too much for them to apply such annoying values. Let me see, so we had minus 8 plus 36 plus 60. Yeah, this is just 36 plus 60. Okay, fair. So this is actually equal to, well, I'm just going to keep it like this. Times v1. Or actually this is equal to the second vector minus this number times the first vector. What are these fucking numbers though, man? This is like really shitty to calculate with. Okay, so we have x2 is equal to this. I'm going to simplify this. I'm going to divide by 8. This will become 11. And this is going to divide by 8. This will become 12. So then we subtract 11 12 times that. So we have minus 44 12 minus 66 12 minus, or plus 66 12, and well, this is just the same. Is there a neat way to simplify this? Probably not. Wait, actually this is 5.5. So this is then minus 4.5. So this is 9 minus 5.5, which is just 4.5. It should be actually it should be 3.5. Yeah, okay. And then I do 36. That's 3, which leaves me with leaves me with 8. So that is 2/3. That's minus 5 2/3. Okay, so this is the second column, which is at least a little bit less like gnarly than I thought it would be. Okay, and then the third column is this column minus, let me see, B3 times V2. So we have B3 times V2, that's 5 to 3. I know I fucked up my calculation somewhere, man, just show me. It was 88 over 88 instead of 88 over 96. Okay, cool. You live and you learn. Okay. This is a lot easier. I wish they gave me this one instead of the next one, or the previous one. Alright. So, we have B1 is equal to this thing. V2 is equal to B2 minus B2 times V1 divided by V1 times V1 times V1. I should really be putting this down here. So we have B2 at first, which is minus 5 minus 2, 0. And I do this minus B2 times V1, which is minus 10. Okay. Divided by, well, this is just 10. So this is going to be minus 1 times V1. So this is just equal to this, the lefting minus, the righting minus the lefting. Not true, because you already subtracted, so you add it. So this becomes 3, and this becomes minus 4. So then we create the set of the two 3 by 1 vectors of 2, 0, minus 4, comma, minus 3, minus 2, minus 4.
Oh no. Fucking, the correct answer is 73 fucking 86th, 100 or 102, 137th.
Is that the correct answer according to Graspel as well?
According to Graspel?
What the fuck? Okay.
Yes.
I messed this up somewhere. I know for a fact. Oh wait, are they linearly independent? They are linearly independent. Cool. So I know for a fact that the first thing is correct. What about the second thing? It's B2 minus B2 times V1. So minus, let's see, B2 times V1. That's like minus 6. Fuck, this should not be that. This is a 0, this is a 2, this is a 5. So B2 minus, then we have B2 times V1, that's negative 10. Yeah, divided by 2 squared plus 4 squared, which is actually 20. Yeah, that makes sense. Okay, so this is actually minus a half. And we subtract minus a half, so we add 1/2 of this to that. So we add 1 here. Shit. We add 1 here, and we add minus 2 there. So it's actually comma minus 4, minus 2, minus 2. There we go. Ugh.
I guess you are a little punk.
Okay, same thing. Delete this. Recall the formula. V2 is equal to B2 minus V2 times B1 divided by b2 times v1 divided by v1 times v1 times v1. So therefore, the first one will be -2, -4, -6, 4. The second one will be -2, 0, 4, -4. Then we that's the b2. Then we multiply these together with a dot product. That becomes 4 minus 24 minus 16, which becomes 4 minus 40, which is 36, divided by v1 squared, which is 4 plus 16 plus 36 plus 4, or plus 16. So this becomes 40. This becomes 32, which is 72, which is 1 over 2. So we add a half times the first vector to the second vector. We subtract a half times first vector from the second vector. So we subtract 1, which is adding 1. We subtract -2, which is adding 2. We subtract -3, which is adding 3. And we subtract 2, which is subtracting 2. Which leaves us with the vector -2, with the basis -2, -4, -6, 4, comma, -1, 2, 7, -6. Okay, this is a process that you really have to get the hang of. I'm getting it. I see what it's doing. And I probably fucked up my 1/2 here. The original thing, that's 4 minus 20. It's minus 1/2. Because the top thing is minus minus 36. Okay, let's try that again. So we subtract -1/2, so we add a half. Adding a half of -2 is adding -1, subtracting 1. Adding half of -4 is -2. Adding half of -6 is -3. Adding half of 4 is 2. So then this thing instead of that becomes -3, -2, 1, -2. There we go. Always watch your minus signs, kids.
That sounds like contraception or something.
Yep. Only 3 to go. 2.5 realistically. Okay. Use the Gram-Schmidt process for this. Okay. So we have V1 is equal to B1, V2 is equal to B2 minus B2 times V1 divided by V1 times V1 times V1. V3 is equal to B3 minus B3 times V2 divided by V2 times V2 times V2 minus B3 times V1 divided by V1 times V1 times V1. I'm starting to at least get the hang of memorizing the formula, let me tell you that much.
Somewhere I understand that.
You do? Pog. Okay. So then we take this is B1, so let me write down B2, multiply that by the first one, that becomes -6, minus 12, minus 24, divided by square of V1, which is, or the, yep, so V1 squared, which is 4 plus 4 plus 16, which is 24. Keep in mind, V1 squared is 24. So this becomes -1, so we add -1 times the left one to the right one. Adding that means subtracting 2 from -3, which becomes -5, -5, -7. Then we can do the same thing with B3, which becomes -1, -1, -5. Then we do V. I'm first going to start by subtracting the V1 thing. So we can start with -2, -2, -20. That is -24 divided by 24, which we already know from before, which is -1. So we subtract -1, which means we add +1. So I add the leftmost one to the rightmost one, which makes it 1, 1, -1. Should keep in mind that this is still -1, -1, -5. And then I multiply B3 by V2, which is 1 plus 1 plus 35, or actually 5 plus 5, 35, which is 45 divided by V2 squared. V2 is 557, that's 25 plus 25 plus 49. That's like 99. Which means I've probably made a mistake somewhere. Hmm. Oh. I think what I've done so far is correct though. So this becomes 5 plus 5 plus 35, which is 45, yep. And then I have to do V2 times V2, which is 25 plus 25 plus 49. That also makes sense. Then I probably made some kind of miscalculation within my V2 calculation. So let me have a look. It was B2, which is -3, -3, -3, minus B2 times V1. B2 times V1 is the same as B2 times B1, which is equal to -6 minus 6 minus 16, or -12, which is -24. So the factor is -24, which means I add the left one to the right one, which explains my issue. So this becomes -1, this becomes -1, and this becomes 1. Okay, so then that makes a lot more sense. Then for my B3, here's my original vector. And then I calculate the B3 times V2, which becomes 1 plus 1 minus 5,
Yo,
which is...
Please never say B3 again, I'm getting flashbacks.
By God, do I agree. Okay. Unfortunately for yellow, so we have B3 times... B3 times V2, so this is indeed 1 plus 1 minus 5, so this is correct. And then we divide that by V2 squared, which is also 3. So this we subtract by -1, so we add 1. And therefore we add 1 times V2 to the intermediate product here, which becomes 0, 0, 0. I'm not sure if this can be correct. I'm not sure if it is correct. But, like, perhaps. -1, -1, 1. Zero, zero, zero.
Whoa. What are you creating here?
An orthogonal basis.
A basis. What's the main point of a basis? That they're linearly independent. What do you get if you could take 0 times the first one times plus 0 times the second one?
Yeah, okay, that makes sense. So I made a mistake
That's
somewhere.
not linear independent. No. You're right. It's a two-dimensional basis. Remove that comma, press enter, you're done.
Huh.
Yeah. The original thing isn't linearly independent.
Oh. Okay, I see. So you can either check if it's linearly independent beforehand and then just remove the one that's not.
Yeah.
Which, to be
so
fair.
basically, you calculate this for the column space of your
Hmm?
matrix. So basically, you calculate your basis based on the column space, then, or am I dumb?
Well, technically there is no matrix here. You just have a I mean, technically you could see it as a matrix with a column space, but
Yeah, the
you
span
just
of
go
three.
from one basis to another basis. There's no matrices involved here.
Yeah,
Alright,
I get what you're saying. Like the span of a matrix is equal to the column space, or the span of three vectors is equal to the column space of a matrix that would be that vector.
Ah, yeah, okay, I see. Yeah, okay. Thank you.
Okay. Next one. Woo! It's green, bitches. The Gram-Schmidt algorithm, blah blah blah. Base for self-base W of an orthogonal basis of W for W. When performing an algorithm, we start by finding a base for W. It's not necessarily a basis, since it could be linearly dependent. Yeah, that's what we just found out. Give me 1 second.
I'm doing some quick maths here, and is it correct? I'm awesome.
Okay. In this exercise, we investigate what happens if we skip step finding a basis. We just apply the process to a linearly independent set. Well, I just did this! Holy hell. I just
Yeah,
did this.
this is the least fun of all of them. I recommend skipping them.
Yeah. Cool.
It sucks.
Find an orthogonal basis. This one's linearly dependent. Or linearly independent. So we have v1 is b1, v2 is b2 minus b2 times v1 divided by v1 times v1 times v1. b3 or v3 is equal to b3 minus v3 times v1 divided by v1 times v1 times v1 minus b3 times v2 divided by v2 times v2 times v2. I understand if it's really confusing if I keep saying times instead of dot and times, but this makes it more more legit, like and then more easy for me to remember. More legit. My girlfriend's mom is being scammed.
Lule.
Lule.
Oh my god. Why is she being scammed?
Hmm?
Why is she being scammed? Just don't get scammed.
She got a text message saying, "Hey, if you don't pay this in like 4 days, we are going to come to your house and pick up your shit."
Epic. Oh, I need to Gram-Schmidt.
Okay. Consider linear. Am I still recording, by the way? Yep. 6 hours and 40 minutes in. Find the orthogonal bases. Okay. So we have x1 is equal to this. x2 is equal to the original vector minus these two times each other. That is 9 divided by the by v1 squared, which is also 9. So this is just 1. Note to self, v1 squared is 1. So then we subtract 1 times this from that, which means we add 2, we subtract 2, we subtract 1. Um, okay, so we subtracted 1 times v1. Yep. And then for c1, we write down c1. And we calculate what is b3 times v2 divided by v2 squared. So that is 6 plus 3 plus 6. That is 15 divided by 9 plus 9 plus 9 divided by 36. That doesn't seem to make a lot of sense. I'm dividing by the wrong thing. It should be divided by 9. Because that's 2 squared plus 1 squared plus 2 squared. Does that make sense? Also, this doesn't make much sense either. This should be 9. Yeah, because v1 squared is... Yeah, okay. So I wrote that down incorrectly. So, let's see. This is 6 plus 6 minus 3. 6 plus 6 minus 3 is 9. So we subtract 1 times minus 1 v2. And then for the last one, we do v3 times v1. So that becomes minus 6 plus 3. That's equal to minus 9 divided by v1 squared. We know that's 9, so we have minus 1. We subtract minus 1 times v, so we add 1 times v. Or v1, sorry. So we do these steps. So we subtract 1 times this one, which is 1 minus 4, 1. And then we add 1 of the right one, which turns minus 1, minus 2, 2. So then this becomes the orthogonal basis of the vector minus 2, 2, 1, comma, 2, 1, 2, comma, minus 1, minus 2, 2. And it actually seems pretty logical that these three are orthogonal, so let's see if it's correct. It is correct. Haha! Motherfucker. The set is linearly independent. This is a linearly independent set of 3 vectors in R cubed. This implies that it is a basis of R3. So it's just R3, so it's just orthogonal basis of everything. Okay, that is pretty funny.
Pretty fucking funny.
Find an orthogonal basis for the column space of this thing. Well, let me first do a little check-in, just a little something. Is this thing linearly independent? The sure as fuck seems to be. Yeah, it's linearly independent. I'm not even gonna check. Well, okay, I might check. So I add this one to that one. This becomes 0. This becomes 2. I add this. Subtract this one from that one. This becomes 0. This becomes 0. This becomes 1. This becomes 1. Or this becomes 0. This becomes 1. This becomes 0. This becomes 1. They are linearly independent. So that means we have 3 vectors. V1 is equal to 6 minus 6, 6. V2 is minus 8 minus 2, 0. And V3 is 4, 6 minus 4. So we can say V1 is equal to B1. V2 is equal to B2 minus B2 times V1 divided by V1 times V1 times V1 minus, and V3 is equal to B3 minus B3 times V1 divided by V1 times V1 times V1 minus V3 times V2 divided by V2 times V2 times V2. I can't wait to have to do this with a 3-dimensional basis. It's gonna be fun. Now I'm gonna see if this actually works. So we have a 3-dimensional so we have a 3-dimensional space with 3 dimensions and 3 linearly independent vectors. Therefore, this thing spans the entirety of R cubed. Therefore, we can just say the standard basis is Why does it not work? Whatever. I'll do it the normal way. So we have V1 is V1, which is 6 minus 6, 6. V2 is B2, which is minus 8 minus 2, 0. Minus B2 times V1, which is minus 48 plus 12, which is minus 36. And then we divide that by V1 times V1, which is 36 plus 36, which is minus 1 over 3. V1 cubed or squared is equal to 36 times 3. So then we subtract a third of the leftmost one of the rightmost one, which is the same as adding a third of the leftmost one. So we add 2 minus 2, 2. So this gets 6 minus 4, 2. Okay, then for the next one, we have the original one, which is 4, 6 minus 4. From there on, we... Excuse me. From there on, we... Yeah, okay, I'm going to start with the V1 one. So I'm going to say 24 minus 36 minus 24, which is equal to minus 36, divided by 36 times 3, which is minus 1/3. We subtract 1/3, we add 1/3. Or we subtract negative 1/3, so we add 1/3 V1. Okay, for the second one, we've got minus 24 minus 24 minus 8. So we have minus 48 minus 8 is equal to minus 56. Does anyone know what time we have the calculus or the linear algebra exam on Monday?
2 o'clock or 2 or 2:30. Depends on your batch.
Alright, and how long does it take again? 1.5 hours?
Yeah, I guess.
Okay. Okay. Then we divide this by the V2 squared, which is 36 plus 16 plus 4, which is equal to the same number. So we subtract one times v2, so we add 1 times v2 plus 1 v2. So I'm going to start by adding a third v1, which is the leftmost thing, which becomes adding a third of v1, same as adding 2 here, subtracting 2 here, adding 2 here, and then we add 1 times v2, so this becomes 0, this becomes 0, this becomes 0. It is not... How come it's linearly independent then? Did I fuck up my... Huh. What the fuck? Okay, that also explains why it didn't count that one. 6 minus 6, 6. That is so curious. I'm not going to skip this one. I'm going to say... Huh, so I fucked up during my step of checking if it's linearly independent. How did I fuck that up? So if I add this one to the top and bottom, or let's add this one to the top to this one, so then we get this, and this becomes minus 2, and then I subtract this from the top, so this becomes this becomes... I see. Okay. Find find an orthonormal basis for W.
Yes.
Okay. So first we do the Gram-Schmidt. So we have V1 is B1 and V2 is B2 minus V2. B2 times V1 divided by V1 times V1 times V1. And then we have to normalize the vectors, which isn't too hard. So then we have minus 4, minus 1, which is minus 6, divided by 3. That becomes minus 2. We subtract minus 2. That becomes we add 2. We add 2 times vector 1, which becomes negative 2, 1, 1. Then we have to find the orthonormal basis instead of the orthogonal basis. So what we do then is we create the set of this thing, which is, let's see, this is the square root of 3, so 1 over square root of 3, 1 over square root of 3, 1 over square root of 3, comma, and then we have this one, which is, let's see, that's 4, 5, 6, so this is minus 2 over 2 times the square root of 3, no, that's actually not 2, minus 2 divided by the square root of 6, 1 divided by the square root of 6, and 1 divided by the square root of 6. Okay, is that correct? We have 4, 5, 6, and we have 3, 3, 3. This is indeed the least fun one out of all of them. Suppose you apply the Gram-Schmidt process to a set of vectors that are linear dependent. Funny, we did that. You will obtain a zero vector as one of the vectors. If is an orthogonal basis, then multiplying, well, yes, we have done this before. We have literally answered this question before. The general least square problem is to find a vector x that makes ax as close as possible to b. Yes. Okay. Alright, kings, let's have a look. So we have this. I can't believe I'm happy I'm going back to just normal matrix multiplication. AU, that is 5 minus 1. This becomes negative 4 plus 15, which is 11. This becomes negative 1 minus 10, which is minus 11. And this becomes negative 4 plus 15, which is 11 again. So I can say that AU is equal to 11 minus 11, 11. Oh, actually I can check that. And then we do the same for AV. Alright, AV is this minus 2, so then we get minus 8 plus 15 is minus 7. Is that correct? Minus 8 plus 15. Yeah, okay. Then we get minus 2, this is minus 12, and this is the same again, minus 7. Minus 7, minus 12, minus 7. Is this actually minus 7 though? No, it's positive 7. Because this is minus 8 and this is positive 15. Okay, and then we have to look at the least squares solution of AX is equal to B. Then we have to look at which one of the two is closer to the other one. So this is like 0, 0 apart, 2 apart, 6 apart, and this is 4 apart, 3 apart, 2 apart. That's 4, 3, 2, and 0, 6, 4. Wait, is that correct? So let's see, that was 0 apart, 2 apart, 6 apart. So the least square, so we want to minimize the squares of these numbers. So this is 16 plus 9 plus 4, that is 29, and this is 36 plus 4, this is 40. So UV is closer to the least square solution, so U cannot be the least square solution. I think I calculated it the wrong way. Oh no, actually I did it right. Find the orthogonal projection of B onto column space of A and find the least square solution of AX is equal to B. Aren't these the same? Ugh, after this question we only have 2 more to go. Alright. So...
2 more?
Hmm?
Is this least squares or Gram-Schmidt?
Gram-Schmidt?
Ah, okay.
Yeah, so we have least squares and... like we have to...
Orthogonality and diagonality.
Symmetric matrices, yeah.
That one.
Almost there.
Yeah, fucking strijders. You know you're doing a good marathon when you've ate during the marathon and you're already getting hungry again.
Yep.
Yeah. The distance is the least square error, least square solution. Okay. So once I have the projection, I need to calculate for which x AX is equal to B. Okay, that makes sense. So first I'm going to project B onto column space of A. So I have to... Wait, so projecting B onto column space of A means... God, I did the Gram-Schmidt too much. So that is B minus V1 times B divided by V1. Actually, no, this is not true. This is the projection of
v onto b1 plus v2 times v divided by v2 times v2 times v2 plus v3 times v divided by v3 times v3 times v3. I think that makes sense, yeah. So then I have to calculate v1 times v, that's 36, divided by v1 squared, that is 24 plus 36 plus 2. No, that's not 24, it's 16 plus 36 plus 2. So that is 18 plus 36, that is 1 divided by 1.5, which means this is 2 over 3. 2 over 3 v1 plus, okay, now for the second one we have 0 times v2. You love to see it. And then for the third one we have 9 divided by 2 plus 25 is equal to 27, that's 1/3. So 1 over 3 times v3. So the projection is equal to 2/3 v1 plus 1/3 v3, which is equal to 8 over 3, 2 over 3, 12 over 3, and 2 over 3, plus 1 over 3, 1 over 3, 0, minus 5 over 3. Add these together would give you 9, 1, or 9 over 3, 3 over 3, 12 over 3, and minus 3 over 3, which is minus 1. So the b hat is equal to b hat, 3. yay! B hat, woo! Equal to this. And now we know that, now we want to know that for 1, so we want to know for which a is ax equal to b. So that means we can calculate the inverse of a. No, I don't think that will work. Either way, we can just check. Okay, so 4, 1, 6, 1, 0, minus 5, 1, minus 1, 1, 1, 0, minus 5 is equal to this thing. So then we have to row reduce. Subtract this one from, or subtract this one from that one. So then this becomes 0. Subtracting minus 1 is the same as adding 1, so this becomes 4. Subtracting minus 5 is the same as adding 5, this becomes 6. Subtracting minus 1 is the same as adding 1, this becomes 2. I'm going to divide this all by 2. Okay, I'm going to multiply this row by 4, this becomes 4, this becomes 4, this becomes 20, this becomes 4. I'm going to subtract the top one by the bottom one, or subtract the top one from the bottom one. This becomes 0, this becomes minus 4, this becomes minus 21, this becomes minus 7. I'm going to multiply this row by 2, this becomes 4, this becomes 6, this becomes 2. I'm going to subtract this row from the bottom row. So then we subtract minus 4 times adding 4, we subtract 6, which is, this becomes 27, we subtract 2, it becomes minus 9. Therefore this is equal to 3, 1. And I subtract 2 times this row from this row, which means this becomes 0. Therefore this one is 0. Okay. Then this one can become 0 as well. Then I can turn this into a 3. Become 3 is 2. 1 here is equal to 2 over 3. And 1 here is equal to 1 over 3.
I subtract this one from the top one. So this becomes 0 and this becomes 2 2/3. Then I subtract 0 times 4 times this one from the top one. 4 times 2 is 8. 8 over 3 is 2 over 3. This becomes 0. And therefore the system is consistent with its answers 2 over 3, 0, 1 over 3. Which is also the solution for x hat. Whew! Back to lessons. Every time I read TU Delft, I see FUD. What was it again? Fear, uncertainty, doubt.
I've never known it meant that.
Hmm?
I've never known it meant that.
Oh yeah, I know the thing from GME. About GME, what's it doing?
I think staying regularly normal. Yeah, started off at +5, now it's negative, or at +10, now it's -1.
Whatever. We have the floor.
Exactly.
Not financial advice. Okay. The least squares problem. We're getting there, we're getting there. 2 more lectures and then we are completely finished with all of LA. Except if you want to do more practice. I don't know what else for practice you could really do, but maybe like 7 and 17. Okay, lecture slide. Let's see. So we have the least square solution of a system is defined as the vector x hat such that it is the closest to ax is equal to b. Ax is equal to b. How can you check whether it is the least square solution? The difference between b and ax hat would be orthogonal to the columns of A. Yeah, okay, so this line here is orthogonal to A, which makes sense. Following statement: if x1 and x2 are the least square solutions of ax is equal to b, then so is the sum. The thing of the least square solution is that there's one of them. At least I think so, right?
What?
Yeah.
Where?
X1 and x2 are the least square solutions, plural, of ax is equal to b, then so is the sum. This makes no sense whatsoever.
Yes. Well, it
Cool.
depends. No, you're right. I don't know. No idea. If this is the thing, then they failed to teach us this.
Pog. A set of least square solutions coincides with non-empty sets of the solution of the system of A transposed AX is equal to A transposed B, which makes sense because you're just left multiplying everything by A transposed.
Mm-hmm.
Equation of the system are called normal equations. Oh, because these two are normal. Unique law square solution. The system AX equal to B has the uniquely least square solution for each B in Rm. That also means the columns in A are linearly independent, and it also means the matrix A transpose A is invertible. When these statements are true, it's given by A transposed A inverse A transposed B.
Yeah, I want to know. It's easy to see why.
Yeah,
Because
so we have A transposed AX is equal to A transposed B, and we want to know X, so we can left multiply with A transposed A inverse times A transposed A x is equal to A transposed A inverse A transposed B, and we know that this thing here is, something inverse times something, so this is going to fall away, and then we are left with this. Linear models. I was half paying attention during this lecture, and by God, it does not look pretty.
It's actually quite easy.
Okay, that's good.
Yes.
The vertical differences are called the residuals.
Neef, ik ga eten maken. Ik ben klaar.
Okay.
Good luck.
Dank u. It might be that I'm not done by the time.
Oh, I thought Jelle eet smakelijk.
Okay, so we have fitting a linear model to data. So y equals to fucking olive null type shit. B0 plus B1x. Then x1, y1 means you just fill x1 and y1 into x. Okay. Yeah, this makes a lot of sense actually, once you look at it. Okay. Okay. Cool. Sum of the squares of the residuals is, well, you can check this here. So if we fill in x, we get 2, so here it's 0. If we fill in x, we get 3, which is 0 again. And if we fill in x here, we get 5, so the difference here is 2, and the square of that is 4. Does that make sense?
Alleen maar Nederlanders op dit moment.
Yeah, that's correct. However, I'm going to upload this to YouTube, so I'm going to stay English.
Ja, dat dacht ik al. Nice. Lekker.
Yeah. Good that you mentioned it, though. It's interesting. Only the Dutch people are pulling through. Okay, so we can see which one is a better fit by comparing the least squares. That's like literally what it says. The squares of the residuals. So let's see. This one is 4. We've just calculated that, and for this one it is 0.5 squared, which is 1 over 4. For this one it is let's see, 1. So this is just 0. And for this one it is 1. Yeah, because you get 4, a half of 4 is 2, plus 3 is 4, minus 3 is 1. So this is 1/4. So L2 is a better fit than L1. Alright, cool. Least square fitting of other curves. Find B that minimize the, yeah. I don't care about this one, I don't care about this. Okay, let's try to actually see if we can apply this. Pre-lecture, start now. We tried to model the size of a population of mice living in AV. That is pretty funny. To a population using exponential growth model, where n is the number of mice and t is the time in days when we start counting the mice. We can rewrite the equation to ln of n is equal to A plus RT, where A is equal to ln C. Constant A and R are unknown. Table contains the mice counts of a number of consecutive days. Number of mice follows a model of exponential growth. These data points should fit the equation ln n is equal to A plus RT for some constant A and R. This leads to a system of linear equation in the unknown constant A and R. So we have a matrix A times AR is equal to B for some matrix A and vector B. Gives the matrix A and the vector B separated by a comma. So what it's saying here, okay, so we have here the equation ln n is equal to A plus RT. Therefore, we have on the right side, let's actually draw one of these out. So we have ln of 959 is equal to A plus R times 16, and ln of 1135 is equal to A plus R times 17. Therefore, we can swap these around. We can rename these from A and R to x1 and x2. And now we can see that we have something in the form of 1, 1, 16, 17, x is equal to ln 959 ln 1135. And we can do this for all of them. Except for in this case, x is our, what is it called again? Parameter vector. So let's see, we will get a 2 by 1, 2, 3, 4, 5, 6, 7. So we have a 2 by 7, or 7 by 2, my bad, which is just a bunch of 1s. And 16, 17, 18, 19, 20, 21, 22. Oh, comma, a 7 by 1 vector, namely the ln of 959, the ln of 1135, the ln of 1413, the ln of 1705, the ln of 2051, the ln of 2460. Is that correct? Yeah, and the ln of 2994. So this should be correct. Let's go. Is the linear system corresponding to the data fitting problem consistent? By God, it's not. Good luck trying to fucking row reduce this shit.
Yeah, that's just Bane.
Yeah. If the other case would be, if it would be the case, then it would be like, 1, 1, 0 something, 1, 0 something, 0, 0, 0, 0, 0, 0, etc.
Yeah, that's true.
Yeah, but it's definitely not the case. And it will, I can almost promise you that it will certainly never be the case if you're measuring real life data accurately that it will exactly fit on a graph.
Yeah, that's also true.
Yeah. If the columns of A are linearly dependent, then the equation has at least one least square solution. That's correct. Because we saw this, actually it's probably in here as well. Oh. Here, the columns are linearly independent. That means it has a unique solution, and it also means that the matrix A transpose A is invertible. The least square solution of AX is equal to B is the solution AX is equal to B. Only if it actually falls on that line. As we said before, like, if the system actually exists, then POG. But, you know, it probably won't. We can find a set of least square solutions solving the normal equations, which are given by... Okay, so they're asking explicitly for the normal equations. That's this one. We can solve them for this, but they're asking for this. Okay. Given these points, the least squares line is such that the sum of distances, nope. The sum of the squares of the vertical distances is minimal, and the sum of the squares of the orthogonal distances from a data point to the line, no. It's just the sum of the squares of the vertical distances. Cool. Given the data points, we can find the parameters that appear in the equation by solving the system x, b is equal to y, in which b is the parameter thing, and x is equal to 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 3, 1, 5, 1, 7, with y is equal to, and again this is just 1 and then the x coordinates, and then we have the, or the input, and then you have the output, that's 10, 15, 23, 34. Bin up. What's that? Yo, we're having meatloaf! Alright, I will instigate a quick 5-minute break while I eat my meatloaf. Be right back. All right, let's resume our normal schedule. So, and continue. Post-lecture exercises. This is going to be quite something. Find the equation of the least squares line that best fits given data points. All right, let's have a look. So we can fit this to 1, 1, 1, 1, -2, 0, 2, 3, times something is equal to 0, 1, -4, -5. Okay, so I'm going to subtract this one from everything else. This is like definitely not the way to go. Okay. So x is given by a d a inverse times a transpose b. Okay. So let's try to find this. So in this case, the A is equal to this matrix, the quote-unquote design matrix. So we have 1, 1, 1, 1, 1, -2, 0, 2, 3. So we have, this is A. I'm going to store that here really quickly. A transpose is equal to A 1, -2, 1, 1, 1, 0, 2, 3. We want to multiply A transpose by A. Or actually, I should put that over here. And this one over here. So this is, well, 1, 1, 1, 1, that's equal to 4. 3 plus 2, that's 5. Minus 2, that's 3 again. This is equal to 9 plus 4 plus 4. So this is equal to 15. And this is equal to, well, 3 again. So this is A transposed A. Alright. Then we want to find the inverse of this. So let's do that real quick. So this, 1, 0, 0, 1. So I'm gonna multiply this by 3. Yes, this is 12, this is 9, and this is 3. Gonna multiply this by 4, so this is 12, this is 60, and this is 4. Gonna subtract the top one from the bottom one. This will become 0, this will become 51, this will become -3. Then I will divide everything here by 3. This will become 4, this will become 3, this will become 1. Then I'm gonna multiply by, let's see, I'm allowed to use a calculator, so what is 51 divided by 3? 17. Gonna multiply it by 17, so this will become 68. This will become 51. This will become 17. Subtract this one from the top one. So then this will become 0. This will become 20, and this will become -4. Then I'm going to subtract to divide everything by, I guess, 68. 20 divided by 68. Well, that doesn't work. Makes sense. I'm gonna divide everything by 4 at least, because I know that works. So this becomes -1, this becomes 5, and this becomes 17. So this is 5 divided by 17, this is -1/17, and this becomes 1. Then we have 51 divided by 3. Okay, so this is 1, this is minus 1 over 17, and this is minus 4 divided by 51. So this is the inverse matrix of A, or the inverse of this thing. So we have A transposed A inverse. That's equal to this thing. So then we multiply this by A transposed. It's going to become 1, 1, 1, 1, and negative 2, 0, 2, 3. What an exercise. Luckily this is 1 of 4, so it makes sense, but minus 2 over 17, or actually this is going to be 2 over 17 plus 5 over 17, so this is going to become 7 over 17. This is going to become 5 over 17, this is going to become 3 over 17, and this is going to become 2 over 17. This one's going to be a little bit more annoying. This is going to be negative 8 over 51 plus, let's see, so that's, or minus 3 over 51, so this is 11 over 51. Then this is equal to, how will this even be a 2 by 2 vector once we're done with this? Oh wait, I see how that can be a 2 by 2 vector once we're done with it. Okay, cool. So this is minus 1 over 17. This is 8 over 51 minus 3 over 51. That's 5 over 51. And this will be 12 over 51 plus 1 over plus 3 over 51. That's 15 over 51. So this is equal to A transposed A inverse A transposed is equal to this thing. So then we multiply this thing by B. So I put this one over here, and B is 0, 1, minus 4, minus 5. Whew, this sure is an interesting problem. So this is minus 10 over 17, minus 12 over 17, plus 5 over 17. Therefore, this is 22 over 17, which ends up with 17 over 17, or minus 17 over 17, which is actually equal to minus 1. And now this one, which is minus 75 over 51, minus 20 over 51, minus 1 over, oh, this should be 51, minus 1 over 51. So this is all in all 95 minus 96 over 51. Is that correct? So this is 0, 1, minus 4, minus 5. 0, 1, minus 4, minus 5. So again, we have, this is 75, this is, oh, I think I fucked something up. So this is 75. Yeah, this is divided by 17, so this should be 3. So this should be negative 3, yeah. So then we will get 98 over 51. So then this will be the answer. I very much doubt this is it, but I am very much willing to try. So I made a calculation mistake somewhere. So this step is, I already fucked up this step. This will be a 17 instead of a 15. That's even less pretty. What the fuck?
Bruh.
Fucking hell. Final result. DY Graspel, very cool. Fucking hell. Okay. What's the residual for the first data point? Well, I can remove this entire thing. And this as well. But their answer was, let's see, B1 was the first one, so that's negative 67 over 59 plus x, or minus 78 over 59x. Filling that in will give... Oh, I don't want to fill this in. At least we know it should be x, or it should be 0, and then this should be 2 times that. So then I can grab my calculator and say 57, or sorry, 67 plus 2 times 68. 67 plus 2 times... Oh! 67 plus 68 plus 68. So that means we have negative 203 over 59. The expected answer was negative 2. Or no, the expected answer was 0. So the residual is this thing. And since it's a distance, I can remove this, I think. The difference between the observed value y1 and a predicted value, well, y1 was just either they're 0 indexing or I made a mistake. I sure hope they're not 0 indexing. Yeah, so it should be minus 67 minus 68 minus 68. 203 over 59. What the fuck?
You forgot the minus sign.
Yeah, but it's about a distance, right? And even then.
What?
Okay, what's their fucking answer? Yeah, but that's not the first one. That's the second one. Holy shit, they're 0 indexing. What is the residual vector? Yeah, no, you can suck a fat one.
Comments skip.
Fucking hell. If the test is like this, I will just cry, honestly.
Yeah.
I should really do it because it's good to try. But at least give us less data points. Alright, so we have A is equal to 1, 1, 1, 1. 2, 3, 5, 6. Why are these bold? So we have A transpose that we multiply by A. So we do this, and then we transpose it, which means 1, 1, 1, 1, 2, 3, 5, 6. So this will become 4. This will be 6 plus 5 plus 3 plus 1, which is 9 plus 7, which is equal to 16. This is going to be 16 as well, and this is going to be 36 plus 25 plus 9 plus 4. Oh, 4. Well, 4 plus 36 is equal to 40. This is equal to 34. This is equal to 74. Boy, this is going to make calculations a lot of fun. So this is A transposed A equal to this thing. Then I have to take the inverse. 1 0 1 1 0 0. So I'm gonna start by multiplying the top row entirely by 4, which will give me 16. This will turn into 64. This will turn into 4. Subtract the top one from the bottom one. This will become 0. This will become 10. This will become minus 4. Then divide the top row by 4 again. This will become 4. This will become 16. This will become 1. Subtract the top. Divide the top row by. Yeah, nothing really. I'm gonna divide it by 10, just to humor it. Or no, I'm not gonna work with fucking fractions. Okay, 40, 160, 10, and it's gonna become 160. This is multiplying by 16. So this is gonna make it 64, and this is gonna become 16. Subtract this one from the top one. This becomes 0. Subtracting 64 becomes 74. Subtracting 16 becomes negative 16. This one will become, this is divided by 40. This is divided by 40. This is divided by 160. This is, and this is divided by 160. I understand why I don't like these. I'm gonna multiply these by 4 as well. So that is going to be 280 plus 16, that is 296. 296 over 160. And this is going to become negative 64 over 160. Because then we have everything in terms of 160, which is going to make the later computations a lot easier. Quote unquote.
Fair.
Okay, then what? So now we have this, and we should multiply this by A transpose again. You know, I'm really starting to not feel this. 1 1 1 1 2 3 5 6. Oh, let me fix that again. I said let me fix that again. Oh. What? Okay. And can I now drag the entire line out? Whatever, good enough. So this is going to become... You know that this is a really interesting subject. But fuck this. Negative 1. I'm just going to leave out the divided by 160 and add those in later. So this is going to come negative 128 plus 269, 296. I'm going to fill that in my trusty old calculator. It's 168. And then 296 minus 64 times 3. So we have 296 minus 64 minus 64 minus 64. That's 104. Then 15 means 296 minus 64 minus 64 minus 64 minus 64 minus 64. That is not... Is that correct? Fuck. Okay, what I'm going to do instead is I'm going to say negative 64 times 5 plus 296. Okay, so this is indeed equal to negative 24. my word isn't big enough. I can't imagine doing this on paper, man. Doing this on paper would be such a fucking mess. I'm gonna at least bring like 10 to 20 pieces of paper. And then we subtract another times 64 from this, so this will become negative 88. Same thing here, so we have negative 64 plus 2 times 16, that's negative 32. We have that plus another times 16, which becomes negative 16. We added ones too much, so that's becomes 16. Then we added ones more, that's 32. But these numbers are at least a little bit better. So this is A transpose A inverse times A transpose. So then we can multiply this matrix by B. So let me fill that in here. Yeah, okay. And this is all divided by 160. 160 divided by 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 160 and divided by 160. And then the B is the result column, here called the observation vector, which is 3, 2, 1, 0, which means it is minus 24 plus 208 plus 168 plus 168 plus 168. Space.
Good luck with the last parts and bits. I'm gonna have dinner.
Thanks.
I might join you if I'm done on time, but
alright.
we'll see.
Have a good one and enjoy your dinner, man.
Thanks. You too. Thanks for doing this.
You're
really
welcome.
appreciate it. You.
I'm glad. Bye bye. Okay, so then we are left with 16 plus or minus 32 minus so we have 16 minus 32 minus okay, I see. So minus, and that's 32 minus 32 minus 32. That is a negative 112. So then that is the vector of 668 divided by 160 over negative 112 divided by 160. Alright, let's see if using their way actually works as well. Because honestly, it probably does.
Okay, I can do this one. Give me the design matrix. 1, 2, 3, 4, 5, 6. So the design matrix is 1 minus 4, 1 minus 2, 1 minus 1, 1, 2, 1, 3, 1, 5. Oh, and we all, okay, yeah. It's 1, it's the number itself. Okay, yeah. Didn't see that, my bad. So we have 1, 1, 1, 1, 1, 1, 1. Minus 4, minus 2, minus 1, 2, 3, 5. $16, 4, 1, 4, 9, 25. And the output will then be also a, yeah, this one. Okay, so we have A being 1, 1, 1, 1, 1. Negative 2, negative 1, 2, 4, 5. Then we have A transposed being 1, 1, 1, 1, 1. Negative 2, negative 1, 2, 4, 5. And we want to multiply this by y, which are the results. The result is a 1 by 5 vector, so I should put this over here and the results over here. The results are 4, minus 3, 4, minus 3, 5. Fuck is this linear? Okay, cool. So this is equal to 5 minus 3 plus 4 minus 3 plus 4. Put it into my calculator. Whatever, 4 minus 3 plus 4 minus 3 plus 5. Okay, so that's 7. And then we have 25 minus 12 plus 8 plus 3 minus 8. So that is 16. So the right hand side of this equation is equal to this thing. So RHS is equal to this. And the left hand side of this equation is equal to A transpose times A. And that is what we want to solve. So let's see, let's first get A transpose A. So let's take A transposed. So let's see, 1, 2, 3, 4, 5. That is 1, 1, 1, 1, 1. Negative 2, negative 1, 2, 4, 5. And here we have A, which is 1, 1, 1, 1, 1. Negative 2, negative 1, 2, 4, 5. This is 5. This is, let's see, this is, oh. This is 20, or actually this is the right hand and the bottom there, okay, so that is equal to 5 plus 4 plus 2 plus minus 1 minus 2. This is equal to 8. Same thing goes here. I'm going to do it again though. 5 plus 4 plus 2 minus 1 minus 2. That's 8. And here it becomes interesting because we have 25 plus 16 plus 4 plus 1 plus 4. 25 plus 16 plus 4 plus 2 plus 4. So this is 51. Check it again. So this is 25 plus 16. 25 plus 16 is 41. Then we add 4, that's 45. Then we add 1. Then we add 4. That becomes 50. Wait, what? So this is 25 plus 16 is 41. That's 45. That's 46. That's 50. So I made a mistake somewhere. Let me check that again. That's 25 plus 6. Oh. 25 plus 16 plus 4 plus 1 plus 4. Okay. So this is the left-hand side, or at least this part of the matrix. So this times x is equal to that. So now we want to know... Okay, now I can just row reduce this one. Okay, so let's row reduce this one then. Multiply the top row by 8, that becomes 40, 64, 56, is that correct? Yeah. Okay. Bottom row by 5, so this becomes 40, this becomes 250, this becomes 80. Subtract the bottom row from the top row. So, or let's do the top row from the bottom row. So this becomes 0. This becomes 250 minus 64. This becomes 186. And this becomes 80 minus 54. So this is actually equal to 24. Is this actually equal to some nice number, or are they fucking with me again? Okay, valid. And if I multiply that by 4, so this is equal to 31 over 4, 1. Is that correct? By the way, this would then become 70. Yeah, okay, so this would be 7.75. 1 multiplied by 4. This becomes 4. And this becomes 31. And then this is 1, and this becomes divided by 31. Okay. Then I can subtract. Oh god. Subtract 64 times this one from the top one. Then this becomes 0. And this becomes this minus 64 times 4 divided by 31. Okay, so this becomes minus 64 times 4 divided by 31 plus is that correct? Yeah, that seems about correct. Plus 56 or 50. I clicked the wrong fucking button. Okay, minus 64 times 4 divided by 31 plus 56 times 31. So this is equal to 1480 divided by 31. Then I can divide this by 40. So this is actually equal to 37 divided by 31. So if I'm correct, this is going to be 37 over 31, and this is going to be 4 over 31. No fucking way. Okay. Dude, holy hell. Alright. I mean, you guys understand that I'm getting a little bit emotional with linear algebra after almost 7 hours of it. But yeah. Next one. I'll over their word equal point. So let me see. Get rid of this. Get rid of all of this. So we have A is equal to 1, 1, 1, 1, 1, or actually 1, 1, 1, 1, minus 2, minus 1, 1, 3. We want to find AX is equal to B. We left multiply by A transpose. Okay, so then we find that A transposed A. So then we start with A transpose, which is 1, 1, 1, 1, 1, minus 2, minus 1, 1, 3. Yep, and then multiply by 1, 1, 1, 1, minus 2, minus 1, 1, 3. This becomes 4. This becomes 3 plus 1 minus 1 minus 2. So this becomes 1. Same here. Is that true? That's 4 minus 3. Yep, that's true. This becomes 9 plus 1 plus 1 plus 4. So this becomes 4, that's 15. Cool. So the left hand side is 15 times x. Or left hand side is this, sorry, times x. And then the right hand side is A transpose times B. So that is 1, 1, 1, 1, negative 2, negative 1, 1, 3. And then here the B is equal to negative 2, negative 1, 2, 0. So this will become 2 minus 2 minus 1 is minus 1. This become 2 plus 1 plus 4. 2 plus 1 plus 4, that's 7. Is that correct? 2 plus 1 plus 4, yep, that's 7. So the right hand side will become this. That means I can go ahead and delete this all. I can copy this over. And then this is what we are going to solve. Multiplying the bottom by 4 gives 4, 60, and 28. Subtracting the bottom or the top from the bottom will give 0, 59, 29. Dividing this all by 59 gives 1, 29 divided by 59. Subtracting the bottom from the top will give 0, 1 minus 1 minus 29 divided by 59. This is equal to minus 59 divided by 59, which is equal to minus 59 minus, yep, so this divided by 59. Or actually this is, yeah, okay, I can do that. Which is 88. Is that correct? 29 plus 59, that's 88, yeah. So this is minus 88 divided by 59. Then we divide both sides by 4, which gives minus 22 divided by 59. So this is the 2 by 1 matrix of minus 22 divided by 59, 29 divided by 59. Whew! Okay. What is the residual for the first data point? Well, we've got a formula now, namely minus 22 over 59 plus 29 over 59x. For the first data point, well, we want this one or this one. They are very vague about that. So minus 2, I'm going to say this is equal to, this is minus 2 as well. 2 times this thing is equal to 58. So let me put this in here. I think the answer is well, different should be positive. Now what the fuck is wrong? They're talking about y1 and x1, which I think is this one. Holy fuck. Let me actually test that. So they had -1, -1. So they had the difference between -1 and -22 divided by 59 minus 29 divided by 59. Which is equal to 51 divided by 59. No, but even that shouldn't make sense. Huh, so it is the I don't know. What is the residual vector? Okay, so my calculation for this one was correct because it was the difference between 1 and this. Or -1 and this. So it should be this minus -1 is equal to 8 over 59. So that I just fucked up somewhere within my calculation for the first one. Okay. Honestly though. Give the design matrix X, I can do that one. 1, 2, 3, 4, 5, 6. So that is 6 times 3. So then we have -4, -3, 0, 2, 4, 5. Then we have 11, 4, 5, 6, 8, 15. And then we have 121, 16, 25, 36, 64, and 225. It's the design matrix. I'm a fucking dumbass. Oh, clicked the wrong button again. I can do this one, he says. So it's 1, 1, 1, 1, 1, 1, 1. It is -4, -3, 0, 2, 4, 5. Oh. And it is 16, 9, 0, 4, 16, 25. That makes a lot more sense as well. Find the least squares line that best fits this thing. Your wish is my command, apparently. 2, 3, 5, 6. And then we want ax is equal to b. We want a transposed. Ax is equal to a transposed b. So let's get a transposed in here. This is 1, 1, 1, 1. And we have 2, 3, 5, 6. And then we put the original one here. This is equal to 4. This is equal to 6 plus 5 is 11 plus 3 is 14. That's 16. This is 16 here as well. And here we have 36 plus 25 plus 9 plus 4. I think I've actually done this one before. This is 40. This is wait, I didn't fuck it up, right? Okay, yeah. 40. So this is 65. This is 74. So the left hand side is 74x. Or the left hand side is this thing, x. And the right hand side is A transpose times B, which is 1, 1, 1, 1, 2, 3, 5, 6. And B, which is 3, 2, 1, 0. So this is 6, and this is 5 plus 6 plus 6, which is 17. So this is what we want to solve. Okay. Got this. Oh, put it down there. Multiply top row by 4. This will give me 16, 64, 24. Subtract top row from bottom row. This will become 0. This will become 10. This will become -7. Okay. I will multiply this by 10. This by 64. What is 7 times 64? Well, let's have a look. 448. Subtract this from the top. This will become 0. And it'll become minus 448. This will be something like negative 192, but I've been doing maths for 7 hours, so I'm beginning to doubt my sanity because of reasons like that. So this will become, let's see, what's the best way to reduce this thing? Can I do 448 divided by 64? Fuck. Fuck. 7. Okay, so this is equal to, it will be 10 and this will be negative 7. So this will be 1 and this is negative 7 divided by 10. It's a lot better. And then this will be negative 208 divided by 160. Okay, so that is a better way to do that is negative 208 divided by negative 208 divided by 16. So this will be 10 and this will be negative 13 and this will be negative 13 divided by 10. Therefore, the answer to this one is negative 13 over 10 and negative 7 over 10. Wait, so this one was correct. I just fucked up something in the top one. Okay, that's good to know. 1, 2, 3, 4, 5, 6. 6 times 3. Then it is 1, 1, 1, 1, 1, 1. Then it is negative 4, negative 2, 0, 2, 3, 6. 16, 4, 0, 4, 9, 36. I've got to get one of these right someday, right? Might as well be today. So then we will get 1, 1, 1, 1. This will be 2, 3, 5, 6. This will be 1, 1, 1, 1. Oh, one too many. 2, 3, 5, 6. I think I've done this one before. 4. This will be 6 plus 5 plus 3 plus 1. This will be 16, 16. And 36 plus 25 plus 9 plus 4. This is 74. So this is the left hand side. Or actually, I should not get rid of this. Let me put that here while I copy this over here. Store this one away over here. And the right hand side will just be the answers. So that is 3, 2, 1, 0. So this will be 1 plus 2 times 3. This is 6. And this will be 5 plus 6 plus 6. That is 17. This is literally the one I did just now. They are starting to run out of problems to give me because I am so inadequate. Okay, multiply everything by 4. This will give me 16, 64, 24. This will be 0, 10, minus 7, 1, minus 7 divided by 10. This will be 0, and this will be minus 7 divided by 10 times 64. And then I divide this whole thing. Wait, is that correct? So I subtract 64 times the bottom one from the top one. So minus 64 times minus 7 over 10. And then I divide this whole thing divided by 16. This is actually not a 1, this is a 0, and this is a 1 then. I have stopped trying to simplify, as you can tell. So this is 24 minus 64 times minus 7 over 10 divided by 16, and this is minus 7 over 10. This should be a 1. That felt so good. Alright. Last one, hopefully. So we have the design matrix. Let's see, we want AX is equal to B. We do A transposed, A transposed. So we have 1, 1, 1, 1, -2, 0, 1, 4, 5. Oh god, this is a 5 mod 1, but it should still be easy. And then here we will have 1, 1, 1, 1, 1, and -2, 0, 1, 4, 5. This is going to be 5. This is going to be 5 plus 4 plus 1 minus 2, which is equal to 8. So this is going to be 5, 8, 8, and this is going to be 25 plus 16 plus 1 plus 4, and this is going to be 47. So this times x is the left hand side. I'm actually going to put that over here, and then I can take A transpose and multiply that by B, which is the result factor. So minus 5, minus 2, 3, minus 5, minus 1. This will be minus 1, minus 6, plus, or minus 3, minus 5, minus 10. This will be minus 5. Okay, I'm actually going to do this in Google. So this will be minus 5, minus 20, plus 3, plus 10. This is going to be minus 12. So I can copy this thing, put it at the end of this, delete this, got this, put it in here. Alright, multiplying this one by 8 will give 40, this will be 64, this will be negative 80. Multiplying this one by 5 will give 40, this will be this times 5, and this will be negative 60. This will be equal to 230. I can subtract the top one from the bottom one. This will be this minus 64, and this will be this plus 80, which is 20. This will be 116. Then this will be 1, and this will be divided by 116. I can divide everything here by 4, which will become 10, this will become 16, this will become 20. Yeah, okay, I'm dividing by 4. Yeah, this is 16, this will become negative 20. Then I'm going to add, or I'm going to subtract 16 times the bottom one. So minus 16 times 20 over 116. And then divide this whole thing by 10. Wow. It feels so weird, but after a while you just get not good, but decent at it. So minus 20 minus 16 times 20 divided by 116 over 10. And this becomes 20 divided by 116. Okay, I made a mistake somewhere. $83? Huh. Alright, interesting. I don't want to do this one because this will only award me a third of a point. I want to do that one, yeah. Sure, I'll take this one as the last one for this one. So then this will be, oh god, that's 6. That is really annoying. Either way, so this is... You know what? I've done it so many times. I'm just making dumb mistakes, but I know how to do it. So I'm calling it knowledge % done for this one. I'm done though. That's post-lecture exercises done. I'm now going to do the pre-lectures of the last one, which will be symmetric matrices. What about them? Good question. So this is a symmetric matrix and not orthogonal. Well, yeah, that makes... yeah, because an orthogonal matrix has to have orthonormal columns. Hello, welcome back.
Hello.
How was your dinner?
Yeah, it was good.
I'm glad to hear
Lovely.
it, man.
Nice.
What do you have?
You're still going?
Yeah. I actually had to quit early on lecture 11 because I spent over an hour on it and I couldn't get like I just kept making dumb small mistakes.
Oh yeah.
But that's what happened when you spend 7 hours in a row just working on it.
Yeah, that's insane.
Yeah.
Really insane, man.
But
And
yeah.
now you're doing lecture to
The last
when?
one, so that's 20. Looking at
Nice.
yeah.
Nice, man. I'll have a OP meeting in like 20 minutes or something, but I'll stick along as long as I
Yeah.
can.
Thanks. It was getting kind of lonely.
Yeah, I can imagine.
Yeah. I can imagine other people don't really feel like it after 7 hours as well, though. But I don't blame them. But yeah. Okay, so as we were saying, so this is a symmetric matrix. It's not orthogonal because the columns of an orthogonal matrix have to be orthonormal. Every symmetric matrix only has real eigenvalues. Okay. If A is a symmetric matrix, then two eigenvectors of A belonging to different eigenvalues are orthogonal. So, so any two. So all of them are orthogonal together. So they form an orthogonal set. An m by m matrix A is orthogonally diagonalizable if there exists an orthogonal matrix P. An orthogonal matrix P, which means orthonormal, okay? And a diagonal matrix D, such that A is equal to PDP inverse. Since P is an orthogonal matrix, this is equal to this is equivalent to A equals P transposed. Oh, guys had enough. A is symmetric if and only if A is orthogonally diagonalizable. Cool. The special theorem. An n by n symmetric matrix has the following properties. It has n real eigenvalues counting multiplicities. For each eigenvalue, the geometric multiplicity is equal to the algebraic multiplicity. The eigenspaces are mutually orthogonal. So all of them are orthogonal together. And A is orthogonally diagonalizable. And the algorithm for it is compute the eigenvalues. For each eigenvalue, construct the basis of the corresponding eigenspace. For each eigenvalue, construct an orthonormal basis of the corresponding eigenspace using, again, orthonormal. So we use Gram-Schmidt to orthogonalize and then scaling to normalize. And then we construct the matrix P using the basis vectors as columns and matrix D using the corresponding eigenvalues on the diagonals. No questions? Okay. A is orthogonally diagonalizable and B is diagonalizable. We know that A is orthogonally diagonalizable because it is symmetric, that those two are synonymous. And we know B is diagonalizable because it is a triangular matrix and therefore the eigenvalues are 2 and 4. I'm getting so many fucking messages. Give me a sec. Where are they coming from?
Yeah, take your time.
Oh, I found it. Okay, they're talking in the Minecraft Discord. For an hour.
Minecraft is nice.
Yeah, for sure. I speedrun it. I have our server has like 12 or something world records.
For real.
Yeah, I started it with like the TU Delft group, so we had like 10 people, and we got the first like ever run in the category 10 plus. And then we just started branching out, and now we have 250 members doing like regular runs every week.
Damn, that's nice.
Yeah, it's really interesting and a lot of fun.
Oh, nice. I only play it with the OG boys.
Fair, fair. All right, let's see. So, if A is invertible and orthogonally diagonalizable, then A inverse is also orthogonally diagonalizable. Yeah, because that means that A is equal to P D P inverse, with D being an orthogonal, with P being orthogonal, I guess then. Let me see exactly what it means again. Yeah, orthogonal matrix P. Then A inverse is equal to PDP inverse is equal to P inverse D inverse P inverse, which is equal to P D inverse P inverse. And since a diagonal matrix has an inverse, that means that this is true. Okay. This matrix is symmetric. To determine K, let's see. Well, we know for a fact that that this thing has to be orthogonal. So we know that these three are orthogonal, so we can construct, let's say, 2, 1, 0, 1, minus 2, 1, 0. Is that? No, that's not the right thing to do actually. So we know that 2 minus 2 is equal to 0. Well, that makes sense. We know that 2 plus 1 plus k is equal to 0. Well, okay, that makes sense. And then we can get k to the other side, and this will become minus 3. Okay.
That worked.
Hmm?
That worked.
Yeah, I mean, we know that everything of this has to be orthogonal with each other. This column won't tell me anything about k, so the only thing is these two. And that that works. Alright. Wait, that's it? Wow, okay. So that means we have now read every single lecture and information piece about linear algebra that we have to know. It feels really weird to say, but it's also really, really fucking nice.
Yeah.
Okay. So let's go to Graphable. Pre-lecture exercises. Is the matrix symmetric? Yes. That's 1 out of 5. Is this matrix symmetric? No. 2 out of 5. Is this matrix symmetric? Nope. 3 out of 5. This is going well. This matrix symmetric? No. 4 out of 5. Is this matrix symmetric? Yeah. Fuck.
Almost.
Yes. Almost
So
100%. Feels bad, man.
Okay. It's green.
Still green. That's a W in my book. Okay, there are symmetric matrices that are not orthogonally diagonalizable. False, because these two are interchangeable. If P equals to B equals to PDP inverse, where PT equals P inverse, so that means that P is orthogonal, and D is a diagonal matrix, then B is a symmetric matrix. Yes. Because this basically means that B is orthogonally diagonalizable, and that means that they are symmetric. Any orthogonal matrix is orthogonally diagonalizable. False. This is not automatically true, because then you also need an orthogonal symmetric matrix. The dimension of an eigenspace of a symmetric matrix may be less than the multiplicity of the corresponding eigenvalue. That's false, because they're always the same. So the algebraic and geometric multiplicities match for each of its eigenvalues. Is the following statement true or false? There exists square matrices ADP, APD, for which A equals the PDP inverse, D is a diagonal matrix, and A is a symmetric matrix, and the columns of P are not orthogonal. You see, A being a symmetric matrix means that A is orthogonally diagonalizable. So that means there exists PDP for which P is orthogonal. I'm not sure if that also means that there doesn't exist a P for which is not orthogonal, but I'm going to say true. Yeah, okay. Okay. Can you find an example for the previous statement? So try to construct matrices. So let's see. Yeah, this is the last one. Try to construct matrices PDA for A equals PDP inverse. D is a diagonal matrix, A is a symmetric matrix, and the column of P are not orthogonal. Make sure you work with 3x3 matrices that give your answer as PDA. So in this order and separated by commas. Not orthogonal. Okay, let me think. What is the inverse of the identity matrix? Still the identity matrix, right?
Yeah, my brain functions are going down, so whatever.
Understandable. Okay, so what I've got is if we have the identity matrix is equal to the identity matrix multiplied by the identity matrix multiplied by the inverse of the identity matrix. And it's actually not orthogonal because fuck, it's orthogonal. Damn it. Actually, I think So I was on the right path though. So if A is a diagonal is the identity matrix, and D is the identity matrix as well, then P can be any invertible non-diagonal matrix. So what I'm thinking is I is equal to P I P inverse. Well, P times I is just equal to P, and I is equal to PP inverse, and this holds for anything as long as P is a for as long as P is invertible. So I need to have an invertible matrix. Okay, wait. Okay, the inverse of it. I just picked a random 3x3 matrix which is invertible from Google. So I have 1, 2, minus 1, 1.
Make sure to do P at the beginning. Make sure to do the P matrix at the beginning.
Good call. That would have cost me points.
Yeah.
So this is 1, 1, 1, 0, 0, 0, 0, 0, 0, and then some random invertible matrix. So that is 0, 0, 1, 2, minus 2, 1, minus 1, 1, minus 1. Let's see, is that correct? Yeah, I think so. Then we have P, and then we have D, and then we have A.
Nice.
Feels good. Okay. Vakkenstrijder, last one. 0 out of 5. Find. Okay. Okay.
Initiate
Fucking hell.
crying.
Fucking hell, man. Okay. You may use the fact that A has eigenvalues, blah blah blah. Therefore, I'm going to start with eigenvalue 27. So I'm going to start with minus 9, 12, 6, 18, 6, 18, 3, 12, 6. This whole thing is like divisible by 3. I'm gonna subtract 27. So this is gonna be minus 27. That will be 39, 36. Sorry. Minus 27 is minus 24. Minus 27 is minus 21. 0, 0, 0. So then, okay, I can multiply this one by 2. This will become 12. This will become 36. This will become minus 42. I can subtract this one from that one. So this will become 0. I will subtract 36 from minus 42 to 24. This will become 60. I will subtract minus, so this will also become 60. So this will become 1. Bin up. This will become minus 1. Bone jaw. After this one I'm done. So how long do I have?
No, however long you want.
Okay. Sure, won't be too long. Finding the orthogonal diagonalization of a matrix.
I just said the Thieves' Knave. On the exam, they will have better values, so the Thieves.
Ha, fair. I mean, these are relatively alright. Everything's divisible by 3. It should be, like, not too bad. Not really. I see. My brother disagrees with the divisibility of everything, but we'll see. So this will add
I think eventually only numbers in the eigenvectors
36.
are 1, 2, and a half. So
Yeah, exactly. I don't. Yeah, I don't think this is too bad actually. So this is negative 2. This is negative 1. This is 2. This is negative 1. Well, we know that this is a multiple because we're looking for eigenvalues. And then I can say I'll multiply by negative 1/2. That become 1. Yeah, so the columns are orthonormal.
Yes.
Yep. Ben up. Yep. Ja.
En 2, blijf dan een plekje in yellow op het record op 26, 34 ding. Terwijl je op 26, 32 wil denken, daar zit like, veel minder blokken en veel minder cleanen.
Wat gaat in voor duo's?
Als in voor duo's en voor quads. Gaan we even de duo voor terugpakken, want het is net een minuut van.
Fucking yikes. Alright, good luck. Alright, so this is equal to, this is equal to, like this. Okay, so this is 1/2, 1, 1. Okay, about the next one, minus 18. Oh, also the, let's see, PDP. So in this case, the D matrix will just be 27 minus 18 minus 9. So I can already fill that in. So that becomes minus 9, 12, 6, 12, 3, 18, 6, 18, 6, and then we subtract minus 18, so we add 18, so this becomes 9, this becomes 21, this becomes 24. I will divide this by 3, this or by 2, this will become 3, this will become 9, this will become 12. I will multiply this by 3, this will become 9, this will become 27, and this will become 36. I'm going to subtract the top from the bottom. This becomes 0, this will become 15, and this will become 30.
Hey man, good luck with the last 5 exercises. I have to go to a meeting.
Yeah, alright. Have a good one, man. Thanks for
See you
staying. Bye
later.
bye.
You.
Okay, then I will divide this by 4. No, I'm gonna divide this by 3. This is 3, this is 4, and this is 2. Multiply this by 4, this is 12, this is 16, and this is 8. Subtract the top one from the bottom one. This is 0, this is 5, and this is 10. We know these two are multiple of each other. And then I can also do minus 16 here. So this will become 0, and this will become minus 16 times 2 is minus 32, so this will be minus 24. So this will be minus 2, this will be 1. Equal sign, negative sign away. So this will be 2, 1, or 2 minus 2, 1. Is that correct? Yeah. Yeah, okay. Last one is minus 9. If I got this one correct, then I fully trust myself to do the rest as well. Because this is like super tedious and long taking. 12, 3, 18. And also 6, 18, and 6. So I will subtract minus 9. So I'll add 9. This will become 0. This will become 12. And this will become 15. Okay, starting out, I will double this this column. This will become 12. This will become 36. This will become 30. Then I will subtract this one from this one. This will become 0. This will become 24. This will become 12. I will half this. This will become 12. This will become 6. I will subtract the top one from this one. This will become 0. This will become 0. I will subtract the top one from this one. This will become 0. This will become 12. This will become 1. This will become 1. This will become 1. This will become 1 half. Therefore, this is equal to minus. This is equal to minus. Therefore, this is minus 1 minus a half 1. So we have the 3 columns, or let's call them the 3 eigenvalues. Sorry, the 3 eigenvectors. All right. Given these 3 eigenvectors, we need to make them diagonally, or we need to make them orthonormal. So right now, I need to check if they are orthogonal yet. So I will multiply this one by that one. So that is 1 minus 2 plus 1. That is. I'll multiply the first one with the last one. That's minus 1 half minus 1 half plus 1. That is. I'll multiply the second one by the last one. That will be minus 2 plus 1 plus 1. That is. Luckily for us, all 3 of these are already norm. What are they called? Orthogonal. So now I can make them orthonormal, and then we should be done. So that is let's see. So this is. I need to know the magnitude of this thing. So that is the square root of 1 over 4 plus 1 plus 1. So that will mean that this thing is 1 over 2 divided by the square root of 2 plus 1 over 4. This will be 1 divided by the square root of 2 plus 1 over 4. Actually, that's like way too big to write when I just realized that this is equal to, so the square root of 2 plus 1 over 4, that's equal to 9 over, square root of 9 over 4, which is equal to 2 over 3. 3 over 2. Is that correct? 9 over 4, 3 over 2. Yeah. So we divide this thing. We divide this thing by 3 over 2. We do 1 divided by 3 over 2. Well, divided by 3 over 2 is the same as multiply by 2 over 3. And same here. No. Same here, 2 over 3. And I can actually say this is 2 over 6 then. Okay. For the second one, we have got square root of 4 plus 4 plus 1. That's square root of 9. So I can say divide this by 3. So that's 2 over 3 minus 2 over 3, 1 over 3. And then for the very last one, that is same thing. We are looking at the same column, so that is 2/3 as a as something you should multiply by. So that means this is minus 2/3 minus 2/3, and this will become, or this is positive 2/3, excuse me, and it'll become minus 2/6. Check my answer. Suspense fucking killing me, man. No, fuck! I swapped around P and D. No. Okay. Retry. Can I copy paste this? Comma. Yeah, because P doesn't have to be diagonalizable, and D is a diagonal matrix. That is correct. Ah, feels good. Whew. Okay, we know that 5 is an eigenvalue. We know that 111 is an eigenvalue. Binnen! Yeah, yeah. So we have ax equal to lambda x. We know, in this case, av is equal to lambda v. Well, we know that, let me copy this over. We know that 4 minus 1 minus 1 minus 1, 4 minus 1 minus 1 minus 1, 4 times 1, 1, 1. This will become, well, these are all just going to be the same, but this will be 2, 2, 2, 2. So we know the other eigenvalue is 2. And since we know that okay. So we know the eigenvalue of 5, we know the eigenvalue of 2, and there's another one. There is another. Let's see. I'm actually gonna do the cofactor expansion. There's probably a better way. However, I'm fine using this because I need to train it again as well. So it is 4. Actually, gonna do that here. 4 times determinant of -1, -1, or -1, 4, -1, -1, 4, plus or minus the determinant of -1, -1, -1, 4, minus the determinant of -1, 4, -1, -1. So that is 4 times, fuck, instead of 4 it should be 4 minus L every time. Okay, and if we have a matrix like this, we know it is first one times last one minus the product of the second two. So this is going to be 4 minus L squared minus 1 or minus, well, it's going to be minus 1 times -1, which is minus plus 1, which is like this. Okay, minus the determinant of, or minus -1
times 4 minus L minus 1 minus the determinant of 1 minus 1 times 4 minus L. Let's see, equals 0. And this should not be the determinant, this should just be this thing. Okay, 4 minus L squared is equal to 4 squared minus 8L minus plus L squared minus 1, that will become 15. Turning this around gives L squared minus 8L plus 15. Multiplying everything by 4 gives 4L squared minus 32L plus 60 minus, this is 1, so multiplying this by minus 1 gives this, minus 1 gives this, and then we can get, oh, I fucked something up. Okay, so multiplying by minus 1 gives this, subtracting 1 gives this, multiplying by minus 1 gives this. So this is going to become 65, subtract 1 more L, this is going to minus 33L, and it's going to become 1 minus 1 times this thing, so this is 1 minus 4 plus L, 1 plus 4 minus L, that's going to become minus, 5 minus L, this is going to come plus, this is going to come minus, this is going to come a plus, so we subtract 1 L again, we look at this, this is also 6t, so then we're back at square 1. That means we can divide everything by 4, this is going to become 15, this is going to become 8, and this is going to become L. Then we have holy shit. This should not be 4, this should be 4 minus L. Well, luckily we know that these two cancel out now. Let's see if that's correct. So at first this was 32 plus 60. And then afterwards it was 32 plus 60. So we know these two cancel out. That's good. And we only have one equation to worry about. So that's 4 minus L times this thing. And I think actually this is a great way to show this. Because then we have L squared minus 32L plus 15. So then we have 4 minus L is equal to 0, or this is going to become L minus this is weird. I know it's not these values, but it should be those values. You know what? Fucking whatever. Highest eigenvalue is 5, 2, 1, 0, 0. 4, 2. Too bad. You know what? I'm done for today. I did the previous one correct. I'm good enough. I've been busy for 7 hours and 40 minutes. There's nobody even here listening. Well, no, maybe Kiki Gogo 9, but apart from that, I'm alone. I think it's good for today. Good luck in your exam, King.
Thanks, man.
Alright. Bye-bye.